Welcome to the Comprehensive Data Scientist full course for 2023. In this course, we will cover essential topics to equip you with the skills needed to excel in the dynamic field of data science. Without further delay, let's discuss the agenda for today's session. Module 1 is Data Science in 5 minutes. Get an overview of data science and its significance in various industries. Next, Module 2, that is Top 5 Reasons to Learn Data Science in 2023. Discover why data science is a hot and rewarding career choice this year. Followed by that, we have Module 3, that is Top 10 Data Science Certifications for 2023. Explore the most sought after certifications to boost your career prospects. Proceeding ahead, we have Module 4, that is Data Science Roadmap 2023. Plan your learning journey with a step-by-step guide to mastering data science. Up next, Module 5, that is Data Science Life Cycle. Understand the key phases involved in a data science project from start to finish. Then we have Module 6, that is AI versus ML versus DL versus data science. Difference explained. That is, learn the distinctions between artificial intelligence, machine learning, deep learning, and data science. Up next, Module 7, that is the top 5 best courses for data science. Review the top rated online courses to enhance your data science expertise. Followed by that, we have Module 8, that is Statistics for Data Science. Get familiar with essential statistical concepts for data analysis. Proceeding ahead, we have Module 9, that is R Programming. For beginners, begin your journey into the popular programming language for data science. Next, we have Module 10, that is Top 5 Python Libraries for Data Science. Explore powerful Python libraries to streamline your data science projects. Proceeding ahead, we have Module 11, that is Data Visualization in R. Master data visualization techniques using R. Followed by that, we have Module 12, that is Data Science with Python. Dive deeper into data science applications using Python. Up next, Module 13, that is Types of Distribution in Statistics. Understand different types of statistical distributions and their applications. Proceeding ahead, we have Module 14, that is Probability Density, Functioning and with Example. Learn about probability density functions through practical examples. After that, we will learn Module 15, that is Population and Sample in Statistics Example. Grasp the concepts of population and sample in statistics with real-world illustrations. Followed by that, in Module 16, we have Mean Squared Error. We will study the mean squared error metric used in evaluating machine learning models. Proceeding ahead, we have Module 17, that is Machine Learning Algorithms. Here we will gain insights into various popular machine learning algorithms and their applications. Up next, we have Module 18, that is Skewness and Kurtosis and Movements. We will analyze skewness, kurtosis, and movements in data distributions. Followed by that, we have Module 19, that is Random Forest Algorithm. Random Forest Algorithm, and we will explore the algorithm that is a powerful ensemble method. Next, in Module 20, we have Naive-Bayes Classifier. Here we will understand the Naive-Bayes Classifier and its implementation. Followed by that, we have Module 21, that is Support Vector Machine. Here we will understand how support vector machine works and learn the fundamentals of support vector machines. Up next, Module 22, that is Bayes Theorem. Here we will grasp the concept of Bayes Theorem and its significance in data science. Then we have Module 23, that is What is Anova. We will study the analysis of variance, that is Anova method for statistical analysis. Proceeding ahead, we have Module 24, that is What is Correlation. Examine the concept of correlation and its importance in data science. Followed by that, we have Module 25, that is Types of Correlation. Here we will explore different types of correlations used in data analysis. Up next, we have Module 26, that is Correlation versus Regression. Here we will differentiate between correlation and regression in data analysis. Proceeding ahead, we had Module 27, that is Data Science Interview Questions. Prepare for interview with common data science interview questions. And this is the agenda, and hope I made myself clear with the agenda for today's session. And before we begin, if these are the types of videos you would like to watch, hit the subscribe button, like, and press the bell to never miss out on future content.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science, because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In our meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She's a curious soul who asks a lot of whys. one of the many traits of a good data scientist. Now, she gears up for data acquisition to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In her project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and dashboards. And then finally, she deploys and maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Well, that's how Emma completes the data science project. We have seen the daily routine of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques along with genomic data provides a deeper understanding of genetic issues in reaction to particular drugs and diseases. Logistic companies like DHL, FedEx have discovered the best routes to ship, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, machine learning engineer, deep learning engineer, data engineer, and of course, data scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data.
Technological advancement has offered us seamless connectivity, and the advent of smartphones and connected devices worldwide has elevated the gravitas at which the data is generated every minute. Zettabytes of data, endless data lakes and server farms, billion-dollar investments, stakeholders, CMOs, CTOs and CEOs. Everyone is dependent on one detailed report that data scientist delivers. A wise decision backed by data research and analysis can yield prospering results. Still on the contrary, one wrong marketing decision, one misinterpreted detail could be a good recipe for a catastrophic financial disaster for an organization. That's the pivotal role a data scientist plays in any organization. A data scientist's caliber to devise algorithms to crunch numbers and extract precious information is invaluable. This is one good reason why data science is reported as the top IT profession in the current IT industry and is projected to be on the top for a good time. Welcome to Simplilearn's YouTube channel. Today, we will explain why you should learn data science. Before we get started, take a moment to subscribe to us and hit the bell to get notified of our content. If you're watching this, I'm sure you are interested in data science, looking for a flexible and online training program that better suits you like a glove and helps you get ahead in your career. Well, your search ends here. Simplilearn is offering an online data science bootcamp with Caltech in collaboration with IBM. Here, you will be mentored by real-time industry professionals, aligning your learnings to the current industry standards to get a better chance of landing your dream job. The course covers the most sought-after technical skills like exploratory data analysis, descriptive statistics, inferential statistics, model building, and fine-tuning, supervised and unsupervised learning, ensemble learning, deep learning, data visualization, and the course will help you get hands-on with important tools like NumPy, Pandas, Python, R, and SciPy. What are you waiting for? Hurry up. For more details, check the link in the description box below. IT firms are venturing into data science, recognizing its potential to open the doors to a wide spectrum of opportunities. It enables enterprises to monitor and report performance metrics to facilitate heightened and reinforced decision-making. Organizations can now analyze trends to make critical decisions to engage clients better, enhance company performance, boost productivity, and increase profitability. The organizational importance of data science is increasing at a relentless pace. The global data science platforms market is poised to grow at a CAGR of 16.43%, more than any other industry. Converging to IT, data science facilitates it with its power to extract information from larger volumes of data. Information technology makes our life easier by gathering and processing more data quickly and efficiently to provide results in minutes and hours, unlike days and weeks. Statistics and science have become the answer to complex data. Data science enables tapping and analyzing massive amounts of untapped data from many sources to leverage productivity and profitability. This is one good reason why many tech aspirants find data science to be the most interesting job profile. Apart from the IT domain, data science has spread its roots into other fields. For instance, the healthcare sector is more inclined towards data science and artificial intelligence to diagnose and treat the most complicated syndromes and robots to perform the most tedious surgeries. Online stores and shopping websites depend solely on data science to manage the supply chain and enhance the user experience by recommending the right product. Data science plays a pivotal role in transportation and logistics. It provides customized recommendations to best suit customers' comfort and manages unexpected circumstances using predictive analytics. Geographical experts, weather reports, and many more employ data science to predict seismic events, reservoir behavior, climate interpretation, water buoys to enable navigation, and more. Construction companies are integrating their process with data science to enhance plotting, constructing, and automating tasks to build better, faster, and bigger projects in the most efficient way possible. In the ever-evolving field of data science, new advancements and discoveries in research accelerate rapidly. You always get to learn something new, making every day's work exciting. New data science skills can be acquired endlessly, giving you a competitive edge with knowledge and expertise. The salary of a data scientist in India ranges from 15 to 25 lakhs per annum. And in the United States of America, the salaries range from $150,000 to $250,000 per annum. Depicting the future of data science results in an unmatched potential to settle in a secure job role. As the field expands, more jobs should become available as more data scientists are needed for analysis. Individuals wishing to pursue a career in data science can look forward to a bright future with data science. Data science has a huge scope across all industries. The global market for data science is expected to grow all the way up to $230 billion by early 2026, opening the gates for about 11 million data scientist job roles. Another important aspect of the future of data science is artificial intelligence. AI will likely to be most powerful technology data scientists will have to deal with in the future. To put it another way, the future of data science will align itself to make it better in the long run. To become a data scientist, the professionals in the organizations need to have healthy data literacy, powerful programming skills, mathematics, statistics, logic building skills, strong foundations in data cleaning, and a comfortable understanding of data visualization and machine learning algorithms. Handling all these are nothing less than herding cats. One skill gap could be the final nail in the coffin. If you are an aspiring data scientist looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Just grab Simplilearn's postgraduate program in data science from Purdue University in collaboration with IBM. That should be your right choice. For more details, use the link.
Data scientist is one of the hottest, highest paid and most enthusiastic job roles in the current IT industry. Business organizations are actively hiring professionals who could collect data, analyze the market to help the companies diagnose and overcome economic barriers to lead the industry. Many MNCs, including the FANG companies, are actively upskilling their employees to bridge the gap in the world of fast-paced and intelligent technologies. According to the US Bureau of Labor Statistics, Now is the best time to start a career in data science, as the number of jobs requiring data science skills alone is expected to grow by 27.9% by 2026. The potential recruiters are actively looking for data scientists and are willing to compensate their employees with handsome salaries. According to the leading websites like Indeed, Glassdoor, Naukri and LinkedIn, the average salary of a data scientist is anywhere between 10 lakhs rupees to as high as 80 lakh rupees per annum in India, depending on your experience. In the United States of America, the salary of a data scientist ranges from $100,000 to $250,000 per annum on an average. Should you be interested in becoming a successful data scientist but don't know how? Don't you worry, as we have got you covered with our rigorous survey reports, which will help you to not only choose from the top 10 data scientist certifications, but will also help you develop and enhance your data science skills to give your career the boost it deserves. So without much further ado, let's get started with the top 10 best data scientist certifications in 2022. While we are at it, please feel free to get subscribed and hit the bell icon to keep yourself updated with the latest IT trends in the industry. At number 10, we have CAP, which is AKA Certified Analytics Professional. Will be a great addition to your resume, as the certification is valued by many data science and analytics driven organizations. If you're looking forward to becoming a data scientist, this certification is proof that you possess the critical and lucrative technical expertise, understand risk management, information security procedures, and possess relevant soft skills required by a data science and analytics professional. Aspiring data scientists with a bachelor's degree and 5 years of professional analytical experience or master's degree with 3 years of experience are eligible to face CAP certification exam. There are numerous benefits to the certification. Apart from getting exposure to new and updated technical skills, the certification also paves way for new opportunities, as the certification proves your credibility for the role. We have the Open Certified Data Scientist, aka OpenCDS, on number 9. OpenCDS is considered the broadest and encyclopedic certification for a data scientist. Organizations choose OpenCDS certified professionals to fill up the most critical job roles responsible for producing an effective analysis of data to improve the business. The certification is available in 3 different levels. Level 1, Certified Data Scientist. Level 2, Master Certified Data Scientist. Level 3, Distinguished Certified Data Scientist. However, there is a prerequisite for candidates where the applicants are expected to demonstrate skills and experience against a set of conformance requirements through written applications and peer interviews. Next on our list is an interesting one: Tableau Data Scientist and Desktop Specialist. Tableau is one of the leading business intelligence tools, leading in Gartner's quadrant. Tableau offers a wide range of courses, but this certification is absolutely for free. Another similar certification is based on data analytics for interested candidates. Pursuing this certification will help you with data science fundamentals and also enhance your data visualization skills. The course covered data prep with Tableau, visual analytics, data science with Tableau, and finally to put your learning to the test. The course also includes a data scientist skills assessment. The course requires the candidates to possess some fundamentals of data preparation and exploration, creating and sharing insights from data, and some hands-on experience with Tableau. Up ahead, we have SAS Academy for Data Science Certification in 7th position. Statistical Analytical System is a sophisticated tool purpose-built for carrying out advanced analytics and complex statistical operations. Getting certified as an SAS expert will help your resume to stand out. The course features hands-on experience with powerful tools like Learn using SAS, R, Python, Pig, Hive, and Hadoop. The global recognized tailor-made certification will help you prepare for all 3 exams, namely Data Curation Professional, Advanced Analytics Professional, AI and Machine Learning Professional as well. The course will enhance your learning with practical application based on actual C studies that will feature data curation, advanced analytics, AI, and machine learning your way at your own pace. We have Dell EMC Proven Professional Certification Program in the top 6th grade. The Dell EMC Proven Professional Certification Program is a tried and tested certification with affirmed results. Dell claims about 73% of individuals found the program to be effective in their career. 23% of candidates obtained a decent hike with promotion as well. About 86% of HRs admitted to selecting the candidates with this certification. With these groundbreaking numbers, this certification has nothing more to prove. The program is segmented into 2 categories: the associate level certification and specialist level certification. The main growth areas include advanced analytical methods, Hadoop and Big Hive HBase, social network analysis, natural language processing, and visualization methods. The development of these skills and the use of these methods allow the data scientists to identify and communicate conclusions and recommendations to solve business challenges across many domains. If you are interested in wondering about the prerequisites needed, that's good news for you. The program expects only fundamental programming and analytical skills and have a good understanding of cloud computing. On the top 5th position, we have TensorFlow Developer Certification. The main goal of this certification is to help aspiring data scientists get well versed with TensorFlow and showcase their expertise in machine learning. The TensorFlow Developer Certification can be considered as one of the best foundational certifications for demonstrating training and deployment of the machine learning models. The candidates appearing for the certification are expected to have a fundamental knowledge of image recognition, object detection, test recognition algorithms with deep neural networks, convolutional neural networks, and exploring strategies to prevent overfitting, including augmentation and dropouts. The best part of the certification is it does not have an expiration date. One amongst the top 5 is Simplilearn's postgraduate program in data science. Simplilearn collaborates with IBM and with the best and world-renowned Purdue University for providing postgraduate certification in data science. Simplilearn's data science certification is ranked as the number 1 by Economic Times. The course focuses on the comprehensiveness of content and skills required to tackle real-world business problems. The best part of the certification program is that it does not concentrate on one language like the others. Here you get into the master data science with both Python and R programming languages. The course then navigates you through advanced machine learning paradigms with real-time industry professionals and experienced faculty from Purdue University. By the end of the program, you will get hands-on experience with 3 capstone projects. And also, you will have lifetime access to 25 plus real-time business problems and their solutions for future reference. The projects are related to top organizations like Amazon, Uber, Walmart, Comcast, to name a few. The IBM Data Science Professional Certificate stands at the 3rd position of top data science certifications. You will learn to import and clean data sets, analyze and visualize data, and build and evaluate machine learning models and pipelines using Python. You will apply various data science skills, techniques, and tools to complete a project and publish a real-time report by the end of the course. The course revolves around Python, so it happens to be one of the major prerequisites, and along with that comes SQL and Jupyter Notebook. IBM claims that the course gives people the foundational blocks to learn and master data sources. We are now at the top 2nd certification, the Google Certified Professional Data Engineer. You might be wondering, why are we discussing data engineering? It is a fact that to become a successful data scientist, you need to possess a good grip over the data that you're working with. Data Engineer certification will give you an edge over the other candidates, proving your caliber while handling data. This certification will take you through various stages where you will learn to design and build data processing systems, operationalize machine learning models, and deliver the best solution. Having a comfortable understanding of Google Cloud would be necessary. A good 1 year of experience with data management and analytics could add to taking up the certification. On the number 1 position, we have Google Data Machine Learning Engineer. Most of the time, data scientists are comfortable working with Jupyter Notebook. This could be feasible in normal conditions. But if you wish to send your model production on the website or mobile devices, things can escalate real quick. Unexpected issues might pop up from nowhere and hinder the production environment. Although it is obvious and many educational programs teach this concept, it is preferred to learn it from the experts. In Google's Data Machine Learning Engineer program, you will get hands-on experience in various domains. A few important ones like framing and developing machine learning problems, automation and orchestrating machine learning pipelines, monitoring, optimizing and maintaining machine learning solutions. The best part of the certification program is you do not need to have any concrete prerequisite to take up this certification program. With that, we have come to the end of this session on the top 10 data scientist certifications for 2022. We hope the session was informative and interesting. Should you have any queries, please let us know in the comment section below.
Google had gathered 5 exabytes of data between the beginning of time 2003. This amount of data started to be produced every 2 days in 2010 and every 40 minutes by 2021. The responsibility of a data scientist is to gather, clean and present data and have a keen business sense and analytical abilities. Let us have a discussion about it in the upcoming slides. How can you become a data scientist as a beginner? I guarantee you, after watching this video, you will have a clear understanding on how to drive your career as a data scientist. Hey guys, welcome to Simplilearn. Before proceeding, please make sure you subscribe to Simplilearn's YouTube channel and press the bell icon to never miss any updates. Today we are going to cover significance of data scientists in industries. After that, prerequisites and technologies required for a data scientist. And finally, salary of a data scientist. I have a query for you. Which technology is used by Google Maps to predict traffic jams? Deep learning, machine learning, natural language processing, data structure. Please leave the answer in the comment section below. And stay tuned to get the answer. Significance. Now we will see how top industries are involved in the field of data science. By 2025, the data science industry is anticipated to grow to a value of $16 billion. There is an abundance of data science jobs all over the world. Now let's list out crucial areas where data science is used. Media and entertainment. The major player in the media and entertainment sector such as YouTube, Netflix, Hotstar, etc. have begun to use data science to better understand their audience and provide them with recommendations that are both relevant and personalized. E-commerce. Data science has aided retail companies in better meeting their expectations. As they bring a unique combination of deep data knowledge, technology skills, and statistical experience, data scientists are in high demand in the retail industry. Top recruiters are Amazon, Flipkart, Walmart, Myntra, etc. Digital marketing. Large volumes of data are currently being fetched from its users through search pages, social networks, online traffic display networks, movies, web pages, etc. A high level of business intelligence is needed to analyze such large amount of data, and this can only be done with the proper use of data science approaches. Top recruiters are Amazon, Flipkart, Facebook, Google, etc. Cybersecurity. Data science and AI are now being used by the cybersecurity industry to prevent the growing usage of algorithms for harmful purposes. Top recruiters includes IBM, Microsoft, Accenture, Cisco and many more. Before moving forward, what is the response to the Google Map question that I asked? Answer is machine learning. Coming to prerequisites. Now that we know significance of data science in industries, let us explore the prerequisites and technologies required for a data scientist. Seeing the demand of data scientists in every industry, it is obvious that the scope of a data scientist is very high. So, how to start? There is no necessity that you should be knowing any technology or programming language. You can be a layman too.
Data scientists typically have a variety of educational and professional experiences. Most should be proficient in 4 crucial areas. Important skill is mathematical expertise. 3 concepts like linear algebra, multivariable calculus, and optimization technique are crucial because they aid in our understanding of numerous machine learning algorithms that are crucial to data science. Similar to that, knowing statistics is crucial because they are used in data analysis. Additionally, important to statistics, probability is regarded as a must for mastering machine learning. Next is computer science. In the field of computer science, there is a lot to learn. But one of the key inquiries that arises in relation to programming is R or Python language. There are many factors to consider when deciding which language to choose for data science because both have a comprehensive collection of libraries to implement complex machine learning algorithms. In addition to learning a programming language, you should learn the following computer science skill: fundamentals of algorithm and data structures, distributed computing, machine learning, deep learning, Linux, SQL, MongoDB, etc. Domain expertise. Most individuals wrongly believe that domain expertise is not crucial to data science, yet it is. Consider the following scenario. If you are interested in working as a data scientist in the banking industries and you already know a lot about it. For instance, you are knowledgeable about stock trading, finance, etc. This will be very advantageous for you, and the bank itself will favor you over other applicants. And finally, communication skill. It covers both spoken and written communication. In a data science project, the project must be explained to others when findings from the analysis have been reached. This can occasionally be a report that you provide to your team or employer at work. Sometimes it might be a blog entry. It is frequently a presentation to a group of co-workers. Regardless, a data science project always involves some form of communication of the project's findings. Therefore, having a good communication skill is a requirement for being a data scientist. Apart from all this, practicing is very important. Keep using different tools. Also start reading blogs on data science. Start building projects on data science which can be added to your resume. Also, you can find many interesting courses on data science by Simplilearn. Salary reward is the result of good work. Now we shall discuss salaries that a data scientist will get. It should come as no surprise that data scientists may add significantly to a business. Every step of the process, from data processing to data cleansing, requires persistence, a lot of arithmetic and statistics, as well as scattering of engineering skills. One of the most important factors in a data scientist's salary is experience. At the beginner level, a data scientist can make $95,000 annually. The typical annual compensation for a mid-level data scientist is between $130,000 and $195,000. A seasoned data scientist typically earns between $165,000 and $250,000 per year. In India, at the beginner level, a data scientist can make 9,40,000 rupees on average per year. At mid-level, data scientists will get 20 lakhs rupees per annum. And if you are at the advanced level, you will get paid an average of rupees 25 lakhs annually. This salary will vary in different countries. The top hiring businesses in the US that provide the highest salaries for data scientists are Apple with $180,000 per annum. Next is Twitter with $170 per annum. Meta Technology $170 annually. LinkedIn $160,000 per annum. Wipro Technology provides 17,50,000 per annum. IBM provides 14 lakhs per annum. And Accenture will provide you with 19 lakhs per annum. And finally, American Express will provide on average of 13 lakhs per annum.
Data Science, my name is Mohan, and today we are going to take a look at what this buzz is all about. So now let's talk about the life cycle of a data science project. Okay, the first step is the concept study. In this step, it involves understanding the business problem, asking questions, get a good understanding of the business model, meet up with all the stakeholders, understand what kind of data is available, and all that is a part of the first step. So here are a few examples. We want to see what are the various specifications and then what is the end goal, what is the budget, is there an example of this kind of a problem that has been maybe solved earlier. So all this is a part of the concept study. And another example could be a very specific one to predict the price of a 1.35 carat diamond, and there may be relevant information inputs that are available, and we want to predict the price. The next step in this process is data preparation, data gathering and data preparation, also known as data munging, or sometimes it is also known as data manipulation. So what happens here is the raw data that is available may not be usable in its current format for various reasons. So that is why in this step, a data scientist would explore the data. He will take a look at some sample data, maybe pick, if there are millions of records, pick a few thousand records and see how the data is looking. Are there any gaps? Is the structure appropriate to be fed into the system? Are there some columns which are probably not adding value, may not be required for the analysis? Very often these are like names of the customers. They will probably not add any value or much value from an analysis perspective. The structure of the data, maybe the data is coming from multiple data sources and the structures may not be matching. What are the other problems? There may be gaps in the data. So the data, all the columns, all the cells are not filled. If you're talking about structured data, there are several blank records or blank columns. So if you use that data directly, you'll get errors or you'll get inaccurate results. So how do you either get rid of that data or how do you fill these gaps with something meaningful? So all that is a part of data munging or data manipulation. So these are some additional subtopics within that. So data integration is one of them. If there are any conflicts in the data, data may be redundant. Yeah, data redundancy is another issue. There may be, you have, let's say, data coming from two different systems and both of them have customer table, for example, or customer information. So when you merge them, there is a duplication issue. So how do we resolve that? So that is one. Data transformation. As I said, there will be situations where data is coming from multiple sources and then when we merge them together, they may not be matching. So we need to do some transformations to make sure everything is similar. We may have to do some data reduction. If the data size is too big, you may have to come up with ways to reduce it meaningfully without losing information. Then data cleaning. So there will be either wrong values or null values or there are missing values. So how do you handle all of that? A few examples of very specific stuff. So if there are missing values, how do you handle missing values or null values? Here in this particular slide, we are seeing three types of issues. One is missing value. Then you have null value. You see the difference between the two, right? So in the missing value, there is nothing, blank. Null value, it says null. Now the system cannot handle if there are null values. Similarly, there is improper data. So it's supposed to be numeric value, but there is a string or a non-numeric value. So how do we clean and prepare the data so that our system can work flawlessly? So there are multiple ways and there is no one common way of doing this. It can vary from project to project. It can vary from what exactly is the problem we are trying to solve. It can vary from data scientist to data scientist, organization to organization. So these are like some standard practices people come up with. And of course, there will be a lot of trial and error. Somebody would have tried out something and it worked and will continue to use that mechanism. So that's how we need to take care of data cleaning. Now, what are the various ways of doing, if values are missing? How do you take care of that? Now, if the data is too large and only a few records have some missing values, then it is okay to just get rid of those entire rows, for example. So if you have 1 million records and out of which 100 records don't have full data, so there are some missing values in about 100 records. So it's absolutely fine because it's a small percentage of the data. So you can get rid of the entire records which have missing values. But that's not a very common situation. Very often you will have multiple or at least a large number of a data set. For example, out of 1 million records, you may have 50,000 records which are like having missing values. Now, that's a significant amount. You cannot get rid of all those records. Your analysis will be inaccurate. So how do you handle such situations? So there are again multiple ways of doing it. One is you can probably, if a particular values are missing in a particular column, you can probably take the mean value for that particular column and fill all the missing values with the mean value, so that first of all you don't get errors because of missing values, and second, you don't get results that are way off because these values are completely different from what is there. So that is one way. Then a few other could be either taking the median value or depending on what kind of data we are talking about. So something meaningful we will have put in there. If we are doing some machine learning activity, then obviously as a part of data preparation, you need to split the data into training and test data set. The reason being, if you try to test with a data set which the system has already seen as a part of training, then it will tend to give reasonably accurate results because it has already seen that data, and that is not a good measure of the accuracy of the system. So typically you take the entire data set, the input data set, and split it into two parts. And again, the ratio can vary from person to person, individual preferences. Some people like to split it into 50-50. Some people like it as 63.33 and 33.3 is basically 2/3 and 1/3. And some people do it as 80-20. 80 for training and 20 for testing. So you split the data, perform the training with the 80%, and then use the remaining 20% for testing. All right. So that is one more data preparation activity that needs to be done before you start analyzing or applying the data or putting the data through the model. Then the next step is model planning. Now these models can be statistical models, this could be machine learning models. So you need to decide what kind of models you're going to use. Again, it depends on what is the problem you're trying to solve. If it is a regression problem, you need to think of a regression algorithm and come up with a regression model. So it could be linear regression. Or if you're talking about classification, then you need to pick up an appropriate classification algorithm like logistic regression or decision tree or SVM, and then you need to train that particular model. So that is the model building or model planning process, and the cleaned up data has to be fed into the model. And apart from cleaning, you may also have to, in order to determine what kind of model you will use, you have to perform some exploratory data analysis to understand the relationship between the various variables and see if the data is appropriate and so on, right? So that is the additional preparatory step that needs to be done. So a little bit of details about exploratory data analysis. So what exactly is exploratory data analysis? It's basically to, as the name suggests, you're just exploring. You just receive the data and you're trying to explore and find out what are the data types and what is the data clean in each of the columns. What is the maximum minimum value? So for example, there are out of the box functionality available in tools like R. So if you just ask for a summary of the table, it will tell you for each column, it will give some details as to what is the mean value, what is the maximum value, and so on and so forth. So this exercise or this exploratory analysis is to get an understanding of your data. And then you can take steps to, during this process, you find there are a lot of missing values. You need to take steps to fix those. You will also get an idea about what kind of model to be used and so on and so forth. What are the various techniques used for exploratory data analysis? Typically, these would be visualization techniques, like you use histograms, you can use box plots, you can use scatter plots. So these are very quick ways of identifying the patterns or a few of the trends of the data and so on. And then once your data is ready, you've decided on the model, what kind of algorithm you're going to use. If you're trying to do machine learning, you need to pass your 80% the training data, or rather you use that training data to train your model. And the training process itself is iterative. So the training process you may have to perform multiple times. And once the training is done and you feel it is giving good accuracy, then you move on to test. So you take the remaining 20% of the data. Remember, we split the data into training and test. So the test data is now used to check the accuracy or how well our model is performing. And if there are further issues, let's say, and model is still during testing, if the accuracy is not good, then you may want to retrain your model or use a different model. So this whole thing again can be iterative. But if the test process is passed, or if the model passes the test, then it can go into production and it will be deployed. All right. So what are the various tools that we use for model planning? R is an excellent tool in a lot of ways, whether you're doing regular statistical analysis or machine learning or any of these activities. R, along with R Studio, provides a very powerful environment to do data analysis, including visualization. It has a very good integrated visualization or plot mechanism which can be used for doing exploratory data analysis, and then later on to do analysis, detailed analysis, and machine learning, and so on and so forth. Then of course you can write Python programs. Python offers a rich library for performing data analysis and machine learning and so on. MATLAB is a very popular tool as well, especially during education. So this is a very easy to learn tool. So MATLAB is another tool that can be used. And then last but not least, SAS. SAS is again very powerful. It is a proprietary tool and it has all the components that are required to perform very good statistical analysis or perform data science. So those are the various tools that would be required for, or that can be used for model building. And so the next step is model building. So we have done the planning part. We said, okay, what is the algorithm we are going to use? What kind of model we are going to use? Now we need to actually train this model, or build the model rather, so that it can then be deployed. So what are the various ways, or what are the various types of model building activities? So it could be, let's say in this particular example that we have taken, you want to find out the price of 1.35 carat diamond. So this is, let's say, a linear regression problem. You have data for various carats of diamond, and you use that information, you pass it through a linear regression model, or you create a linear regression model which can then predict your price for 1.35 carat. So this is one example of model building. And then a little bit details of how linear regression works. So linear regression is basically coming up with a relation between an independent variable and a dependent variable. So it is pretty much like coming up with equation of a straight line which is the best fit for the given data. So like for example here, y is equal to mx plus c. So y is the dependent variable and x is the independent variable. We need to determine the values of m and c for our given data. So that is what the training process of this model does. At the end of the training process, you have a certain value of m and c, and that is used for predicting the values of any new data that comes. All right, so the way it works is we use the training and the test data set to train the model and then validate whether the model is working fine or not using test data. And if it is working fine, then it is taken to the next level, which is put in production. If not, the model has to be retrained. If the accuracy is not good enough, then the model is retrained, maybe with more data, or you come up with a newer model or algorithm and then repeat that process. So it is an iterative process. Once the training is completed, training and test, then this model is deployed, and we can use this particular model to determine what is the price of 1.35 carat diamond. Remember, that was our problem statement. So now that we have the best fit for this given data, we have the price of 1.35 carat diamond, which is 10,000. So this is one example of how this whole process works. Now, how do we build the model? There are multiple ways. You can use Python, for example, and use libraries like Pandas or NumPy to build the model and implement it. This will be available as a separate tutorial, a separate video in this playlist. So stay tuned for that. Moving on, once we have the results, the next step is to communicate these results to the appropriate stakeholders. So, which is basically taking this results and preparing like a presentation or a dashboard and communicating these results to the concerned people. So finishing or getting the results of the analysis is not the last step, but you need to, as a data scientist, take these results and present it to the team that has given you this problem in the first place and explain your findings, explain the findings of this exercise and recommend maybe what steps they need to take in order to overcome this problem or solve this problem. So that is the pretty much once that is accepted, and the last step is to operationalize. So if everything is fine, your data scientist presentations are accepted, then they put it into practice and thereby they will be able to improve or solve the problem that they stated in step 1. Okay, so quick summary of the life cycle. You have a concept study, which is basically understanding the problem, asking the right questions, and trying to see if there is enough data to solve this problem. And then even maybe gather the data. Then data preparation, the raw data needs to be manipulated. You need to do data munging so that you have the data in a certain proper format to be used by the model or our analytics system. And then you need to do the model planning, what kind of a model, what algorithm you will use for a given problem. And then the model building. So the exact execution of that model happens in step 4, and you implement and execute that model and put the data through the analysis in this step, and then you get the results. These results are then communicated, packaged and presented and communicated to the stakeholders, and once that is accepted, that is operationalized. So that is the final step.
Hey everyone, welcome to Simplilearn. Today's video will compare and contrast artificial intelligence, deep learning, machine learning, and data science. But before we get started, consider subscribing to Simplilearn's YouTube channel and hit the bell icon. That way, you'll be the first to get notified when we post similar content. Before moving on, let me ask you 2 interesting queries. Which among the following is not a branch of artificial intelligence? Data analysis, machine learning, deep learning, neural networks. And the second query is, what is the main difference between machine learning and deep learning? Please leave your answer in the comments section below, and stay tuned to get the answer. First, we will unwrap deep learning. Deep learning was first introduced in the 1940s. Deep learning did not develop suddenly, it developed slowly and steadily over 7 decades. Many theses and discoveries were made on deep learning from the 1940s to 2000. Thanks to companies like Facebook and Google, the term deep learning has gained popularity and may give the perception that it is a relatively new concept. Deep learning can be considered as a type of machine learning and artificial intelligence, or AI, that imitates how humans gain certain types of knowledge. Deep learning includes statistics and predictive modeling. Deep learning makes processes quicker and simpler, which is advantageous to data scientists to gather, analyze, and interpret massive amounts of data. Having the fundamentals discussed, let's move into the different types of deep learning. Neural networks are the main component of deep learning, but neural networks comprise 3 main types, which contain artificial neural networks, or ANN, convolution neural networks, or CNN, and recurrent neural networks, or RNN. Artificial neural networks are inspired biologically by the animal brain. Convolutional neural networks surpass other neural networks when given inputs such as images, voice, or audio. It analyzes images by processing data. Recurrent neural networks uses sequential data or series of data. Convolutional neural networks and recurrent neural networks are used in natural language processes, speech recognition, image recognition, and many more. Machine learning. The evolution of ML started with the mathematical modeling of neural networks that served as the basis for the invention of machine learning. In 1943, neuroscientist Warren McCulloch and logician Walter Pitts attempted to quantitatively map out how humans make decisions and carry out thinking processes. Therefore, the term machine learning is not new. Machine learning is a branch of artificial intelligence and computer science that uses data and algorithms to imitate how humans learn, gradually increasing the system's accuracy. There are three types of machine learning, which include supervised learning. What is supervised learning? Well, here, machines are trained using labeled data. Machines predict output based on this data. Now, coming to unsupervised learning, models are not supervised using a training data set. It is comparable to the learning process that occurs in the human brain while learning something new. And the third type of machine learning is reinforcement learning. Here, the agent learns from feedback. It learns to behave in a given environment based on actions and the result of the action. And this feature can be observed in robotics. Now, coming to the evolution of AI. The potential of artificial intelligence wasn't explored until the 1950s, although the idea has been known for centuries. The term artificial intelligence has been around for a decade. Still, it wasn't until British polymath Alan Turing posed the question of why machines couldn't use knowledge like humans do to solve problems and make decisions. We can define artificial intelligence as a technique of turning a computer-based robot to work and act like humans. Now let's have a glance at the types of artificial intelligence. Weak AI performs only specific tasks, like Apple's Siri, Google Assistant, and Amazon's Alexa. You might have used all of these technologies, but the types I am mentioning after this are under experiment. General AI can also be addressed as artificial general intelligence. It is equivalent to human intelligence, hence, an AGI system is capable of carrying out any task that a human can. Strong AI aspires to build machines that are indistinguishable from the human mind. Both general and strong AI are hypothetical right now. Rigorous research is going on this matter. There are many branches of artificial intelligence, which include machine learning, deep learning, natural language processing, robotics, expert systems, fuzzy logic. Therefore, the correct answer for which is not a branch of artificial intelligence is option A, data analysis. Now that we have covered deep learning, machine learning, and artificial intelligence, the final topic is data science. Concepts like deep learning, machine learning, and artificial intelligence can be considered a subset of data science. Let us cover the evolution of data science. The phrase data science was coined in the early 1960s to characterize a new profession that would enable the comprehension and analysis of the massive volumes of data being gathered at the time. Since its beginnings, data science has expanded to incorporate ideas and methods from other fields, including artificial intelligence, machine learning, deep learning, and so forth. Data science can be defined as the domain of study that handles vast volumes of data using modern tools and techniques to find unseen patterns, derive meaningful information, and make business decisions. Therefore, data science comprises machine learning, artificial intelligence, and deep learning.
No matter if you are recently graduated, have experience in the IT field, or are seeking a career change, these courses in data science will provide you with the necessary foundation to pursue a successful career in data science. Obtaining an education in data science can open doors to various job opportunities such as data analyst, data engineer, data architect, or data scientist. Your specific path in data science will depend on your skills and interests. However, all these career paths require a certain level of proficiency in programming, data visualization, statistics, and machine learning. Data engineers and data architects primarily work with coding, databases, and intricate queries, while data analysts and data scientists focus on analyzing, collecting, and interpreting large data sets to aid in making informed business decisions. It is a rapidly expanding and financially rewarding career path, with data scientists reporting an average annual salary of $130,000 in the United States, and in India it is 12 lakhs per annum. In this Simplilearn video on top courses for data science, we will explore some of the top courses in data science, including Wharton, Purdue, IIT Kanpur, Caltech, and SPJMIR. These courses are at the forefront of data science education and research. Their programs are designed to equip students with the skills and knowledge needed to succeed in this exciting and rapidly evolving field. But before moving ahead, do subscribe to our YouTube channel and hit the bell icon to get all the updates from Simplilearn. So let's get started. First one on the list is Caltech. The California Institute of Technology, known as Caltech, is a private research university in Pasadena, California. The university's Division of Engineering and Applied Sciences offer data science courses. This data science course curriculum emphasizes hands-on learning and encourages students to work on projects that have real-world applications. That's why Simplilearn has collaborated with Caltech to create a data science course that leverages the superiority of Caltech's academic eminence. This data science course covers critical data science topics like Python programming, R programming, machine learning, deep learning, and data visualization tools through an interactive learning model with live sessions by global practitioners and practical labs. This course also provides a program certificate with up to 14 CEU credits from Caltech CTME and a course completion certificate from Caltech CTME. You will also earn membership to the Caltech CTME Circle and an online convocation by the Caltech Program Director. And last but not least, hands-on experience with tools like NumPy, Pandas, R, Python, and SciPy with 25 plus industry-relevant projects from the likes of Walmart, Amazon, Uber, Mercedes-Benz, and many more. Interested in this course? Then do check out the link to this course in the description. The second one on the list is Purdue University. Purdue is a public research university located in West Lafayette, Indiana. The university's Department of Computer Science offers a data science program covering data mining, machine learning, and statistical modeling. Well, with Simplilearn's postgraduate program in data science, in partnership with Purdue University and in collaboration with IBM, you can have the opportunity to take the advantage of master classes by Purdue faculty and IBM experts, exclusive hackathons, and Ask Me Anything sessions by IBM. This program in data science is perfect for working professionals and it focuses on essential job skills like R and Python programming, machine learning, NLP, and data visualization with Tableau. To prepare for the job market, you will learn all this through live sessions with experts, hands-on labs, IBM hackathons, and corporate projects. This course will also provide you with the data science certificate from Purdue, the 8th most innovative university in the US, along with IBM certificates from IBM courses. With this, you will also get a chance to build your resume and prepare your interviews with valuable insights from industry experts and 25 plus industry relevant projects from Amazon, Walmart, Uber, and Mercedes-Benz. You can find the link to this course in the description box. And the third one, Wharton. Wharton is a global technology company that has been a leader in the data science field for decades. In addition to offering a range of data science solutions and tools, Wharton also provides training and education in data science. This AI program, in collaboration with Wharton, impacts in-depth knowledge of big data, AI, and machine learning, and how to apply them across the three key business functions: marketing, finance, and people management. This program also covers the risks and ethics of using AI and how you can design governance frameworks for effective AI implementation. Apart from this, you will gain a certificate from Wharton Online, the Wharton School's digital learning platform, and you will learn how AI can be applied across business functions such as marketing, finance, HR, and you will also be having live master classes from top Wharton faculty and get insights on how AI is utilized across companies like McDonald's, Visa, and Citigroup. This program is designed to equip students with the skills and knowledge needed to succeed in this fast-growing field and become a data scientist by diving deep into the nuances of data interpretation, mastering technologies like machine learning, and mastering powerful programming skills to take your career in data science to the next level. Also, the link for this course is mentioned in the description box. Following that, we have IIT Kanpur. The Indian Institute of Technology Kanpur is one of the top engineering schools in India, known for its strong focus on research and innovation. The institute's Department of Computer Science and Engineering is one of the most popular universities offering data science courses. Taking advantage of such resourceful alumni, Simplilearn provides a professional certificate course in data science in collaboration with IIT Kanpur, mastering essential data science skills through applied learning with live classes by industry experts, asynchronous videos, hands-on labs, and master classes from distinguished IIT Kanpur faculty. Along with that, you will get hands-on experience on 25 plus industry-relevant projects from the likes of Walmart, Amazon, Uber, Mercedes-Benz, and many more, along with career mentorship and profile building sessions with valuable insights from industry experts. This course is designed with a carefully curated curriculum that includes critical topics like Python, machine learning, NLP, and data visualization, delivered using hands-on labs and industry-relevant projects to help you advance your career trajectory. This data science course in India aims to demystify data science. The link is mentioned in the description box. And the last one is SPJMIR. SP Jain Institute of Management and Research is a leading business school located in Mumbai, India. The institute's Business Intelligence and Analytics program is designed to provide students with a strong foundation in data science, analytics, and business intelligence. Therefore, Simplilearn has collaborated with SPJMIR to design the Data Science for Business Decisions program that will will help you learn this in-demand skill set and turn yourself into a data-driven decision maker to optimize your organization's performance. This program enables you to master the concepts of machine learning, statistics, data visualization, etc. and create a strategy to implement a data science project in your organization. This program will help you drive digital transformation in your organization by understanding data privacy, data architecture, and governance. You will also earn a program completion certification from SPJMIR, a leading school of management in India, and master the concepts of data science through live sessions delivered by SPJMIR faculty. You will also bag an opportunity to avail of SPJMIR Executive Alumni Network membership post-program completion, hands-on experience on multiple projects, and a capstone pertaining to various industry domains. The link is mentioned below in the description. And if you are one of the aspiring data scientists looking for online training and graduating from the best universities, or a professional who highly sets to switch careers with data scientist by learning from the experts, then try giving a shot to Simplilearn's Caltech postgraduate program in data science in collaboration with IBM. The course link is mentioned in the description box below, and you will navigate to the course page where you can find a complete overview of the program being offered.
Let's begin this lesson by defining the term statistics. Statistics is a mathematical science pertaining to the collection, presentation, analysis, and interpretation of data. It's widely used to understand the complex problems of the real world and simplify them to make well-informed decisions. Several statistical principles, functions, and algorithms can be used to analyze primary data, build a statistical model, and predict the outcomes. An analysis of any situation can be done in two ways: statistical analysis or a non-statistical analysis. Statistical analysis is the science of collecting, exploring, and presenting large amounts of data to identify the patterns and trends. Statistical analysis is also called quantitative analysis. Non-statistical analysis provides generic information and includes text, sound, still images, and moving images. Non-statistical analysis is also called qualitative analysis. Although both forms of analysis provide results, statistical analysis gives more insight and a clearer picture, a feature that makes it vital for businesses. There are two major categories of statistics: descriptive statistics and inferential statistics. Descriptive statistics helps organize data and focuses on the main characteristics of the data. It provides a summary of the data numerically or graphically. Numerical measures such as average, mode, standard deviation or SD, and correlation are used to describe the features of a dataset. Suppose you want to study the height of students in a classroom. In the descriptive statistics, you would record the height of every person in the classroom and then find out the maximum height, minimum height, and average height of the population. Inferential statistics generalizes the larger dataset and applies probability theory to draw a conclusion. It allows you to infer population parameters based on the sample statistics and to model relationships within the data. Modeling allows you to develop mathematical equations which describe the interrelationships between two or more variables. Consider the same example of calculating the height of students in the classroom. In inferential statistics, you would categorize height as tall, medium, and small, and then take only a small sample from the population to study the height of students in the classroom. The field of statistics touches our lives in many ways, from the daily routines in our homes to the business of making the greatest cities run. The effect of statistics are everywhere. There are various statistical terms that one should be aware of while dealing with statistics: population, sample, variable, quantitative variable, qualitative variable, discrete variable, continuous variable. A population is the group from which data is to be collected. A sample is a subset of a population. A variable is a feature that is characteristic of any member of the population differing in quality or quantity from another member. A variable differing in quantity is called a quantitative variable. For example, the weight of a person, number of people in a car. A variable differing in quality is called a qualitative variable or attribute. For example, color, the degree of damage of a car in an accident. A discrete variable is one which no value can be assumed between the two given values. For example, the number of children in a family. A continuous variable is one in which any value can be assumed between the two given values. For example, the time taken for a 100-meter run. Typically, there are 4 types of statistical measures used to describe the data. They are measures of frequency, measures of central tendency, measures of spread, measures of position. Let's learn each in detail. Frequency of the data indicates the number of times a particular data value occurs in the given dataset. The measures of frequency are number and percentage. Central tendency indicates whether the data values tend to accumulate in the middle of the distribution or toward the end. The measures of central tendency are mean, median, and mode. Spread describes how similar or varied the set of observed values are for a particular variable. The measures of spread are standard deviation, variance, and quartiles. The measure of spread are also called measures of dispersion. Position identifies the exact location of a particular data value in the given data set. The measures of position are percentiles, quartiles, and standard scores. Statistical Analysis System, or SAS, provides a list of procedures to perform descriptive statistics. They are as follows: proc print, proc contents, proc means, proc frequency, proc univariate, proc g-chart, proc boxplot, proc gplot. Proc print. It prints all the variables in a SAS dataset. Proc contents. It describes the structure of a dataset. Proc means. It provides data summarization tools to compute descriptive statistics for variables across all observations and within the groups of observations. Proc frequency. It produces one-way to n-way frequency and cross-tabulation tables. Frequencies can also be an output of a SAS dataset. Proc univariate. It goes beyond what proc means does and is useful in conducting some basic statistical analyses and includes high-resolution graphical features. Proc g-chart. The g-chart procedure produces 6 types of charts: block charts, horizontal, vertical bar charts, pie, donut charts, and star charts. These charts graphically represent the value of a statistic calculated for one or more variables in an input SAS dataset. The charted variables can be either numeric or character. Proc boxplot. The boxplot procedure creates side-by-side box and whisker plots of measurements organized in groups. A box and whisker plot displays the mean, quartiles, and minimum and maximum observations for a group. Proc gplot. Gplot procedure creates 2-dimensional graphs, including simple scatter plots, overlay plots in which multiple sets of data points are displayed on one set of axes, plots against a second vertical axis, bubble plots, and logarithmic plots. In this demo, you'll learn how to use descriptive statistics to analyze the mean from the electronic dataset. Let's import the electronic dataset into the SAS console. In the left plane, right-click the electronic.xlsx dataset and click Import Data. The code to import the data generates automatically. Copy the code and paste it in the new window. The proc means procedure is used to analyze the mean of the imported dataset. The keyword data identifies the input dataset. In this demo, the input dataset is electronic. The output obtained is shown on the screen. Note that the number of observations, mean, standard deviation, and maximum and minimum values of the electronic dataset are obtained. This concludes the demo on how to use descriptive statistics to analyze the mean from the electronic dataset. So far, you have learned about descriptive statistics. Let's now learn about inferential statistics. Hypothesis testing is an inferential statistical technique to determine whether there is enough evidence in a data sample to infer that a certain condition holds true for the entire population. To understand the characteristics of the general population, we take a random sample and analyze the properties of the sample. We then test whether or not the identified conclusions correctly represent the population as a whole. The population of hypothesis testing is to choose between two competing hypotheses about the value of a population parameter. For example, one hypothesis might claim that the wages of men and women are equal, while the other might claim that women make more than men. Hypothesis testing is formulated in terms of two hypotheses: null hypothesis, which is referred to as H-null; alternative hypothesis, which is referred to as H1. The null hypothesis is assumed to be true unless there is strong evidence to the contrary. The alternative hypothesis is assumed to be true when the null hypothesis is proven false. Let's understand the null hypothesis and alternative hypothesis using a general example. Null hypothesis attempts to show that no variation exists between variables, and alternative hypothesis is any hypothesis other than the null. For example, say a pharmaceutical company has introduced a medicine in the market for a particular disease, and people have been using it for a considerable period of time, and it's generally considered safe. If the medicine is proved to be safe, then it is referred to as null hypothesis. To reject null hypothesis, we should prove that the medicine is unsafe. If the null hypothesis is rejected, then the alternative hypothesis is used. Before you perform any statistical tests with variables, it's significant to recognize the nature of the variables involved. Based on the nature of the variables, it's classified into four types. They are categorical or nominal variables, ordinal variables, interval variables, and ratio variables. Nominal variables are ones which have two or more categories, and it's impossible to order the values. Examples of nominal variables include gender and blood group. Ordinal variables have values ordered logically. However, the relative distance between two data values is not clear. Examples of ordinal variables include considering the size of a coffee cup, large, medium, and small, and considering the ratings of a product, bad, good, and best. Interval variables are similar to ordinal variables, except that the values are measured in a way where their differences are meaningful. With an interval scale, equal differences between scale values do have equal quantitative meaning. For this reason, an interval scale provides more quantitative information than the ordinal scale. The interval scale does not have a true zero point. A true zero point means that a value of 0 on the scale represents zero quantity of the construct being assessed. Examples of interval variables include the Fahrenheit scale used to measure temperature and distance between two compartments in a train. Ratio scales are similar to interval scales in that equal differences between scale values have equal quantitative meaning. However, ratio scales also have a true zero point, which give them an additional property. For example, the system of inches used with a common ruler is an example of a ratio scale. There is a true zero point because 0 inches does in fact indicate a complete absence of length. In this demo, you'll learn how to perform the hypothesis testing using SAS. In this example, let's check against the length of certain observations from a random sample. The keyword data identifies the input dataset. The input statement is used to declare the aging variable and cards to read data into SAS. Let's perform a t-test to check the null hypothesis. Let's assume that the null hypothesis to be that the mean days to deliver a product is 6 days. So null hypothesis equals 6. Alpha value is the probability of making an error, which is 5% standard, and hence alpha equals 0.05. The variable statement names the variable to be used in the analysis. The output is shown on the screen. Note that the p-value is greater than the alpha value, which is 0.05. Therefore, we fail to reject the null hypothesis. This concludes the demo on how to perform the hypothesis testing using SAS. Let's now learn about hypothesis testing procedures. There are two types of hypothesis testing procedures. They are parametric tests and non-parametric tests. In statistical inference or hypothesis testing, the traditional tests, such as t-test and ANOVA, are called parametric tests. They depend on the specification of a probability distribution except for a set of free parameters. In simple words, you can say that if the population information is known completely by its parameter, then it is called a parametric test. If the population or parameter information is not known, and you are still required to test the hypothesis of the population, then it's called a non-parametric test. Non-parametric tests do not require any strict distributional assumptions. There are various parametric tests. They are as follows: t-test, ANOVA, chi-squared, linear regression. Let's understand them in detail. T-test. A t-test determines if two sets of data are significantly different from each other. The t-test is used in the following situations: to test if the mean is significantly different than a hypothesized value, to test if the mean for two independent groups is significantly different, to test if the mean for two dependent or paired groups is significantly different. For example, let's say you have to find out which region spends the highest amount of money on shopping. It's impractical to ask everyone in the different regions about their shopping expenditure. In this case, you can calculate the highest shopping expenditure by collecting sample observations from each region. With the help of the t-test, you can check if the difference between the regions are significant or a statistical fluke. ANOVA. ANOVA is a generalized version of the t-test and used when the mean of the interval dependent variable is different to the categorical independent variable. When we want to check variance between two or more groups, we apply the ANOVA test. For example, let's look at the same example of the t-test example. Now you want to check how much people in various regions spend every month on shopping. In this case, there are four groups, namely East, West, North, and South. With the help of the ANOVA test, you can check if the difference between the regions is significant or a statistical fluke. Chi-square. Chi-square is a statistical test used to compare observed data with data you would expect to obtain according to a specific hypothesis. Let's understand the chi-square test through an example. You have a data set of male shoppers and female shoppers. Let's say you need to assess whether the probability of females purchasing items of $500 or more is significantly different from the probability of males purchasing items of $500 or more. Linear regression. There are two types of linear regression: simple linear regression and multiple linear regression. Simple linear regression is used when one wants to test how well a variable predicts another variable. Multiple linear regression allows one to test how well multiple variables, or independent variables, predict a variable of interest. When using multiple linear regression, we additionally assume the predictor variables are independent. For example, finding a relationship between any two variables, say sales and profit, is called simple linear regression. Finding a relationship between any three variables, say sales, cost, and telemarketing, is called multiple linear regression. Some of the non-parametric tests are Wilcoxon rank sum test and Kruskal-Wallis H-test. Wilcoxon rank sum test. The Wilcoxon signed rank test is a non-parametric statistical hypothesis test used to compare two related samples or matched samples to assess whether or not their population mean ranks differ. In Wilcoxon rank sum test, you can test the null hypothesis on the basis of the ranks of the observations. Kruskal-Wallis H-test. Kruskal-Wallis H-test is a rank-based non-parametric test used to compare independent samples of equal or different sample sizes. In this test, you can test the null hypothesis on the basis of the ranks of the independent samples. R is a programming language for statistical computing and graphics. It was developed at AT&T Bell Laboratories by Robert Gentleman and Ross Ihaka. It's a GNU project and is similar to the S language. It can be considered as another implementation of S. However, there are a few important differences, but much of the code written for S can be run unchanged in R. R offers various statistical and graphical techniques, which make it extensible. R is a free and open source language. The present R is the result of contributions and collaborations from highly active community members from all over the world. R is capable of compiling and running code on all platforms, such as Linux, Mac, and Windows. Due to its underlying philosophy and design, R is useful for statistical computation and graphic visualization. R is a lot more than just a programming language. It has a worldwide repository system called Comprehensive R Archive Network, or CRAN, which can be accessed through the given link. CRAN is a network of web servers and FTPs spread across the world. This network stores similar codes and updated documentation of R. As per the data of 2011, there were more than 3,000 packages hosted on CRAN, while there were many more on other websites as well. At present, the repository includes about 7,429 packages. Do you know there are some limitations of R too? One of the limitations is that it has a steep learning curve. It takes some time for a learner to understand the actual power of R. However, it's much better than other statistical languages. For a novice, it may be difficult to be understood, although there are a few easy-to-use GUIs available, but they do not offer the polish of the commercial offerings. Its documentation is sometimes very concise, which makes it less understandable for a non-statistician. However, a few high-standard books are trying to plug in the documentation gaps. In addition, R has memory or RAM limitations when working with large datasets. Its commands offer less attention to memory management, so they may consume all the available memory quickly. Therefore, when doing data mining, it can be a major restriction. As a solution, one may choose to use 64-bit operating systems over 32-bit ones. Here is a list of various reputed companies that use R for various purposes. Microsoft uses it in video gaming for purposes like Xbox matchmaking and scientific revenue. Using R, developers can perform functions like identifying trouble spots in game levels. The New York Times uses R for purposes like data visualization, data journalism, and interactive features like election forecast and dialect quiz. Bing uses this language for social search awareness. The New Scientist magazine is another company that uses R for data visualization, data journalism, and the analysis of news articles. Ford uses R for data-driven decision-making. Facebook also uses it for purposes like experimental analysis, exploratory data analysis, human resources, big data visualization, and the analysis of user behavior with respect to status updates and profile pictures. The famous recommendation engine of Foursquare is backed up by R. Uber uses R for the purpose of statistical analysis. In addition, Google uses it for economic forecasting, advertising effectiveness, and big data statistical modeling. Do you want to know more about R? One of the main advantages of R is that users can write their custom functions and own programs with ease. The syntaxes are so easy to learn that even users with no programming experience can use them. R can be used as a powerful environment to do complex analyses on almost each data type. Here are a few more pointers that will help you understand R. R statements or commands can be separated by a semicolon or a new line. The assignment operator used in R is as given, although the equal to operator also works. All characters after hash are treated as comments. In addition, there are no multi-line or block-level comments. The dollar operator is analogous to a dot operator in other languages. The use of the operator is shown on the screen. In this lesson, you'll learn about installing R on operating systems, including Windows, Mac OS X, and Linux. Let's first learn to install R on Windows from CRAN website. For this, you can download the package from the given website. As the first step, you would need to download the given Windows executable from this link. Once the package is downloaded, open the executable and follow the instructions. If you are installing R on a 64-bit Windows, the options will include 32 or 64-bit versions of R, and the default is to install both. You can choose to leave the settings as default and click Next to proceed. Once you install R successfully, you will see its icon on the desktop. You can start the R console like any other program. This demo will show the steps to install R on a Windows PC. In this demo, you'll learn how to install R on a Windows PC. Download the latest R package from the given URL. Double-click the executable file to begin the installation. The R installation wizard will open. Proceed with the installation by clicking the Next button. Select your preferred installation directory. Otherwise, leave the settings as default. Click the Finish button to finish the installation. If everything goes well, you will see the R icon on the desktop. RStudio is an IDE, or Integrated Development Environment for R. It's a project that provides most of the desired features for an IDE in an innovative way, which makes it easier and more productive to use R. It includes a console and tools for history, plotting, workspace, and debugging management. It also includes an editor that highlights the syntaxes, which supports execution of the code directly. Some other notable IDEs are listed in the table shown on the screen, along with the supported platforms. RStudio is available in various commercial and open source editions. It can be run on a desktop or through a web browser connected to RStudio Server or RStudio Server Pro. The desktop version is available for Windows, Mac OS X, and Linux platforms. To install RStudio on a Windows or Mac OS X system, you would need to simply download its self-installing binary. For this, you would need to go to the RStudio official website given on the screen and download the appropriate version for your system. Next, you would need to double-click the downloaded executable file and start the installation process. However, for Linux, the installation process varies. For Debian distribution, including Ubuntu, you can install the RStudio using its regular package management tools.
So let's talk about this amazing library, TensorFlow, which is also one of my favorites. So TensorFlow is a library for high-performance numerical computations with around 35,000 GitHub commits and a vibrant community of around 1,500 contributors. And it's used across various scientific domains. It's basically a framework where we can define and run computations which involves tensors. And tensors, we can say, are partially defined computational objects again, where they will eventually produce a value. That was about TensorFlow. Let's talk about the features of TensorFlow. So TensorFlow is majorly used in deep learning models and neural networks, where we have other libraries like Torch and Theorem also. But TensorFlow has hands down better computational graphical visualizations when compared to them. Also, TensorFlow reduces the error largely by 50 to 60% in neural machine translations. It's highly parallel in a way where it can train multiple neural networks and multiple GPUs for highly efficient and scalable models. This parallel computing feature of TensorFlow is also called pipelining. Also, TensorFlow has the advantage of seamless performance. As it's backed by Google, it has quicker updates, frequent new releases with the latest of features. Now, let's look at some applications. TensorFlow is extensively used in speech and image recognition, text-based applications, time series analysis and forecasting, and various other applications involving video detection. So, favorite thing about TensorFlow that it's already popular among the machine learning community and most are open to trying it. and some of us are already using it. Now, let's look at an example of a TensorFlow model. In this example, we will not dive deep into the explanation of the model as it is beyond the scope of this video. So here we're using Amnest dataset, which consists of images of handwritten digits. Handwritten digits can be easily recognized by building a simple TensorFlow model. Let's see how. When we visualize our data using Matplotlib library, the inputs will look something like this. Then we create our TensorFlow model. To create a basic TensorFlow model, we need to initialize the variables and start a session. Then after training the model, we can validate the data and then predict the accuracy. This model has predicted 92% accuracy. Let's see, which is pretty well for this model. So that's all for TensorFlow. If you need to understand this tutorial in detail, then you can go ahead and watch our deep learning tutorial from Simplilearn as shown in the right corner. Interesting, right? Let's move on to the next library. Now let's talk about a common yet a very powerful Python library called NumPy. NumPy is a fundamental package for numerical computation in Python. It stands for Numerical Python as the name suggests. It has around 18,000 commits on GitHub with an active community of 700 contributors. It's a general purpose array processing package in a way that it provides high performance multi-dimensional objects called arrays and tools for working with them. Also, NumPy addresses the slowness problem partly by providing these multi-dimensional arrays that we talked about, and then functions and operators that operate efficiently on these arrays. Interesting, right? Now let's talk about the features of NumPy. It's very easy to work with large arrays and matrices using NumPy. NumPy fully supports object-oriented approach. For example, coming back to NdArray once again, it's a class possessing numerous methods and attributes. NdArray provides for larger and repeated computations. NumPy offers vectorization. It's more faster and compact than traditional methods. I always wanted to get rid of loops, and vectorization of NumPy clearly helps me with that. Now let's talk about the applications of NumPy. NumPy, along with pandas, is extensively used in data analysis, which forms the basis of data science. It helps in creating the powerful n-dimensional array. Whenever we talk about NumPy, the mention of the array, we cannot do it without the mention of the powerful n-dimensional array. Also, NumPy is extensively used in machine learning when we are creating machine learning models, as in where it forms the base of other libraries like SciPy, scikit-learn, etc. When you start creating the machine learning models in data science, you will realize that all the models will have their base as NumPy or pandas. Also, when NumPy is used with SciPy and Matplotlib, it can be used as a replacement of MATLAB. Now let's look at a simple example of an array in NumPy. As you can see here, there are multiple array manipulation routines. Like there are basic examples where we can copy the values from one array to another. We can give a new shape to an array from maybe one dimensional to we can make it as a two-dimensional array. We can return a copy of the array collapsed into one dimension. Now let's look at an example where this is a Jupyter notebook and we will just create a basic array, and for detailed explanation you can watch our other videos which targets on these explanations of each libraries. So first of all, whenever we are using any library in Python, we have to import it. So now this np is the alias which we will be using. Let's create a simple array. Let's look what is the type of this array. So this is an NdArray type of array. Also, let's look what's the shape of this array. So this is a shape of the array. Now here we saw that we can expand the shape of the array. So this is where you can change the shape of the array using all those functions. Now let's create an array using arrange functions. If I give arrange 12, it will give me a 1D array of 12 numbers like this. Now we can reshape this array to 3, 4, or we can write it here itself. So this is how arrange function and the reshape function works for NumPy. Now let's discuss the next library, which is SciPy. So this is another free and open source Python library extensively used in data science for high-level computations. So this library, as the name suggests, stands for Scientific Python, and it has around 19,000 commits on GitHub with an active community of 600 contributors. It is extensively used for scientific and technical computations. Also, as it extends NumPy, it provides many user-friendly and efficient routines for scientific calculations. Now, let's discuss about some features of SciPy. So SciPy has this collection of algorithms and functions which is built on the NumPy extension of Python. Secondly, it has various high-level commands for data manipulation and visualization. Also, the NdImage function of SciPy is very useful in multi-dimensional image processing, and it includes built-in functions for solving differential equations, linear algebra, and many more. So that was about the features of SciPy. Now let's discuss its applications. So SciPy is used in multi-dimensional image operations. It has functions to read images from disk into NumPy arrays, to write arrays to disk as images, resize images, etc., solving differential equations, Fourier transforms, then optimization algorithms, linear algebra, etc. Let's look at a simple example to learn what kind of functions are there in SciPy. Here I'm importing the constants package of SciPy library. So in this package, it has all the constants. So here I'm just mentioning C or H or NA, and this library already knows what it has to fetch, like speed of light, Planck's constant, etc. So this can be used in further calculations. Data analysis is an integral part of data science. Data scientists spend most of the day in data munging and then cleaning the data also. Hence, mention of pandas is a must in data science lifecycle. Yes, pandas is the most popular and widely used Python library for data science, along with NumPy and Matplotlib. The name itself stands for Python Data Analysis, with around 17,000 commits on GitHub and an active community of 1,200 contributors. It is heavily used for data analysis and cleaning, as it provides fast, flexible data structures like data frames, series, which are designed to work with structured data very easily and intuitively. Now let's talk about some features of pandas. So pandas offers this eloquent syntax and rich functionalities. Like there are various methods in pandas like drop NA, fill NA, which gives you the freedom to deal with missing data. Also, pandas provides a powerful apply function, which lets you create your own function and run it across a series of data. Now forget about writing those for loops while using pandas. Also, this library's high-level abstraction over low-level NumPy, which is written in pure C. Then it also contains these high-level data structures and manipulation tools, which makes it very easy to work with pandas, like their data structures and series. Now let's discuss the applications of pandas. So pandas is extensively used in general data wrangling and data cleaning. Then pandas also finds its usage in ETL jobs for data transformation and data storage, as it has excellent support for loading CSV files into its data frame format. Then pandas is used in a variety of academic and commercial domains, including statistics, finance, neuroscience, economics, web analytics, etc. Then pandas is also very useful in time series specific functionality like date range generation, moving window linear regression, date shifting, etc. Now let's look at a very simple example of how to create a data frame. So data frame is a very useful data structure in pandas, and it has very powerful functionalities. So here I'm only enlisting important libraries in data science. You can explore more of our videos to learn about these libraries in detail. So let's just go ahead and create a data frame. I'm using Jupyter Notebook again, and in this, before using pandas, here I'm importing the pandas library. Let me go and run this. So in data frame, we can import a file, a CSV file, Excel file. So there are many functions doing these things, and we can also create our own data and put it into data frame. So here I am taking random data and putting in a data frame. Also I'm creating an index and then also giving the column names. So PD is the alias we've given for pandas, random data of 6x4, index, which is taking a range of 6 numbers, and column name I'm giving as ABCD. Now let's go ahead and look at it. So here it has created a data frame with my column names at ABCD, my list as 6 numbers 0 to 5, and a random data of 6x4. So data frame is just another table with rows and columns where you can do various functions over it. Also, I can go ahead and describe this data frame to see. So it's giving me all these functionalities where count and mean and standard deviation, etc. Okay, so that was about pandas. Now let's talk about next library and the last one. So matplotlib for me is the most fun library out of all of them. Why? Because it has such powerful yet beautiful visualizations. We'll see in the coming slides. Plot in matplotlib suggests that it's a plotting library for Python. It has around 26,000 commits on GitHub and a very vibrant community of 700 contributors. And because of such graphs and plots that it produces, it's majorly used for data visualization. And also because it provides an object-oriented API which can be used to embed those plots into our applications. Let's talk about the features of matplotlib. The pyplot module of matplotlib provides MATLAB-like interface. So matplotlib is designed to be as usable as MATLAB with an advantage of being free and open source. Also, it supports dozens of backends and output types, which means you can use it regardless of which operating system you're using or which output format you wish. Pandas itself can be used as wrappers around matplotlib's API so as to drive matplotlib via cleaner and more modern APIs. Also, when you start using this library, you will realize that it has a very little memory consumption and a very good runtime behavior. Now let's talk about the applications of matplotlib. It's important to discover the unknown relationship between the variables in your dataset. So this library helps to visualize the correlation analysis of variables. Also in machine learning, we can visualize 95% confidence interval of the model just to communicate how well our model fits the data. Then matplotlib finds its application in outlier detection using scatterplot, etc. and to visualize the distribution of data to gain instant insights. Now let's make a very simple plot to get a basic idea. I've already imported the libraries here. So this function matplotlib inline will help you show the plots in the Jupyter notebook. This is also called a magic function. I won't be able to display my plots in the Jupyter notebook if I don't use this function. I'm using this function in NumPy to fix random state for reproducibility. Now I'll take my n as 30 and will assign random values to my variables. So this function is generating 30 random numbers. Here I'm trying to create a scatter plot. So I want to decide the area. Let's put this. So it's just multiplying 30 with random numbers to the power 2 so that we get the area of the plot, which we will see in just a minute. So using the scatter function and the alias of matplotlib as plt, I've created this. If I don't use this, then I have very small circles as my scatter plot. It's colorful, it's nice. So that's one very easy plot. I suggest that you explore more of matplotlib and I'm sure you will enjoy it. Let's create a histogram. So I'm using the style as ggplot and assigning some values to these variables, any random values. Now we are assigning bars and colors and alignment to the plot. And here we get the graph. So we can create different type of visualizations and plots and then work upon them using matplotlib, and it's just that simple. So that was about the leading Python libraries in the field of data science. But along with these libraries, data scientists are also leveraging the power of some other useful libraries. For example, like TensorFlow, Keras is another popular library which is extensively used for deep learning and neural network modules. Keras wraps both TensorFlow and Theano backends, so it is a good option if you don't want to dive into details of TensorFlow. Then Scikit-learn is a machine learning library. It provides almost all the machine learning algorithms that you need, and it is designed to interpolate with NumPy and SciPy. Then we have Seaborn, which is another library for data visualization. We can say that Seaborn is an enhancement of matplotlib as it introduces additional plot types.
After completing this lesson, you'll be able to explain the various types of graphics available in R, list the possible file formats of graphic outputs, describe the methods to save graphics as files, and describe the procedure to export graphs in RStudio. With its large set of powerful functions, R defines a flexible graphical environment for the visual representation of data. These graphics that help in meaningful data visualization can be viewed on screen, and users can create precisely customized graphical output. The graphics can be saved in various good quality formats, including PDF, PNG, JPEG, WMF, and PS. Typically, graphs are designed on screen, which can then be replotted on, for example, a PDF file. You can also copy and paste in case of a Word or PowerPoint file. Using R, you can produce a variety of graphical images. Basic 3D plots, scatter plots, bar plots, histograms, box plots, and pie charts are 8 standard statistical plots that R can provide. R can also support heat maps, word cloud, kernel density plots, and line charts. Let us look into details of each of these graphics in the subsequent screens. Plotted on vertical or horizontal bars, bar graphs show discrete comparisons among categorical data. The lengths of the bars, each of which represents a category, indicates the frequency, percentage, or proportion of values that fall into the categories. The syntax to create a simple bar chart is barplot x. In the function, x stands for height, which is a matrix or vector. If the height parameter is a vector, the values of the vector give the heights of the sequence of rectangular bars that make up the plot. Let's look at a few examples of how to create vertical and horizontal bar charts. Here, by using an embedded dataset of MT cars, you can plot bar graphs. To create the first bar graph, you pass gear data to the bar plot function. The default setting for bar orientation is vertical. To plot a horizontal graph, you can pass horizontal equals true as the second parameter to the bar plot function. In the next screen, we'll take a quick look at a few arguments to edit simple bar plots. You can add labels, colors, and titles to the bar plot by using specific arguments. For example, legend.text is useful when the height is a matrix. The arguments xlab and ylab provide the labels for the x-axis and y-axis respectively. Call will define the color of each bar. By default, if height is a vector, then gray is used, whereas if height is a matrix, a gamma-corrected gray palette is used. Main sub gives the overall and subtitles for the bar plot. This demo will show the steps to create a bar chart in R. In this demo, you'll learn how to create bar charts. For this data, we will use the MT cars dataset available in R. Simple bar charts can be created using the bar plot function. You can create horizontal bars by specifying horizontal equals true as an argument to the bar plot function. You can also add title, colors, and legends to bar plot by specifying details in an argument. For more options or help document, type the given command in the console. You can create a stacked bar plot if the input is a matrix. The stacked bar will indicate each column on the matrix. The argument beside specifies if you want the bars to be stacked or adjacent to each other. By default, beside is set to false, and if height is a matrix, a stacked bar graph results. If you set beside to true, then you get the columns of height as adjacent bars. You can create a stacked bar plot with colors and legends as shown in the screen. Here in this example on the screen, it's a matrix of VS and gear data from MT cars datasets. Using the same example as in the previous screen, you can create a grouped bar plot. Reiterating, if the height parameter of bar plot function is a matrix and beside is set to true, then the values in each column are juxtaposed rather than stacked. Here, you use the row names function to set the legend, which will set or retrieve the names of rows or columns of a matrix-like object. In this demo, we'll show the steps to create a stacked bar plot and a grouped bar plot in R. In this demo, you'll learn how to create a stacked bar plot and a grouped bar plot. For this data, we'll use the MT-CARS dataset available in R. For a stacked bar plot and a grouped bar plot, we'll have to create a table like data from the MT-CARS dataset using the table function. You can create a stacked bar plot using the bar plot function. You can also add title, colors, and legends to bar plot by specifying details in an argument. You can create a grouped bar plot by specifying beside equals true as an argument to the bar plot function. For more options or help document, type the given command in the console. Pie chart is a type of graph in which a circle is divided into sectors, each representing a proportion of the whole. Pie charts are not as popular as dot plots or bar charts in R. You can create pie charts using the function pi x, labels equals. Here, x is a vector of non-negative numerical quantities. The value of x indicates the area of a pie slice. Labels are character strings or expressions that give names to vectors. In the example shown here, you first create the slices vector, which contains numbers 10, 12, 4, 16, and 8. LBLS is the labels vector. Then you pass both these vectors to the pi function as parameters. To set the overall title for the plot, you pass main as a parameter. In this screen, you can see how percentages can be added to the pie chart. In the given example, out of the data vector, you can create the PCT vector and a character vector, LBLS, to add actual labels to the slices. To paste data to the labels vector and add the percentage sign, you use the paste function. Another character vector, call, helps fill in or shade the pie slices. Let's now see how you can create a three-dimensional pie chart. Using the Plottrix package, which has the Pi3D function, you can produce 3D representations of pie charts. There is an explode parameter that enables the pieces to be separated on the chart. However, you first have to install the Plottrix package and reference it using the library function install.packages Plottrix library Plottrix. This demo will show the steps to create a pie chart in R. In this demo, you'll learn how to create pie charts. Pie chart graphics are not available by default. You'll have to install the Plottrix package by using the given command. After installing, you'll have to load the package into R using the given command. For this demo, we'll create a custom dataset using vectors. We can create pie charts using the pi function in the Plottrix package. We can also add a title and labels by specifying the details in an argument. You can create 3D pie charts using the Pie3D function in the Plotrix package. For more options or help document, type the given command in the console. Let's look at another visual representation of data distribution, the histogram. Histograms are a great way to get to know your data. A histogram has an x-axis, a y-axis, and bars of different heights. The bars group ranges of values or continuous categories on the x-axis, and the y-axis shows how frequently the values on the x-axis occur in the data. They display the distribution of a continuous variable and the frequency of scores in each bin on the y-axis by dividing the range of scores into bins on the x-axis. As shown on the screen, the syntax for a histogram is hist in R. For a given set of data values, the generic function hist works out a histogram. If plot equals true, plot.histogram plots the resulting object of class histogram before it's returned. You can create a histogram using the histx function, where x is a vector of values for which you want to plot the histogram. Instead of frequencies, the option frequency equals false plots probability density when you want a histogram of proportion. To control the number of bins, that is bars, use the breaks equals controls option. The break argument helps you control the bin width along with the number of breakpoints you desire. In the example shown on the screen, you can see histograms for dark green colored bins that indicate the miles per gallon or MPG value of the MT cars dataset. A more effective way of visualizing numeric variable distribution, kernel density plots are created using the plot density x function as shown on the screen. Here, x is a density object. You can use the density function to compute the density parameter in plot. In the example shown in this slide, you can create a kernel density graph for the mileage per gallon, or MPG, of MT cars dataset by first calculating its density and then creating the graph. In the second figure, use the polygon function for kernel density of the data for MPG. Vertices are given in X and colors of the area and the border are given by color equals sky blue and border equals black, respectively. This demo will show the steps to create a histogram and density plot in R. In this demo, you'll learn how to create histograms and a density plot. For this demo, we'll use the MT cars dataset available in R. Histograms can be created using the hist function. You can also specify the number of bins and the color of bin as arguments to the hist function. For the density graph, we'll have to calculate the density of data using the density function and then use the density data to plot the density graph using the plot function. You can color the curve representing density using the polygon function. For more options or help document, type the given commands in the console. Line charts represent a series of data points, called markers, connected by a straight line. This type of graphical visualization is typically used to display data that changes over time. As shown on the screen, the syntax for a line chart is lines, x, y, type equals, where x and y are coordinates of the points. Type indicates the type of plot to be drawn, say L for line and P for points, or B for both. Let's now look at an example of a line chart. In the code shown in this slide, you can create weight and months vectors, and then plot a line and points graph together by calling the plot function. These two vectors are passed as parameters along with main to set the title of the graph as baby weight chart. Also known as whisker diagrams, box plots display the distribution of data that is based on the 5-number summary. Minimum, smallest value in the data set. First quartile, 25th percentile. Median, 50th percentile. Third quartile, 75th percentile. Maximum, largest value in the data set. And data is broken into 4 quartiles in box and whisker plots, and each quartile has the same number of data values. Although these plots do not display the frequency, they show where the middle of the data is, a feature that is really useful if you want to analyze the skewness of your data. The syntax to create a box plot is shown on the screen. Boxplot data. A box can be created either for individual variables or for variables by group. As shown on the screen, the syntax is boxplot x data equals, where x is a formula and data equals denotes the data frame providing the data. To make the widths of the box plot proportional to the square roots of the number of observations in the sample, use varWidth equals true. With horizontal equals true, you can reverse the orientation of the axis. Default false means the box plots are vertical. In the code shown here, a vector of numbers was created and the summary function called to print the values of the following variables: minimum, first quartile; median, mean third quartile; maximum. Then the boxplot function was used to display the box plot for the vector of numbers. This demo will show the steps to create line graphs and a box plot in R. In this demo, you'll learn how to create line graphs and a box plot. For this demo, we'll create custom dataset using vectors. We'll use the plot function to create line graphs. Points in a line graph can be connected by specifying type equals b as an argument in the plot function. We can create boxplot using the boxplot function. For more options or help document, type the given commands in the console. Heat maps are two-dimensional representations of data in which the values are represented by colors. The two types of heat maps are simple and elaborate heat maps. A simple heat map provides an immediate visual summary of information. An elaborate heat map allows you to understand complex data sets. Rows and columns can be clustered in a heat map, and the result of the hierarchical clustering computation is shown as a dendrogram in the heat map. As shown on the screen, the syntax to create a heat map is heat map data row v equals NA, column v equals NA. Here, row v and column v decide if and how row and column dendrograms should be calculated or reordered. Data refers to the matrix of values that has to be plotted. Let's look at an example that shows you how to create a heat map. In the code shown here, you can create a data frame by reading data from a CSV file and converting it to a data frame before passing it to the heat map function. Besides data, row v and column v as not applicable, color as 256, and scale as columns to plot a heat map graph are passed to the heat map function. This demo will show the steps to create a heat map in R. In this demo, you'll learn how to create a heat map. For this demo, you'll use the custom dataset imported from a CSV file. A heat map can be constructed using the heat map function. You can also specify the color and scale details as arguments to the heat map function. For more options or help document, type the given command in the console. Also known as tag clouds or text clouds, word clouds highlight the most commonly cited words in a text using a quick visualization. Creating a word cloud in R is relatively simple using a text mining package, TM, and word cloud generator package, word cloud. As shown on the screen, to create a word cloud, use the syntax word cloud, words equal data, frequency equals frequency, min.frequency equals 2, etc. You need to install the word cloud package into the R environment using the install.packages, word count, and library word count commands. In the example on this screen, text data is read from a CSV file, and a word count graph is plotted using the word count function. Passwords, frequency, min.frequency as 2, max.words as 100, and random.order as false. The minimum.frequency argument specifies the minimum frequency below which words that have a frequency lower than that value will not be plotted. The maximum number of words to be plotted are determined by the max.words argument. Random.order means that the words will be plotted in a random order. If false, the words are plotted in decreasing frequency. This demo will show the steps to create a word cloud in R. In this demo, you'll learn how to create a word cloud. Word cloud graphics are not available by default. You'll have to install the word cloud package using the given command, and then load the package using the other command. For this demo, we'll use the custom data imported from the CSV file. We can use the word cloud function to create a word cloud. We can also specify the minimum frequency and maximum word as arguments to the word cloud function. For more options and help document, type the given command in the console. Let's now take a look at the various file formats for saving your plots. R supports several graphic formats and runs on different operating systems. Consequently, there are many formats to choose from depending on what you want to do with the graph, how you connect remotely or locally, and what operating system you use. A few of the available formats are as follows. JPEG doesn't resize and can be used anywhere. PDF easily resizable and is the best choice with PDF latex. PNG doesn't resize and can be used anywhere. WMF easily resizable and works on Windows only. Best choice with Word. PostScript easily resizable and is the best choice with OpenOffice and LaTeX. On the slide, you can see an example to save a graphic output as a file. Regardless of the way you connect or the type of operating system you use, the general method that will work on any computer that has R involves the following steps. Select the file format you want. For example, if you want to save your plot as a JPEG file, use the JPEG driver, which only requires the name of the file that you will use to save the graph. Note that your plot will be stored relative to the current directory, which can be found by typing getwd at the R prompt. Entering your plotting commands next will save those to a file. Then use the dev.off command to close the file. Either you will get a partial plot or nothing in case you fail to enter the dev.off command after you are done with the plotting commands. So if you want to save a JPEG file called myplot.jpg containing a bar graph, you will type the commands as shown on the screen. Recalling the example from the previous screen, you will see that you need to re-enter the commands to save your plot to a file after making a plot to the screen. However, in R, there is another command, dev.copy, which will copy the contents of the graph window to a file without the hassle of re-entering the commands. In this approach, produce the graph as you usually do, and then call dev.copy along with the arguments that are appropriate to the driver. For example, to create a myplot.jpg file from a graph shown by R, type the commands shown on the screen. Until you call dev.off, the plot isn't actually written to the file. This demo will show the steps to save graphics to a file in R. In this demo, you'll learn how to save graphics to a file. You can save a graphic as a JPEG file using the JPEG function. You'll also have to use the dev.off function to return the control to the console back again. For more options and help document, type the given command in the console. In this screen, let's see how you can export graphs in RStudio. Follow these steps to export graphs in RStudio, a powerful interface for R. In the graphics panel of RStudio, click the Plots tab. Click the Explore menu and select the Save as Image menu item. The Save Image window is displayed. Select the image format and directory to save the file. Click the Save button. Follow these steps to export graphs as PDFs in RStudio. In the Graphics panel of RStudio, click the Export menu and select the Save as PDF menu item. Select the directory to save the file. Click the Save button. This demo will show the steps to save graphics using RStudio. In this demo, you'll learn how to save graphics using RStudio. You can save a graphic from RStudio by clicking the Export menu and selecting Save as Image. Select the directory to save the file, and then click Save. Let's summarize the topics covered in this lesson.
And if you are one of the aspiring data scientists looking for online training and graduating from the best universities, or a professional who highly sets to switch careers with data scientist by learning from the experts, then try going a short to Simplilearn Caltech postgraduate program in data science in collaboration with IBM. The course link is mentioned in the description box below, and you will navigate to the course page where you can find a complete overview of the program being offered.
So, what does Python have for data science? Python is an interpreted, dynamically typed language with a precise and efficient syntax, and is renowned for its ease of use to analyze, visualize, and present data. Python has an extensive library with built-in modules, providing easy access to system functionalities, which not only improves accessibility, but also provides standardized solutions for everyday programming challenges. By taking away platform-specific requirements and replacing them with platform-neutral APIs, modules in Python libraries encourage users to make programs portable. Why should a data scientist use Python? Apart from being an open-source ecosystem, Python and most of its incredible libraries are platform-independent, so you can run this notebook on Windows, Linux, or OS X without a change. Python is part of the winning formula for productivity, software quality, and maintainability at many companies and institutions around the world. Python is one of the leading technologies used widely in academic circles and industries because of its flat learning curve. Still not sold on Python? Then here's some proof. Case study. ForestWatch.com, a weather report accuracy rating service, is a 100% Python solution, using it in all its components, the front end, back end, as well as the performance critical portions. Python was chosen to develop this solution as it comes with many standard libraries useful in collecting, parsing, and storing data from the web. Python is impressive as an object-oriented, rapid application development language. One of Python's key strengths lies in its ability to produce results quickly without sacrificing maintainability of the resulting code. Because of the clean design of the language, refactoring the Python code was also much easier than in other languages. Moving code around simply requires less effort. ForecastWatch.com was made possible because of the ease of programming complex tasks in Python, the rapid development that Python allows, the ease to analyze and represent data in a simple and visually appealing style. Market potential. So how does the future look for Python as the tool for data science? According to KD Nuggets, 46% of all the data science jobs list Python as the skill required, second only to SQL. According to a survey by the Association for Computing Machinery, ACM, posted on javaworld.com, Python has surpassed Java as the top language used to introduce U.S. students to programming and computer science. Projected skill gap. There is also going to be a huge demand for data scientists who know Python. McKinsey & Company, a trusted advisor and counselor for many of the world's most influential businesses and institutions, projects that by 2018, the demand for data scientists who know Python may surpass supply by perhaps 60%, making Python a must-know skill for data scientists. Forbes.com mentions that the demand for Python programmers in big data-related positions increased by 96.9% in 12 months.
Now let's talk about Python. For doing data science, we need some kind of a programming language or a tool and so on. So this session will be about Python. There are other tools like, for example, R, and we will probably do a separate video on that. But this session is on Python, and you must have already heard Python is really becoming very popular. Everybody is talking about Python, not only data science, in IoT and AI and many other places. So it's getting very popular. So if you are not yet familiar with Python, this may be a good time to get started with it. So why do we want to use Python? So basically, Python is used as a programming language because it is for data science, because it has some rich tools from a mathematics and from a statistical perspective. It has some rich tools. So that is one of the reasons why we use Python. And if you see some of the trends, if you're probably tracking some of the trends, you will see that over the last few years, Python has become programming language of choice, and especially for data science, SAS was earlier one of the most popular tools, but now increasingly Python is being used for doing data science, and of course as well as R. One of the reasons, of course, is that Python and R are open source compared to SAS, which is a commercial product. So that could definitely be one explanation, but beyond that, I think it is the ease of understanding this language, the ease of using this language, which is also making it very popular, in addition to the availability of fantastic libraries for performing data science. What are the other factors? There are speed, then there are availability of number of packages, and then of course the design goal. Alright, so what are each of these? Design goal. Primarily, the syntax rules in Python are relatively intuitive and easy to understand. Thereby, it helps in building applications with concise and readable code base. So with a few lines of code, you can really achieve a lot of stuff. And then there are a lot of packages that are available that have been developed by other people, which can be reused. So we don't have to reinvent the wheel. And last but not least, the speed. So Python is a relatively faster language. Of course, it is not as fast as, let's say, C or C++, but then relatively it is still faster. So these are the three factors which make Python the programming language of choice. So if you want to get started with Python, the first thing obviously is to install Python. So there is some documentation, and there are some steps that you need to follow. So we will try to briefly touch upon that. Otherwise, of course, there is a lot of material available on how to install Python and so on. You can always look around, but this is one of the, again, there are different ways in which you can also install Python. So we will use the Anaconda path. There is a packaging tool called Anaconda. So we will use that path. You can also directly install Python, but in our session we will use the Anaconda route. So the first thing you need to do is download Anaconda, and this is the path for that. And once you click on this, you will come to a page somewhat like this, and download, you can do the corresponding download based on whether you have a Windows or Ubuntu. There is also a download possible for, or package available for Ubuntu if you are doing something on Ubuntu. So based on which operating system, in fact this page will automatically detect which operating system you're having, and it will actually suggest. So for example, you see here, if you're running Mac OS, then it will automatically detect that you have Macs, and the corresponding installers will be displayed here. Similarly, if you're on some flavor of Linux like Ubuntu or any other, then you will get the corresponding download links here. And then beyond that, you can also select which version of Python you want to install. Of course, the latest version is in the 3.x range at the time of recording. This 3.6 is one of the latest versions, but some of you may want to do or start with the earlier version, which is Python 2.7, 2.x, and you can download that as well. If you don't have anything installed, then my suggestion is start with Python 3.6. Alright, so once you do that, you will be able to install Python and you will be able to run Jupyter Notebook. Okay, so now that you know how to install Python, and if you have installed Python, let's take a look at what are the various libraries that are available. So Python is a very easy language to learn, and there are some basic stuff that you can do. For example, adding or printing a hello world statement and so on without importing any specific libraries. But if you want to perform data analysis, you need to include or import some specific libraries. So we are going to talk about those as we move forward. So pandas, for example, is used for structured data operations. So if you, let's say, are performing something on on a CSV file. You import a CSV file, create a data frame, and then you can do a lot of stuffs like data munging and data preparation before you do any other stuff, like for example machine learning or so on. So that's pandas. SciPy, as the name suggests, it provides more scientific capabilities, like for example it has linear algebra, it has Fourier transform, and so on and so forth. Then you have NumPy, which is a very powerful library for performing n-dimensional or creating n-dimensional arrays, and it also has some of the stuff that is there in SciPy, like for example linear algebra and Fourier transform and so on and so forth. Then you have Matplotlib, which is primarily for visualization purpose. It has again very powerful features for visualizing your data, for doing the initial what is known as exploratory data analysis, for doing univariate analysis, bivariate analysis. So this is extremely useful for visualizing the data. And then Scikit-learn is used for performing all the machine learning activities. If you want to do anything like linear regression, classification, or any of this stuff, then the Scikit-learn library will be extremely helpful. In addition to that, there are a few other libraries, for example, networks and iGraph. Then of course a very important one is TensorFlow. So if you are interested in doing some deep learning or AI related stuff, then it would be a good idea to learn about TensorFlow, and TensorFlow is one of the libraries. There is a separate video on TensorFlow, you can look for that, and this is one of the libraries created by Google, open source library. So once you're familiar with machine learning, data analysis, machine learning, then that may be the next step to go to deep learning and AI. So that's where TensorFlow will be used. Then you have Beautiful Soup, which is primarily used for web scraping, and then you take that data and then analyze and so on. Then OS library is a very common library. As the name suggests, it is for operating system. So if you want to do something on creating directories or folders and things like that, that's when you would use OS. Alright, so moving on, let's talk in a little bit more detail about each of these libraries. So SciPy, as the name suggests, is a scientific library, and it very specifically, it has some special functions for integration and for ordinary differential equations. So as you can see, these are mathematical operations or mathematical functions. So these are readily available in this library, and it has linear algebra modules, and it is built on top of NumPy. So we will see what is there in NumPy. So this is again, as the name suggests, the num comes from numbers. So it is a mathematical library, and one of its key features is availability of an n-dimensional array object. That is a very powerful object, and we will see how to use this. And then of course you can create other let's say objects and so on. And it has tools for integrating with C, C++, and also Fortran code. And then it of course also has linear algebra and Fourier transformation and so on, all these scientific capabilities. Okay, what else? Pandas is another very powerful library, primarily for data manipulation. So if you're importing any files, you will want to create it like a table. So you will create what is known as data frames. These are very powerful data structures that are used in Python programming. So Pandas library provides this capability. And once you import the data into data frame, you can pretty much do whatever you're doing like in a regular database. So people who are coming from a database background or SQL background would really like this, because it is they will feel very much at home, because it feels like you're viewing a table or using a table, and you can do a lot of stuff using the Pandas library. Now there are two important terms or components in Pandas, series and the data frame. I was just talking about the data frame. So let's take a look at what are series and what is a data frame. So within Pandas we have series and data frame. So series is primarily, some of you may also be knowing this as let's say an array. So it's a one-dimensional structure, data structure if you will. So in some other languages we may call it as an array, or maybe some others probably an equivalent of a list. In R perhaps, I'm not very sure on that aspect, but yes. So this is like a one-dimensional storage of information. So that is what is series. Whereas data frame is like a table. So you have a two-dimensional structure, you have rows and you have columns, and this is very, people, as I said, who are familiar with SQL and databases will be able to relate to this very quickly. So you have like a table, you have rows and columns, and then you can manipulate the data. So if you want to create a series, this is how you would create a code snippet. And as you can see, the programming in Python is very simple. There are no major overheads. You just need to import some libraries which are essential and then start creating objects. So you don't have to do additional declaration of variables and things like that. So that is, I think, one key difference between Python and other programming languages. And what does this series contain? It has to contain these numbers 6, 3, 4, 6, and X is my object consisting of the series. So if you just say X, it will display the contents of X, and you will see here that it creates a default index. Then you have data frame. So if you want to create a data frame, as you can see, the series is like a one-dimensional structure. There is just like a row, one row of items, whereas a data frame looks somewhat like this. It is a two-dimensional structure. So you have columns in one dimension, and then you have rows in the other dimension. How do you create a data frame? You need to rather import pandas, and then you import. In this case, we are basically creating our own data. So that's the reason we are importing NumPy, which is one of the libraries we just referred to a little bit before. So we are using one of the functionalities within NumPy to create some random numbers. Otherwise, this is not really mandatory. You probably will be importing the data from outside, maybe some CSV file, and import into the data frame. So that's what we are doing here. So in this case, we are creating our own test data. That's the reason we are importing NumPy as NP, and then I create a data frame saying pd.dataframe. So this is the keyword here. Similarly here in this case, while creating series, we said pd.series, and then you pass the values. Similarly here, you're saying pd.dataframe. Now in order to create the data frame, it needs the values in each of these cells. What are the values in the rows and what are the values in the columns? So that in our example we are providing using this random number generator. So np.random is like a class or a method that is available in NumPy, and then you are saying, okay, generate some random numbers in the form of a 4x3 matrix or 4x3 data frame. The 4 here indicates the number of rows and the 3 here indicates the number of columns. So these are the columns, 0, 1, 2 are the columns, and these are the rows. Here 0, this is 1, this is 2, this is 3. Okay, and once again it will, when you display df, it will give us a default index. There are ways to omit that, but at this point we will just keep it simple. So it will display the default index and then the actual values in each of these rows and columns. So this is the way you create a data frame. So now that we have learned some of the basics of pandas, let's take a quick look at how we use this in real life. So let's assume we have a situation where we have some customer data and we want to kind of predict whether a customer's loan will be approved or not. So we have some historical data about the loans and about the customers, and using that we will try to come up with a way to maybe predict whether loan will be approved or not. So let's see how we can do that. So this is a part of exploratory analysis. So we will first start with exploratory analysis. We will try to see how the data is looking. So what kind of data? So we will, of course, I'll take you into the Jupyter notebook and give you a quick live demo. But before that, let's quickly walk through some of the pieces of this program in slides, and then I will take you actually into the actual code and do a demo of that. So the Python program structure looks somewhat like this. The first step is to import all the required libraries. Now, of course, it is not necessary that you have to import all your libraries right at the top of the code, but it is a good practice. So if you know you are going to need a certain set of libraries, it may be a good idea to put, from a readability perspective, it's a good practice to put all the libraries that you're importing at the beginning of your code. However, it is not mandatory. So in the middle of the code somewhere, if you feel that you need a particular library, you can import that library and then start using it in the middle of the code. So that's also perfectly fine. It will not give any errors or anything. However, as I said, it's not such a good practice. So we will import all the required libraries. In this case, we are importing pandas, NumPy, and matplotlib. And in addition, if we include this piece of code, %matplotlib inline, what will happen is all the graphs that we are going to create, the visualizations that we are going to create, will be displayed within the notebook. So if you want to have that kind of a provision, you need to have this line. So it's always a good idea when you're starting off. I think it's a good idea to just include this line so that your graphs are shown in line. Okay, so these are the four. We will start with these 4 lines of code. Then the next step is to import your data. So in our case, there is a training data for loans by the name loan p_train.csv, and we are reading this data. So in this case, you see here, unlike the previous example where we created a data frame with some data that we created ourselves, here we are actually creating a data frame using some external data, and the method is very straightforward. So you use the read_csv method, and it is a very intuitive function name, and you say pd.read_csv and give the path of the file, CSV file. That's about it, and then that is read into the data frame df. This can be any name. We are calling it df. You can call xyz, anything. There's a name, just the name of the object. So head is one of the methods within the data frame, and it will give us the first 5. So this is just to take a quick look. Now you have imported the data. You want to initially have a quick look how your data is looking. What are the values in some of the columns and so on and so forth, right? So typically you would do a head, df.head, to get the sample of, let's say, the first few lines of your data. So that's what has happened here. So it displays the first few lines, and then you can see what are the columns within that, and what are the values in each of these cells, and so on and so forth. You can also, typically you would like to see if there are any null values, or are there any, is the data for whatever reason is invalid or looking dirty for whatever reason, some unnecessary character. So this will give a quick view of that. So in this case, pretty much everything looks okay. Then the next step is to understand the data a little bit overall for each of the columns. What is the information? So the describe function will basically give us a summary of the data. What else can we do? Pandas also allows us to visualize the data, and this is more like a part of what we call it as univariate analysis. That means each and every column you can take and do some plots and visualization to understand data in each of the columns. So for example, here the loan amount column we can take, and then the hist method will create a histogram. So you take all the values from one column, which is loan amount, and you create a histogram to see how the data is distributed, right? So that's what is happening here. And as you can see, there are some extreme values. So this is again to identify, do we have to do some data preparation? Because if the data is in a completely haphazard way, the analysis may be difficult. So these are the initial or exploratory data analysis is primarily done to understand that and see if we need to do some data preparation before we get into the other steps like machine learning and statistical modeling and so on. So in this case, we will see that here by plotting this histogram, we see that there are some extreme values. So there are some values, a lot of it is around 100 range, but there is also something, 1 or 2 observations in the 700 range. So it's pretty scattered in that sense, or they're not really scattered, distributedly scattered, but it is randomly scattered. So the range is really huge. So what can we do about this? So there are some steps that we need to do, normalization and so on. So we'll see that in a bit. So this is for one of the columns. Let's take another column, which is applicant income. Similar situation. You have most of your observations in this range, but there are also some which are far off from where most of the observations are. So this is also this also has some extreme values. So we'll have to see what can be done. Credit history is the binary value. So some people have a 0 value and some will have credit history of 1. This is just like a flag. So this basically is telling us how many people have a 1 and how many people have 0. So looks like majority of them have a value of 1 and a few, about 100 of them, have a value of 0. Okay, what else can we do? So we now understood a little bit about the data. So we need to do some data wrangling or data munging and see if we can bring in some kind of normalization of all this data, and we will kind of try to understand what is data wrangling and before we actually go into it. Okay, so data wrangling is nothing but a process of cleaning the data. If let's say there are multiple things that can happen. In this particular example, there were no missing values, but typically when you get some data, very often it will so happen that a lot of values are missing. Either they are null values or there are a lot of zeros. Now you cannot use such data as it is to to perform some, let's say, predictive analysis or perform some machine learning activities and so on. So that is one part of it. So you need to clean the data. The other is unifying the data. Now, if these ranges of this data are very huge, some of them are going from, some columns are going from 0 to 100,000 and some columns are just between 10 to 20 and so on. These will affect the accuracy of the analysis. So we need to do some kind of unifying the data and so on. So that is what data wrangling is all about. So before we actually perform any analysis, we need to bring the data to some kind of a shape so that we can perform additional analysis, actual analysis on this and get some insights. Now, how do we deal with missing values? This is a very common issue when we take data or when we get data from the business, when a data scientist gets the data from the business. So we should never assume that all our data will be clean and all the values filled up and so on, because in real life, very often the data will be dirty. So data wrangling is the process where you kind of clean up the data. First of all, identify whether the data is dirty and then clean up. So how do we find some data is missing? So there are a few ways. You can write a small piece of code which will identify if for a given column or for a given row, any of the observations are null primarily. So this line of code, for example, is doing that. It is trying to identify how many null values or missing values are there for each of the columns. So this is a lambda function, and what we are saying is find out if a value is null and then you add all of them. How many observations are there where this particular column is null. So it does that for all the columns. So here you will see that for loan ID, obviously it's an ID, so there are no null values or missing values. Gender has about 13 observations where the values are missing. Similarly, marital status has 3 and so on and so forth. So we'll see here, for example, loan amount has 21 observations where the values are missing. Loan amount term has 14 observations and so on. So we'll see how to handle this missing values. So there are multiple ways in which you can handle missing values. If the number of observations are very small compared to the total number of observations, then sometimes one of the easy ways is to completely remove that data, or delete that record, exclude that record. So that is one way of doing it. So if there are, let's say, 1 million records and maybe 10 records are having missing values, it may not be worth doing something to fill up those values. It may be better off to get rid of those observations, right? So that is, the missing values are proportionately very small. But if there are a relatively large number of missing values, if you exclude those observations, then your accuracy may not be that very good. So the other way of doing it is we can take a mean value for a particular column and fill up wherever there are missing values, fill up those observations or cells with the mean value. So that way what happens is you don't give some value which is too high or too low, and it somehow fits within the range of the observations that we are seeing. So this is one technique. Again, it can be case to case, and you may have to take a call based on your specific situation, but these are some of the common methods. If you see in the previous case, loan amount had 21, and now we went ahead and filled all of those with the mean value. So now there are 0 with missing values. Okay, so this is one part of a data wrangling activity. What else you can do? You can also check what are the types of the data. So df.dtypes will give us what are the various data types. So all right. So you can also perform some basic mathematical observations. We have already seen that mean we found out. So similarly, if you do call the mean method for the data frame object, it will actually perform or display or calculate the mean for pretty much all the numerical columns that are available in this, right? So for example, here applicant income, co-applicant income, and all these are numerical values. So it will display the mean values of all of those. Now, another thing that you can do is you can actually also combine data frames. So let's say you import data from one CSV file into one data frame and another CSV file into another data frame, and then you want to merge these because you want to do an analysis on the entire data. Okay, one example could be that you have data in the form of CSV files, one CSV file for each month of the year. January, February, March, each of these are in a different. So you can import them into, let's say, 12 data frames, and then you can merge them together as a single data frame, and then you perform your analysis on the entire data frame or the entire data for the year. So that is one example. So how do we do that? This is how we do. Again, in this case, we are not importing any data. We are just creating some random values, using some random values. So let's assume I have a data frame which is by the name 1, and I assign some random values here, which is a 5x4 format. So there are 5 rows and 4 columns, and this is how my data frame 1 looks. And then I create another data frame, which is data frame 2, again random numbers of the format 5x4, and I have something like this. Now I want to combine these two. How do I combine these two? I can use the concatenate or concat method, and I can combine these two. So pd.concat, and it takes the data frames 1 and 2. If you have more of them, you can provide them, and it will just simply add all of them, merge all of them, or concatenate, whatever you call, whichever term you call, it will. So of course we have to make sure that the structure remains the same. Like I said, this could be, let's say, sales data coming for 12 different months, but each of the files has the same structure. So now you can combine all of them, merge all of them using the concat method. If we have, let's say, structure is not identical, then what will happen? Let's say we have these two data frames. One has a column by the name key, and the second column is lval, and a second data frame which has a column by the name key, but the second column by the name rval, not lval. So you see here the structure is not identical. So you can still combine them, but then the way they get combined or merged is somewhat like this. So it takes the key as a common parameter between them. Some common column has to be there, otherwise this will not work. And then we have to use merge instead of concatenate. And when we do a merge, then we get the result will be in this format. What it does is it uses the key as a common thread between them, and then it kind of populates the values accordingly. So if you see here, the first one had foo and bar for key, and then it had L values of 1 and 2, right? So if we go back, foo and bar had 1 and 2 L values. So that's what we see here, 1 and 2. Whereas in the right data frame, we had foo, bar, and bar as a second time, and then R values are 3, 4, and 5. So what it has done for foo, it has put for the existing, right? For foo is already existing because it has come from left. So it will just put the value of R val here, which is 3. Similarly, it will put 4 here because for bar, if you go back, for bar it is the value is 4. And since it has one more value of bar, it will go and add this 5 as well. The only thing here is that this one had, for example, left had only 2 values and only 1 value for bar. But since we are appending or merging, and there are 2 key values with the bar, therefore it will kind of repeat the value of lval here. So that's what we are seeing in this case, right? So L value appears twice, the number 2 appears twice, but that is because R value, there are 2 of them. Okay. All right. So that is how, when you don't have identical structure, that is how you merge. Now we will talk a little bit about scikit-learn. So scikit-learn is a library which is used for doing machine learning or for performing machine learning activities. So if you want to do linear regression, logistic regression, and so on, there are easily usable APIs that you can call. And that's the advantage of scikit-learn, and it provides a bunch of algorithms. So I think that is the good part about this library. So if you want to use scikit-learn, obviously you need to import these modules, and also there are some sub modules you may have to import based on what you're trying to use. Like for example, we know if we want to use logistic regression, again, people who are probably not very familiar with machine learning, there is a separate module for machine learning. You may want to take a look at that, but we will just touch upon the basics here. So machine learning has some algorithms like linear regression, logistic regression, and random forest classification, and so on. So that is what we are talking about here. So those algorithms are available, and if you want to use some of them, you need to import them, and from the scikit-learn library. So scikit-learn is the top level library, which is basically Sklearn, right? And then it has a kind of subparts in it. You need to import those based on what exactly you will be or which algorithm you will be using. So let's take an example as we move, and we will see that whenever we perform some machine learning activity, those of you who are familiar with machine learning will already know this. We split our labeled data into two parts, training and test. Now, there are multiple ways of splitting this data. How do we some people do it like 50-50, some people do it 80-20, which is training is 80 and test is 20, and so on. So it is an individual preference. There are no hard and fast rules. By and large, we have seen that training data set is larger than the test data set. And again, we will probably not go into the details of why do we do this at this point, but that's one of the steps in machine learning. So scikit-learn offers a readily available method to do this, which is train test split. All right, so in this example, let's say we are taking the values x and y are our values. X is the independent variables and y is our dependent variable. Okay, and we are using these two, and then I want to split this into train and test data. So what do? We import the train test split submodule from within scikit-learn, which is sklearn, right? So within that we import train test split, and then you call this train test split method or function or whatever you call it, and pass the data. So x is all the values of the independent variables and y is our labels. So you pass x and y, and then you specify what should be your size of the test data. So only one you need to specify. So if you say test size is 0.25, it is understood that train size will be 0.75. So you're telling what should be the ratio of the split. So technically nothing prevents you from giving whatever you like here. So you can give test as 80 and train as 20, so whichever way, but then the normal practice is you will have the training data set would be larger than the test data set, and typically it would be 80-20, 75-25 or 65-35, something like that, right? So that is the second parameter, and this is just to say that the data has to be randomly split. So it shouldn't be like you take the first 75% and put it in training and then the next 25% and put it in test, so such a thing shouldn't happen. So we first set the state, random state, so that the splitting is done in a very random way. So they are randomly picked up the data and then put it into training and test, and then this results in these four data frames. So x train and x test and y train and y test. Okay, so that is basically the result it will return. Now that the splitting is done, let's see how to implement or execute logistic regression. So in logistic regression, what we try to do is try to develop a model which will classify the data. Logistic regression is an algorithm for supervised learning for performing classification. So logistic regression is for classification, and usually it is binary classification. So binary classification means there are two classes. So either like a yes, no, or for example, customer will buy or will not buy. So that is a binary classification. So that's where we use logistic regression. So let's take a look at the code, how to implement something like that using scikit-learn. So the first thing is to import this logistic regression submodule or subclass, whatever you call it, and then create an instance of that. So our object is classifier. So we are creating an object by the name. This is a name, by the way. You can give any name. In our case, we are saying classifier. We say classifier is equal to logistic regression. So we are creating an instance of the logistic regression variable or class or whatever. Okay. And you can pass a variable or a parameter rather, which is the random state is equal to 0. And once you create the object, which in our case is named classifier, you can then train the object by calling the method fit. So this is important to note. We don't call there is no method like train here, but we call what is known as, there is a method called fit. So you're basically, by calling the fit method, you're training this model. And in order to train the model, you need to pass the training data set. So x underscore train is your independent variables, the set of independent variables, and y underscore train is your dependent variable or the label. So you pass both of these and call the fit function or fit method, which will actually result in the training of this model classifier. Now, this is basically showing what are the possible parameters that can be passed or initiated when we are calling the logistic or the instance of logistic regression. So this is, but you can also look up the help file if you have installed Python. So some of these are very intuitive, but some you may want to take a look at the details of what exactly they do. All right, so moving on. Once we train the model by calling fit, then the next step is to test our model. So this is where we will use the test data. You need to pay attention here. Here I am calling, so there are two things. One is, in order to test our data, we have to actually call what is known as the method known as predict. Right? So here, this is where, so the training is done. Now is the time for inference, isn't it? So we have the model. Now we want to check whether our model is working correctly or not. So what do? You have your test data. Remember, we split it, 25% of our data was stored here, right? We split it into test and training. So that 25% of the data we pass to and call the method predict, so that the model will now predict the values for y. Right, so that's why here we are calling it as y_predict. And if we display here, as I said, this is a logistic regression, which is basically binary classification. So it gives us the results like yes or no in this particular case. And then you can, so this is what the model has predicted or model has classified. Now, but we also know we already have the labels for this. So we need to compare with the existing labels, with the known labels, whether this classification is correct or not. So that is where is the next step, which is basically calculating the accuracy and so on will come into play. Okay, so in this case, the first thing, most important thing to note is we do the prediction using predict, and here we are passing x_test and not train, right? In this case, we did x and y train. So again, one more point to be noted here. In case of training, we will pass both the independent variables and also the dependent variables, because the system has to internally, it has to verify. That is what is the training process. So what it will do, it will take the x values, it will try to come up with the y value and compare with the actual y value, right? So that is what is the training method. So that's why we have to pass both x as well as y. Whereas in case of predict, we don't pass both, we only pass because we are pretending as if this is the actual data. So in actual data, you will not have the labels, isn't it? So we are just passing the independent variables, and the system will then come up with the y values, which we will then, okay, remember, we also know the actual value. So we will compare this with the actual values, and we will find out whether how accurate the model is. So how do we do that? We use what is known as a confusion matrix. So this is also readily available in the Python library. So we import this confusion matrix, and some of you who already know machine learning will find this familiar, but those who are new to machine learning, this confusion matrix is nothing but this matrix, this kind of a matrix, which basically tells how many of them are correctly predicted and how many of them are incorrectly predicted. So some of the characteristics, let's quickly spend some time on this confusion matrix itself. The total numbers out here, these are just the numbers, these are like number of observations. Then the accuracy is considered to be highest when the numbers or the sum of the numbers across the diagonals is maximum, okay, and the numbers outside of the diagonals should be minimum. So which means that if this model was 100% accurate, then the sum of these two, there would have been only numbers in these two along the diagonal, this would have been 0 and this would have been 0. Okay, so that is like 100% accurate model. That is very rare, but just that you are aware. So just to give an idea. Okay, all right. So once you have the confusion matrix, you then try to calculate the accuracy, which is in a percentage. So there are two things that we can do from a confusion matrix, or that we can calculate from a confusion matrix. One is the accuracy and the other is the precision. What is the accuracy? Accuracy is basically a measure of how many of the observations have been correctly predicted. Okay, so let's say this is a little bit more detailed view of the confusion matrix. It looks very similar like as we saw in this case, right? So this is a 2x2 matrix. That's what we are seeing here, 18, 27, 2, 103. So 18, 27, 2, 103. Now, but what are these values? That is what is kind of the labels are shown here in this. So there are altogether 150 observations. So as I said, the sum of all these four, right? 18 plus 27 plus 103 plus 2 is equal to 150. That's the first thing we have to observe. The sum of all these values will be equal to the sum of test observations, number of test observations. We have 150 test observations, because remember we had about 500. We split that into 2575. So that is why we have 150 here and I think 350 in the training data set. Okay, so that we get the numbers correct. So that's the first thing. Now the next thing is, let's take a look at the actual values. This view is the actual view. So there are actually, right, in the actual data we have labels yes and no. So as per the actual data, there are 45 observations tagged as no, and similarly there are 105 observations that are tagged as yes or labeled as yes. Okay, now I know for the first time when you're seeing this it may be a little confusing, but just stay with me. Okay, so this is the actual part of it, and this side tells us the predicted part of it. So our model has predicted, and it has totally predicted 20 of them as no, right? So that is what this is. Totally 20 of them it has predicted as no, and it has predicted 130 of them as yes. Okay, I hope this part is clear. So before we go into the middle part, let us first understand what exactly are these numbers. So actually tagged as no, there are 45 total. Actually tagged as yes, there are 105. And predicted no, there are 20. Predicted as yes, there are 130. This is the result from our model. Okay, this is the result from our model, and this is the actual value which we already know because this is our label data. That's the first thing. Now let us take a look at each of these individually. Okay, now what are the options we have? Once again, okay, so now what is happening here? Let us look at these values. So this 18 says that these are actually tagged as no, and the model has also predicted as no, which means this is what is known as a true positive, right? Or true negative, sorry, right? Which means that our model has predicted it correctly. It is negative because it says no, so, and it has also predicted no, so it is known as what is known as true negative. Okay, now let's come to this side of it. That way we are talking about the diagonal. Remember I said most of the values should be in the diagonal. Okay, so that means these 18 are correctly tagged. They are labeled as no, and our model has predicted as no, so these are correctly tagged, and these are known as true negative. Okay, similarly if we come diagonally down, there are 103 observations which are labeled as yes, actual value is yes, and our model has also predicted as yes, and these are known as true positive values. Positive because of this yes. Okay, right? So what is important is this is true, this is also true. So we have to make sure that the maximum number of values are in the true section. Okay, true positive and true negative. That's the reason I said the sum along the diagonal should be maximum. Now let's say if our model was 100% accurate, this sum, in this case it is only 103 plus 18, which is 121. But if our model was accurate, the sum of these two would have been 150. That means it's a perfect model. Okay, alright. Now what else? Since we covered these two, let's also cover these two. So here this says that 27 of them were actually labeled no, but our model has predicted as yes. That means this is wrong, right? Similarly, these are two of them where the actual value is yes, but our model has predicted as no. That means it's a wrong prediction. So you get the point? So therefore, along the diagonals are the correct values, whereas in other places it is all wrong values or wrong predictions. Okay. Now, how do we calculate accuracy from this information? So the way to calculate accuracy is, so we say, okay, there are total observations are 150, and what are the correctly predicted values? These are the correctly predicted values, which is 18 plus 103. So this will give us our accuracy. So 103 plus 18, which is 121, divided by our total observations, which is 150, is our accuracy, which is 0.8, or we can say it is 80%. Okay. Now there is another concept called precision. So precision is given by the formula true positives divided by the predicted positives, totally predicted positives. Okay, what do we mean by that? Which are the true positives here? Remember, which are the true positives? We just recall, we just talked in the previous slide. Which are the true positives you see here? So this 103 are the true positives, which means that the value is positive, actual value is positive, predicted value is also positive. So that's why it's called a true positive. So 103 divided by, so that is our true positive, 103 divided by totally predicted as yes. Now what is totally predicted as yes? Remember, 130 of them have altogether been predicted as yes. Not that they are correctly predicted, only 103 have been correctly predicted, but 130 of them have been predicted as yes. So precision is basically the ratio of these two. Out of the totally predicted, how many of them are actually true? That ratio. So 103 by 130, which is again about 80%, is the precision. That's how you calculate precision. So this is just a simple formula and a term that you need to remember. So accuracy is, you need to take total of true positive and true negative divided by the total number of observations, whereas precision is true positives divided by the totally predicted positives. Okay, so that is our accuracy and precision. Now what we did, the accuracy calculation was manual, but we can also use some libraries which are already existing and the functions within that library. So Scikit-learn provides one such method. So for example, accuracy underscore score is one such method. So if you use that and pass your test and predicted values, only the y you need to pass, right? The dependent variable values. So if you pass that, it will calculate it for you. So in this case, again, as you can see, it still calculates the same, which is 80%, which we have seen here as well. Okay, so this can be done using the method. Great. So that's pretty much what we have done here. Before we conclude, let me take you into the code and show you how it actually looks. Okay, so this is our code. Let me run it. Okay, one by one. We have already seen most of the steps in the slides, so I will run this in the actual Jupyter Notebook. Some of you, if you are not yet familiar with Jupyter Notebook, again, there are other videos we created on how to install Jupyter Notebook and how to set up Jupyter Notebook and so on. In this tutorial also, there was one slide on how to install Python and Jupyter Notebook. If you have not yet done, please do that, so that then you can actually walk through this code while you're watching this. Okay, so what are we doing here? We are importing the libraries, required libraries. Recall here we have pandas, we have numpy, and for visualization we have matplotlib, and this line is basically reading the CSV file. So we have the CSV file locally on our local drive, and this is where I'm checking the data. So I'm starting with my exploratory analysis, how the data is looking. So it looks good. There are no major missing values or anything like that. So it will display all the columns, and it will show me the first 5 rows when I'm using this head function. And then I want to see a kind of a summary of each of the numerical columns. So that's what I'm doing here. So these are the numerical columns, and it gives a summary like how many observations are there, what is the mean, standard deviation, minimum, maximum, and so on and so forth for each of them. And then you can do some visualization. So this is the visualization for this. Okay, the next step is to view the data visualization, and we will do that using a histogram for a couple of these columns. So in this case, I'm taking a look at the loan amount, and if I create the histogram, it displays the data here in the form of a histogram. One thing that we gather from this, as I mentioned in the slides as well, is how the data is kind of scattered. So while most of the values are in this range 0 to 300 range, there are a few extreme values around the 700 range. So that is one information we get from this histogram. Similarly, for the applicant income, if we draw a histogram, something similar we can see that while most of the values are in this range 0 to 20,000 range, there are a few in the range of 80,000 and probably 65,000 and so on. Okay, so the next step is to perform data wrangling, where we will check if any data is missing and how to fill those missing values and so on. So in this case, we will just check for all the columns, how many data or how many entries are there with missing values. So this is the result. So loan ID has all the columns or all the cells filled. Gender has 13 missing values. Marital status has 3 missing values, and so on and so forth. Loan amount has 21. And this is what we are going to show you how to remove these missing values. So when you have missing values, as I mentioned during the slide, slides, there are a couple of ways of handling that. One is you can completely remove those, or you fill in with some meaningful values. So in this case, we will fill the missing values with the mean value of the loan amount. So let's go ahead and do that. And now if we check here, now loan amount, number of missing values is 0, because what we did was for all these 21 cells where the values were missing, we filled with the mean value of the loan amount. So now there are no more missing values for loan amount. We can do this for other columns as well, but this was just one example, so we have shown it here. Okay, so we will run this for credit history and loan amount term as well. And then if we calculate the mean of pretty much all the numerical columns, that's the method call. So df.mean will give us the mean of all the numerical values. And another thing that we can do is if you want to find out what are the data types of each of these columns, so you can call df.dtypes and get the data types. Of course, it may not be that very useful. Most of the cases is an object, but for example, this one it shows as int 64 and there are float 64 and so on and so forth. Now, in addition to doing the exploratory data analysis, we can do some machine learning activity as well. So in this case, we are going to do logistic regression. So this is the example that I have shown you in the slides as well. This is the actual code for that. All right. So the first step here is to import the libraries. And then the next step is to separate the independent variables and the dependent variables. So X is our independent variable and Y is our dependent variable. So we separate the data into two parts, and this will be our target as well, right? So that's how we separate it. Now we have to split the data into training and test data sets. As I mentioned during the slides, we use the train test split method, and when we call this and pass the independent variables and the dependent variables, and we specify the test size to be 0.25, which means the training size will be 0.75, which is nothing but you split the data into training data set, which is 75%, and test data set which is 25%. Okay, so once you split that, you will have all your independent variables data in xtrain, the training data, which is 75% of it. Similarly, independent variables for test will be in x_test, and dependent variables train will be in y_train, and dependent variable test will be y_test. Once we do this, we have to do a small exercise for scaling. Remember, we had some data which was kind of very scattered. There were some extreme values and so on. So this will take care of that, so that the data is normalized, so that before we pass to our algorithm, the data is normalized so that the performance will be much better. The next step is to create the instance of logistic regression object. So that's what we are doing here. So classifier is our logistic regression instance, right? Classifier is equal to logistic regression, we are saying. So one instance of logistic regression is created, and then we call the training method. The name of the method actually is fit, but what it is doing is it is taking the training data. X is the training data, the independent variables, and Y is the dependent variables. So we are taking both of these and the model gets trained. So the method for calling the training is fit. Okay, so it gives us the output, and then once we are done with the training, we do the testing. And once again, just to recall, in the slides when I was showing you the slides also I mentioned, we don't pass Y here while we are testing. While for training we do pass Y, but right, so for fit we are passing X and Y, but for test we are only passing X, something you need to observe, because Y will be calculated by the model, and we will then compare that with the known value of Y to measure the accuracy. So that's what we will do here, and the method that is called here is predict. So this will basically create or predict the values of Y. Now we have, in this case, a binary classification. So the outputs are yes or no. Y indicates yes and N indicates no. So Y or N is the output. Now how do we measure the accuracy? As we have seen earlier, I described how confusion matrix works and how we can use confusion matrix for calculating the accuracy. That's what we are seeing here. So this is the confusion matrix, and then you want to do the measure the accuracy, you can directly use this method, and we find that it is 80%. So in the slides we have seen, when we calculate manually as well, we get an accuracy of 80%.
Let's begin this lesson by defining the term statistics. Statistics is a mathematical science pertaining to the collection, presentation, analysis, and interpretation of data. It's widely used to understand the complex problems of the real world and simplify them to make well-informed decisions. Several statistical principles, functions, and algorithms can be used to analyze primary data, build a statistical model, and predict the outcomes. An analysis of any situation can be done in two ways: statistical analysis or a non-statistical analysis. Statistical analysis is the science of collecting, exploring, and presenting large amounts of data to identify the patterns and trends. Statistical analysis is also called quantitative analysis. Non-statistical analysis provides generic information and includes text, sound, still images, and moving images. Non-statistical analysis is also called qualitative analysis. Although both forms of analysis provide results, statistical analysis gives more insight and a clearer picture, a feature that makes it vital for businesses. There are two major categories of statistics: descriptive statistics and inferential statistics. Descriptive statistics helps organize data and focuses on the main characteristics of the data. It provides a summary of the data numerically or graphically. Numerical measures such as average, mode, standard deviation or SD, and correlation are used to describe the features of a dataset. Suppose you want to study the height of students in a classroom. In the descriptive statistics, you would record the height of every person in the classroom and then find out the maximum height, minimum height, and average height of the population. Inferential statistics generalizes the larger dataset and applies probability theory to draw a conclusion. It allows you to infer population parameters based on the sample statistics and to model relationships within the data. Modeling allows you to develop mathematical equations which describe the interrelationships between two or more variables. Consider the same example of calculating the height of students in the classroom. In inferential statistics, you would categorize height as tall, medium, and small, and then take only a small sample from the population to study the height of students in the classroom. The field of statistics touches our lives in many ways, from the daily routines in our homes to the business of making the greatest cities run. The effect of statistics are everywhere. There are various statistical terms that one should be aware of while dealing with statistics: population, sample, variable, quantitative variable, qualitative variable, discrete variable, continuous variable. A population is the group from which data is to be collected. A sample is a subset of a population. A variable is a feature that is characteristic of any member of the population differing in quality or quantity from another member. A variable differing in quantity is called a quantitative variable. For example, the weight of a person, number of people in a car. A variable differing in quality is called a qualitative variable or attribute. For example, color, the degree of damage of a car in an accident. A discrete variable is one which no value can be assumed between the two given values. For example, the number of children in a family. A continuous variable is one in which any value can be assumed between the two given values. For example, the time taken for a 100-meter run. Typically, there are four types of statistical measures used to describe the data. They are measures of frequency, measures of central tendency, measures of spread, measures of position. Let's learn each in detail. Frequency of the data indicates the number of times a particular data value occurs in the given dataset. The measures of frequency are number and percentage. Central tendency indicates whether the data values tend to accumulate in the middle of the distribution or toward the end. The measures of central tendency are mean, median, and mode. Spread describes how similar or varied the set of observed values are for a particular variable. The measures of spread are standard deviation, variance, and quartiles. The measure of spread are also called measures of dispersion. Position identifies the exact location of a particular data value in the given data set. The measures of position are percentiles, quartiles, and standard scores. Statistical Analysis System, or SAS, provides a list of procedures to perform descriptive statistics. They are as follows: proc print, proc contents, proc means, proc frequency, proc univariate, proc gchart, proc boxplot, proc gplot. Proc print. It prints all the variables in a SAS dataset. Proc contents. It describes the structure of a dataset. Proc means. It provides data summarization tools to compute descriptive statistics for variables across all observations and within the groups of observations. Proc frequency. It produces one-way to n-way frequency and cross-tabulation tables. Frequencies can also be an output of a SAS dataset. Proc univariate. It goes beyond what proc means does and is useful in conducting some basic statistical analyses and includes high-resolution graphical features. Proc gchart. The gchart procedure produces 6 types of charts: block charts, horizontal, vertical bar charts, pie, donut charts, and star charts. These charts graphically represent the value of a statistic calculated for one or more variables in an input SAS dataset. The charted variables can be either numeric or character. Proc boxplot. The boxplot procedure creates side-by-side box and whisker plots of measurements organized in groups. A box and whisker plot displays the mean, quartiles, and minimum and maximum observations for a group. Proc gplot. Gplot procedure creates two-dimensional graphs, including simple scatter plots, overlay plots in which multiple sets of data points are displayed on one set of axes, plots against a second vertical axis, bubble plots, and logarithmic plots. In this demo, you'll learn how to use descriptive statistics to analyze the mean from the electronic dataset. Let's import the electronic dataset into the SAS console. In the left plane, right-click the electronic.xlsx dataset and click Import Data. The code to import the data generates automatically. Copy the code and paste it in the new window. The proc means procedure is used to analyze the mean of the imported dataset. The keyword data identifies the input dataset. In this demo, the input dataset is electronic. The output obtained is shown on the screen. Note that the number of observations, mean, standard deviation, and maximum and minimum values of the electronic dataset are obtained. This concludes the demo on how to use descriptive statistics to analyze the mean from the electronic dataset. So far, you have learned about descriptive statistics. Let's now learn about inferential statistics. Hypothesis testing is an inferential statistical technique to determine whether there is enough evidence in a data sample to infer that a certain condition holds true for the entire population. To understand the characteristics of the general population, we take a random sample and analyze the properties of the sample. We then test whether or not the identified conclusions correctly represent the population as a whole. The population of hypothesis testing is to choose between two competing hypotheses about the value of a population parameter. For example, one hypothesis might claim that the wages of men and women are equal, while the other might claim that women make more than men. Hypothesis testing is formulated in terms of two hypotheses: null hypothesis, which is referred to as H-null; alternative hypothesis, which is referred to as H1. The null hypothesis is assumed to be true unless there is strong evidence to the contrary. The alternative hypothesis is assumed to be true when the null hypothesis is proven false. Let's understand the null hypothesis and alternative hypothesis using a general example. Null hypothesis attempts to show that no variation exists between variables, and alternative hypothesis is any hypothesis other than the null. For example, say a pharmaceutical company has introduced a medicine in the market for a particular disease, and people have been using it for a considerable period of time, and it's generally considered safe. If the medicine is proved to be safe, then it is referred to as null hypothesis. To reject null hypothesis, we should prove that the medicine is unsafe. If the null hypothesis is rejected, then the alternative hypothesis is used. Before you perform any statistical tests with variables, it's significant to recognize the nature of the variables involved. Based on the nature of the variables, it's classified into 4 types. They are categorical or nominal variables, ordinal variables, interval variables, and ratio variables. Nominal variables are ones which have 2 or more categories, and it's impossible to order the values. Examples of nominal variables include gender and blood group. Ordinal variables have values ordered logically. However, the relative distance between 2 data values is not clear. Examples of ordinal variables include considering the size of a coffee cup, large, medium, and small, and considering the ratings of a product, bad, good, and best. Interval variables are similar to ordinal variables, except that the values are measured in a way where their differences are meaningful. With an interval scale, equal differences between scale values do have equal quantitative meaning. For this reason, an interval scale provides more quantitative information than the ordinal scale. The interval scale does not have a true 0 point. A true 0 point means that a value of 0 on the scale represents 0 quantity of the construct being assessed. Examples of interval variables include the Fahrenheit scale used to measure temperature and distance between 2 compartments in a train. Ratio scales are similar to interval scales in that equal differences between scale values have equal quantitative meaning. However, ratio scales also have a true 0 point, which give them an additional property. For example, the system of inches used with a common ruler is an example of a ratio scale. There is a true 0 point because 0 inches does in fact indicate a complete absence of length. In this demo, you'll learn how to perform the hypothesis testing using SAS. In this example, let's check against the length of certain observations from a random sample. The keyword data identifies the input dataset. The input statement is used to declare the aging variable and cards to read data into SAS. Let's perform a t-test to check the null hypothesis. Let's assume that the null hypothesis to be that the mean days to deliver a product is 6 days. So null hypothesis equals 6. Alpha value is the probability of making an error, which is 5% standard, and hence alpha equals 0.05. The variable statement names the variable to be used in the analysis. The output is shown on the screen. Note that the p-value is greater than the alpha value, which is 0.05. Therefore, we fail to reject the null hypothesis. This concludes the demo on how to perform the hypothesis testing using SAS. Let's now learn about hypothesis testing procedures. There are 2 types of hypothesis testing procedures. They are parametric tests and non-parametric tests. In statistical inference or hypothesis testing, the traditional tests, such as t-test and ANOVA, are called parametric tests. They depend on the specification of a probability distribution except for a set of free parameters. In simple words, you can say that if the population information is known completely by its parameter, then it is called a parametric test. If the population or parameter information is not known, and you are still required to test the hypothesis of the population, then it's called a non-parametric test. Non-parametric tests do not require any strict distributional assumptions. There are various parametric tests. They are as follows: t-test, ANOVA, chi-squared, linear regression. Let's understand them in detail. T-test. A t-test determines if 2 sets of data are significantly different from each other, The t-test is used in the following situations: to test if the mean is significantly different than a hypothesized value, to test if the mean for two independent groups is significantly different, to test if the mean for two dependent or paired groups is significantly different. For example, let's say you have to find out which region spends the highest amount of money on shopping. It's impractical to ask everyone in the different regions about their shopping expenditure. In this case, you can calculate the highest shopping expenditure by collecting sample observations from each region. With the help of the t-test, you can check if the difference between the regions are significant or a statistical fluke. ANOVA. ANOVA is a generalized version of the t-test and used when the mean of the interval dependent variable is different to the categorical independent variable. When we want to check variance between two or more groups, we apply the ANOVA test. For example, let's look at the same example of the t-test example. Now you want to check how much people in various regions spend every month on shopping. In this case, there are four groups, namely East, West, North, and South. With the help of the ANOVA test, you can check if the difference between the regions is significant or a statistical fluke. Chi-square. Chi-square is a statistical test used to compare observed data with data you would expect to obtain according to a specific hypothesis. Let's understand the chi-square test through an example. You have a data set of male shoppers and female shoppers. Let's say you need to assess whether the probability of females purchasing items of $500 or more is significantly different from the probability of males purchasing items of $500 or more. Linear regression. There are two types of linear regression: simple linear regression and multiple linear regression. Simple linear regression is used when one wants to test how well a variable predicts another variable. Multiple linear regression allows one to test how well multiple variables, or independent variables, predict a variable of interest. When using multiple linear regression, we additionally assume the predictor variables are independent. For example, finding a relationship between any two variables, say sales and profit, is called simple linear regression. Finding a relationship between any three variables, say sales, cost, and telemarketing, is called multiple linear regression. Some of the non-parametric tests are Wilcoxon rank sum test and Kruskal-Wallis H-test. Wilcoxon rank sum test. The Wilcoxon signed rank test is a non-parametric statistical hypothesis test used to compare two related samples or matched samples to assess whether or not their population mean ranks differ. In Wilcoxon rank sum test, you can test the null hypothesis on the basis of the ranks of the observations. Kruskal-Wallis H-test. Kruskal-Wallis H-test is a rank-based non-parametric test used to compare independent samples of equal or different sample sizes. In this test, you can test the null hypothesis on the basis of the ranks of the independent samples. The advantages of parametric tests are as follows. Provide information about the population in terms of parameters and confidence intervals. Easier to use in modeling, analyzing, and for describing data with central tendencies and data transformations. Express the relationship between two or more variables. Don't need to convert data into rank order to test. The disadvantages of parametric tests are as follows. Only support normally distributed data. Only applicable on variables, not attributes. Let's now list the advantages and disadvantages of non-parametric tests. The advantages of non-parametric tests are as follows. Simple and easy to understand. Do not involve population parameters and sampling theory. Make fewer assumptions. Provide results similar to parametric procedures. The disadvantages of non-parametric tests are as follows. Not as efficient as parametric tests, difficult to perform operations on large samples manually.
And if you are one of the aspiring data scientists looking for online training and graduating from the best universities, or a professional who really sets to switch careers with data scientist by learning from the experts, then try going a short to Simplilearn's Caltech postgraduate program in data science in collaboration with IBM. The course link is mentioned in the description box below, and you will navigate to the course page where you can find a complete overview of the program being offered.
We'll discuss the three main types of probability distribution, that is normal, binomial, and Poisson distribution. So let's move ahead.
So what is normal distribution? Normal distribution is a continuous probability density that has a probability density function which gives us a symmetrical bell curve. Now data can be distributed or spread out in different ways, but there are many cases where the data tends to be around a central value with no bias to the left or right, which means that it doesn't show any particular spikes towards the left or the right, and it gets close to a normal distribution. Half of the data will fall on the left of the mean and the other half will fall on the right. Now let's take a look at a graph which shows the height distribution in a class. As you can see, the average height is in the middle and the data to the left of the average height represents the short people and the data to the right of it represents the taller people. The y-axis shows us the likelihood of any of these heights occurring. The average height has the most distribution, or it has the most number of cases in the class, and as the height decreases or increases, the number of people who have that height also decreases. This kind of a distribution is called a normal distribution, where the average or the mean is always the highest point and any other point after that or before that is significantly lower. The resulting data gives us a bell curve, and as you can see, there is no abrupt bias or spike in the data anywhere except for the average height. So this kind of a curve is called a bell curve, and it's usually seen in a normal distribution. The reason we call this a normal distribution is because the data is normally distributed, with the average being the highest and all the other data points having a lower likelihood. Now we came across two terms which are associated with normal distribution: continuous probability density and probability density function. What is continuous probability density? Continuous probability density is a probability distribution where the random variable x can take any given value. Because there are infinite values that x could assume, the probability of x taking on any specific value is 0. For example, let's say you have a continuous probability density for men's height. What is the probability that a man will have the exact height of 70 inches? It is impossible to find this out because the probability of one man measuring exactly 70 inches is very low. It is more probable that he will measure around 70.1 inches or maybe 69.97 inches, and it doesn't stop there. The fact is that it's impossible to exactly measure any variable that's on a continuous scale, and because of this it's impossible to figure out the probability of one exact measurement which is occurring in a continuous probability density. Next, we have the probability density function. It's nothing but a function or an expression which is used to define the range of values that a continuous random variable can take. An example of this would be to gauge the risk and reward of a stock. A probability density function is a statistical measure which is used to gauge the likelihood of a discrete value. A discrete variable can be measured exactly, while a continuous variable can have infinite values. However, for both continuous as well as discrete variables, we can define a function which gives us the range of values within which these variables will fall, and that function is known as the probability density function. Now let's take a look at standard deviation. What is standard deviation? Standard deviation is used to measure how the values in your data differ from one another or how spread out your data is. A standard deviation is a statistic that measures the dispersion of a data set relative to its mean. The standard deviation is calculated as the square root of variance by determining each data point's deviation relative to the mean. If the data points are further from the mean, that means that there's a higher deviation within the data set, and then the data is said to be more spread out.
This leads to a higher standard deviation too. Let's take an example of income in rural and urban areas. In rural areas, let's say such as farming areas, the income doesn't differ that much. More or less everyone earns the same. Because of this, our bell curve has a very low standard deviation and it has a very narrow peak. However, in urban areas, the wealth distribution is very uneven. Some people can have very high incomes and can be earning a lot, while other people can have very low incomes. Furthermore, the data distribution between these two income points is going to be more spread out because there are a lot more people living there who work in various fields and who have various incomes. Because of this, our standard deviation is more spread out and our bell curve will also have a wider peak. Now, how can we find the standard deviation? Standard deviation is obtained by subtracting each data value from the mean and finding the squared average of these values. Let's look at how we can do this with the help of an example. These values correspond to the height of various dogs. We can find the mean by finding the average of all these values, which is nothing but adding all the values and dividing it by the total number of values. The mean that we get is 394. This means that the average height of a dog is 394 millimeters. To find the standard deviation, first we need to subtract the height from the mean. This will tell us how far from the mean our data points actually are. Next, we will square up all of these differences and add them up and again divide it by the total number of values that we have. This is called the variance. The variance that we get in this case is 21704. Finally, when we find the square root of this value, we will get the standard deviation. The standard deviation here is 147. The standard deviation will tell us how our data points differ from the average. And it gives us a basic value suggesting how spread out our data is from the very middle or from the mean. So when we plot these values, this value 147 will mean that a curve will have a width of 147 points around the mean. Now, what is the standard normal distribution? The standard normal distribution is a type of normal distribution that has a mean of 0 and a standard deviation of 1. This means that the normal distribution has its center at 0 and it has intervals which increase by 1. All normal distributions, like the standard normal distribution, are unimodal and symmetrically distributed with a bell-shaped curve. However, a normal distribution can take on any value as its mean and standard deviation. In the standard normal distribution, however, the mean and standard deviation are always fixed. When you standardize a normal distribution, the mean becomes 0 and the standard deviation becomes 1. This allows you to easily calculate the probability of certain values occurring in your distribution or to compare data sets with different mean and standard deviations. The curve shows a standard normal distribution. As you can see, again, the data is centered at 0. This does not mean that the data necessarily starts at 0. This means that after standardizing, this point is where our mean will lie. In a standard normal distribution, the standard deviation is 1. So all the data points will increase or decrease in steps of 1. Let's better understand a standard normal distribution with the help of an example. Again, as you can see, the data is centered around 0, which is nothing but the mean. Let's again consider the weights of students in class 8th. The average weight here is around 50 kgs and the data increases and decreases in steps of 5. The data over here in this curve is evenly distributed along these steps. This is what a standard normal distribution will look like. We already know that the mean of our data is 50, and because the data is increasing and decreasing in equal steps, we can just standardize it and take it to mean that the data is increasing and decreasing in steps of 1. This is what a standard normal distribution looks like, and when you have a data which looks like this, you can always standardize it and convert it into a standard normal distribution. Now, standard normal distribution has a couple of properties which makes calculation comparatively easy. The first one is that 68% of the values fall within the first standard deviation, which means that 68% of all data values on this curve will fall between the range of -1 to 1 or the first interval ranging from -1 to 1. The second property is that 95% of the rest of the values are within the second standard deviation or from the second negative point to the second positive point. And finally, 99.7% of the values fall within the third standard deviation or from the third negative point to the third positive point. This makes calculations on standard normal distribution fairly easy. You can compare scores on different distributions with different means and standard deviations. You can normalize scores for statistical decision making using standard normal distribution. You can find the probability of observations in a distribution which fall above or below a given value. And finally, you can find the probability that a mean significantly differs from a population mean. Now let's take a look at z-score. So what is a z-score? A z-score is used to tell us how far from the mean our data point actually is. It is calculated using the mean and standard deviation, so it can be said that the z-score is how many standard deviations below the mean our data is. Basically, by using the z-score, we can get an approximate location of where our data point lies on the graph with regards to the mean. Now the z-score is given by subtracting the data point from the mean and dividing it by standard deviation. This can also be written as x minus mu divided by sigma. Now any normal distribution can be standardized by converting its values into z-scores. The z-score will tell you how many standard deviation from the mean each values lie. While data points are referred to as x in a normal distribution, they are called z or z-scores in the z distribution. A z-score is a standard score that will tell you how many standard deviations away from the mean an individual point will lie. A positive z-score will mean that your x value is greater than the mean, and a negative z-score will mean that your x value is less than the mean. A z-score of 0 will mean that your x value is equal to the mean. And again, to standardize a value from a normal distribution, all we have to do is convert it to a z-score by subtracting the mean from our individual value and dividing it by the standard deviation. Now let's see how we can find the z-score from data points with the help of a solved example. Let's do a case study. In this case study, we'll be taking the summary of daily travel time of a person who's commuting to and from work. All these values are in minutes. And using these values, we have to calculate the mean, the standard deviation, and the z-score. These values are as shown. As we can see, there are 13 values in total. Let's start by finding the mean. The mean is the average, and it can be gotten by adding all of these values and dividing it by the total number of values. This gives us a value of 38.6. The mean tells us the average of all our data points, which means on an average, he travels for 38.6 minutes to reach work. Next, let's subtract the individual values from our mean and calculate the variance and standard deviation. The values on the left give us the values that we get after subtracting it from the mean, and the variance can be calculated by squaring all of these values, adding up all of the squared values, and dividing it by the total number of values. At the end of the day, we get a variance of 140. To calculate the standard deviation, all we have to do is take a square root of the variance, which gives us a value of 11.8. Now, the mean signifies the average of our values, and we already know this. It gives us the average time which is taken to travel. But the standard deviation will tell us the average value of how much our data points differ from the mean. It tells us the deviation within our own data, and it tells us how far away on an average a point is from the mean. Now the value that we get is 11.8, which means that on an average, a single data point is around 11.8 data points away from the mean. Now let's calculate the z-score. The z-score is given by subtracting individual data points from the mean and dividing it by the standard deviation. We know that we have a standard deviation of 11.8 and a mean of 38.6. Using these values, we can calculate the z-scores for individual x values. Now we know that a negative z-score means that our x value is lower than our mean. But what does the number 1.06 mean? This means that the z-score for 26 is 1.06 standard deviations away from the mean. The negative symbol here means that our x value is less than the mean. And by how less? 1.06 times the standard deviation. Now we know that the negative value of a z-score means that our x value is less than our mean. But what does the number 1.06 mean? This means that the z-score is 1.06 times the standard deviation less than the mean. The same thing can be said for the z-score of 33. It is 0.47 times the standard deviation less than the mean. The z-score of 65 is 2.23 times the standard deviation more than the mean. That means it has to be added to the mean. The reason that we know it's more than the mean is because this has a positive value. So this means that using z-scores, we can know where our data points fall relative to other points on the graph. The z-score will tell us how far away from the mean a point is in steps of our standard deviation.
Basics and terminology. The first one is outcome. Whenever we do an experiment like flipping a coin or rolling a dice, we get an outcome. For example, if we flip a coin, we get an outcome of heads or tails. And if we roll a die, we get an outcome of 1, 2, 3, 4, 5 or 6. Random experiment. A random experiment is any well-defined procedure that produces an observable outcome that could not be perfectly predicted in advance. A random experiment must be well defined to eliminate any vagueness or surprise. It must produce a definite observable outcome so that you know what happened after the random experiment is run. Random events. Consider a simple example. Let us say that we toss a coin up in the air. What can happen when it gets back? It will either give a head or a tail. These two are known as outcome, and the occurrence of an outcome is an event. Thus, the event is the outcome of some phenomenon. The last one is sample space. A sample space is a collection or a set of possible outcomes of a random experiment. The sample space is represented using the symbol S. The subset of all possible outcomes of an experiment is called events, and a sample space may contain a number of outcomes that depends on the experiment. If it contains a finite number of outcomes, then it is known as a discrete or finite sample spaces. Now let's discuss what is random variable. A random variable is a numerical description of the outcome of a statistical experiment. A random variable that may assume only a finite number of values is said to be discrete. One that may assume any value in some interval on the real number line is said to be continuous. Let's see an example. Let x be a random variable defined as the sum of numbers when two dice are rolled. X can assume the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Notice there is no 1 here because the sum on the two dice can never be 1. Now that we know the basics, let's move on to binomial distribution. The binomial distribution is used when there are exactly two mutually exclusive outcomes of a trial. These outcomes are appropriately labeled success and failure. The binomial distribution is used to obtain the probability of observing x successes in n number of trials, with the probability of success on a single trial denoted by p. The binomial distribution assumes that p is fixed for all the trials. Here is a real-life example of a binomial distribution. Suppose you purchase a lottery ticket, then either you are going to win the lottery or not. In other words, the outcome will be either success or failure that can be proved through binomial distribution. There are 4 important conditions that needs to be fulfilled for an experiment to be a binomial experiment. The first one is there should be a fixed number of n trials carried out. The outcome of a given trial is only 2, that is either a success or a failure. The probability of success remains constant from trial to trial. It does not change from one trial to another. And the trials are independent. The outcome of a trial is not affected by the outcome of any other trial. To calculate the binomial coefficient, we use the formula which is NCR into p to the power r into 1 minus p, to the power n minus r, where r is the number of success in n number of trials and p is the probability of success. 1 minus p denotes the probability of a failure. Now, let's use this formula to solve an example. Suppose a die is tossed 3 times. What is the probability of no 5 turning up, 1 5 and 3 5s turning up? To calculate the no 5 turning up, here r is equal to 0 and n is equal to 3. Substituting the value in the formula, we have 3c0 into 1 by 6 to the power 0 into 5 by 6 to the power 3, where 1 by 6 is the probability of success and 5 by 6 is the probability of failure. Calculating this equation, we'll get the value to be 0.5787. In a similar manner, to calculate the probability of 1 5 turning up, we'll replace r with 1 and n will be 3. So px1 will be equal to 3c1 into 1 by 6 to the power 1 into 5 by 6 to the power 2, which will come out to be 0.347. And for 3 5 turning up, we'll substitute r equal to 3 and the formula will remain the same and we'll get the value to be 0.0046. Now that we are done with the concepts of binomial probability distribution, here's a problem for you to solve. Post your answers in the comment section and let us know. A Poisson distribution is a probability distribution used in statistics to show how many times an event is likely to happen over a given period of time. To put it another way, it's a count distribution. Poisson distributions are frequently used to comprehend independent event at a constant rate over a given interval of time. The Poisson distribution was developed by French mathematician Simon Denis Poisson in 1837. A Poisson distribution is used in cases where the chances of any individual event being a success is very small. The number of defective pencils per box of a 6,000 pencil, the number of plane crashes in India in 1 year, or the number of printing mistakes in each page of a book. All of these examples can have use of Poisson distribution. The Poisson distribution can be used to calculate how likely it is that something will happen x number of times. A random variable x has a Poisson distribution with parameter lambda, and the formula for that is e to the power minus lambda into lambda to the power x divided by x factorial, where x can be the number of times the event is happening. The value of e is taken as 2.7182. Let's discuss some application of Poisson distribution. If you want to calculate the number of deaths per day or week due to rare disease in a hospital, you can use the Poisson distribution. In a similar manner, the count of bacteria per cc in blood or the number of computers infected with virus per week. The number of mishandled baggage per 1000 passengers can also have an application for Poisson distribution. Let's discuss one example to see how we can calculate the Poisson distribution. Suppose on an average, a cancer kills 5 people each year in India. What is the probability that one person is killed this year? We'll assume all these events are independent random events. So, by the formula, we have x is equal to 1 because we have to calculate the probability of one person that is killed this year. So, p x equal to 1 will be equal to e to the power minus 5 into 5 to the power 1 divided by 1 factorial, which will come out to be 0.033, which will be near to 3.3%. So, the probability that only one person is killed this year due to cancer is 3.3%. Now, we have one question for you. Do try to answer in the comment section. Suppose the trains arrive at a railway station with an average arrival rate of 4 trains per hour. What is the probability exactly 6 trains will arrive in a 2-hour period? And here are our options. Please do let us know your answers in the comment section.
So now let's dive into the definition of the probability distribution function. What is probability distribution function? A function which defines the relationship between a random variable and its probability such that you can find the probability of the variable using the function is called a probability density function. In simple words, probability density is the relationship between an observation and the probability. Some outcomes of a random variable will have low probability density and other outcomes will have a very high probability density. Basically, the probability of a variable x happening or occurring will vary, and it can sometimes take on a lower value or it can take on a way higher value. The overall shape of the probability density is referred to as probability distribution, and the calculation of probabilities for specific outcomes of a random variable is performed by a probability density function, or PDF for short. Now consider a variable x with a PDF of f of x. This is what your probability density function will look like. There might be a point where the probability of x occurring is very high. Hence, your probability distribution function, or f of x, will also be very high. At other points, the distribution or the probability of x happening or occurring is going to be very low. Hence, your f of x is also going to have a very small value. Basically, given the random sample of a variable, we might want to know things like the shape of the probability distribution. This here is something called a normal distribution, where your probability distribution function takes on a bell shape. However, this is not the probability density function that might always occur. There are different probability distribution functions, and all of their graphs look very different from each other. Knowing the probability distribution for a random variable can help you calculate movements of the distribution like the mean and variance, but it can also be useful for other more general considerations like determining whether an observation is unlikely or very unlikely and might be an outlier or an anomaly. Like, consider this graph itself. In this graph, these points over here, which have very less probability distribution, are outliers, which means that the chance of them occurring is very low. And basically, this is not something that you're going to see in your regular scenario for your variable x. Now let's consider 2 points a and b, which are values that our variable x can take. P of a and P of b just represent the probability of a and the probability of b, which can be found out by drawing a straight line and coinciding it with our graphs. The area under the graph over here, which is going to give you your probability of this region occurring, can be written as probability of a less than equal to x, which is the probability that we're searching for here, less than equal to probability of b. What does this mean exactly? This means that this area is always going to be greater than or equal to the probability of A, but less than or equal to the probability of B. This gives us the narrow region of the probability which is present over here. And doing this, we can find the probability of occurrence for any value of x. Suppose you want to find the probability of B happening. For a probability distribution function, the probability of B happening is not simply this point here, but the entire area of the graph which is taking place before this point itself. So if you want to find the probability between these regions, you're going to have to find the entire area and not simply the probability at one point. Now, so far we've been talking about different types of variables, which is discrete random variables and continuous variables. What exactly do these mean? A variable which can only take a value within a certain range is called a discrete random variable. The value is usually within a certain distance of another finite value. An example of this would be the sum of two dices. Basically, values which are well defined are called discrete values, and a variable which has well-defined values will be called a discrete random variable. This variable can only take values which fall within a certain set of values. Let's say you roll a dice. The dice can only give you specific outcomes which range from 1 to 6. This is what you would call a discrete output. On the other hand, a continuous random variable can take on infinite different values within a range of values. For example, the height of a student. The height of a student is not fixed. Even if the height is 1.7 meters, in reality, the height can be 1.77 or 1.765 or 1.789. The exact height is very hard to determine because it's not easy for us to find the precise value of the height of a student. So basically, the height can take on an infinite different range of values. When we're trying to define the values that a continuous random variable can take, we usually say it in the form of a range of values, which means that the value can fall in that range and can take on any value in that range. It's not like a discrete random variable where you can define definitive values. Now let's understand a probability density function with the help of a graph. Consider the graph below, which shows the rainfall distribution in an year in a city. The x-axis has the rainfall in inches, or the amount of rain that we're getting, and the y-axis has the probability density function of getting that amount of rain. The probability of some amount of rainfall is obtained by finding the area of the curve to the left of it. So let's say we have a point 3. If we want to find the probability of 3 inches of rainfall occurring, we would have to find the area of the curve which falls to the left of 3. When we draw a line from 3 which intercepts the graph and further extend it onto the y-axis, we get a value of 0.5. Simply put, this means that the probability of 3 inches of rainfall occurring is going to be lesser than or equal to 0.5. The exact probability can be found out by finding the area of the curve, which falls to the left of 3. How do we find the probability distribution function? The first step is to summarize your density with the help of a histogram. The first step in a density estimation is to create a histogram of the observations in the random sample. Now, what is a histogram? A histogram is a plot which involves first grouping the observation into bins and counting the number of events that fall in each bin. The counts or frequency of observation in each bins are then plotted as a bar graph with the bins on the x-axis and the frequency on the y-axis. The choice of the number of bins is important as it controls the coarseness of the distribution and in turn how well the density of the observation is plotted. It is a good idea to experiment with different bin sizes for a given data sample to get multiple perspectives or views on the same data. At the same time, the number of bins is important as it determines how many bars the histogram will have and their widths. This will change not only the shape of the graph, but also how the graph is read. This will also determine how a density is plotted. Now, let's see how we can summarize our density with histograms using Python. First, let's import all of our necessary modules which we're going to require. We're going to require matplotlib to plot graphs. We're going to need the normal random function so that we can get a normal distribution. We're going to import mean and standard deviation from NumPy to use on our graphs. We're also going to normalize our data, so we're going to import the norm function from SciPy. We finished importing all of our necessary modules. Now let's generate a sample which has a size of 1000 and it's going to be a normal distribution. And we're going to also plot this with the help of a histogram in bins of 10. So as you can see here, you get a normal distribution, which is nothing but a almost bell-shaped curve. And we have 10 bins here, which are centered at 0 and which extend from -3 to 3. How will our graph look if we change the number of bins though? Let's run it and see. So you still have a normal distribution, but it's not as well defined. Because of how less the number of bins are, you lose a majority of the data which will contribute to your normal distribution. It doesn't look like a proper normal distribution, but it looks more like a discrete data at this point. Now let's take a look at the next step of finding our probability distribution function. The next step is called parametric density estimation. What exactly is parametric density estimation? The probability density function is of many types. The shape of your histogram will help you determine what type of a function it is. We can also calculate the parameters associated with the function to get our density. Now, different probability distribution functions will have different graphs which will have different shapes and which will also have different parameters like mean, standard deviation, etc. associated with them. Using these parameters, we can find important points of our data. Hence, it's very important for us to recognize what type of a distribution it is. Common distributions will occur again and again in different and sometimes unexpected domains. Getting familiar with common probability distributions will help you identify a distribution from a histogram, and once identified, you can attempt to estimate the density of the random variable with a chosen probability distribution. This can be achieved by estimating the parameters of the distribution from a random sample of data. Now, an example of this would be a normal distribution which has two main parameters, the mean and standard deviation. Given these two parameters, we will now know the probability distribution function. These parameters can be estimated from data by calculating the sample mean and sample standard deviation. This entire process is known as parametric density estimation, and it includes identifying your probability distribution function and getting the parameters which are associated with it. Now, once we have estimated the density, we can check if it's a good fit. This can be done in three different ways. One is plotting the density of the function and comparing the shape to the histogram. The next is sampling the density function and comparing the generated sample to the real sample. And the last one is using a statistical test to confirm if the data fits the distribution. Now over here, as you can see, all we've done is taken our data and plotted the density function on top of a histogram, and we've compared the shape. So the density function that we're actually considering here is a normal distribution. And from this graph, we can see that it's almost an exact fit to our histogram. Now let's see how we can perform parametric density estimation using Python. To begin with, let's generate a random sample of 1000 observations from a normal distribution with a mean of 50, which is determined by the LOC parameter, and a standard deviation of 5, which is determined by the scale parameter. Now, just to show you what the distribution looks like, we're going to plot it in the form of a histogram. So this is what the histogram looks like. But this is just to give you a basic idea of our data and what it looks like once plotted. But let's assume that we don't know the probability distribution and we don't know what it looks like as a histogram, and we don't know that it's normal. So now, if we just assume that it's normal, we can calculate the parameters of the distribution, specifically the mean and the standard deviation. We would not expect the mean and standard deviation to be 50 and 5 exactly, given the small sample size and the noise in the sampling data. So because of this noise and the small sample size, we have a mean of almost 50 and a standard deviation of a little more than 5. Now let's define the distribution as normal. So now using this, we've defined a normal distribution. We've used the norm method of the SciPy library, and we're doing this with the mean and the standard deviation that we've obtained from our samples. So up until now, we're just assuming that it's a normal distribution, and because of that, the parameters that we've calculated is the mean and standard deviation. And using the calculated mean and standard deviation, we've gotten a normal distribution. And up until now, again, keep in mind, we do not know for certain that it is a normal distribution. So far, all we have is this data. So the next thing that we're going to do is fit the distribution with these parameters and then sample the probabilities for a distribution for a range of values in our domain, which in this case is 30 and 70. So all we're doing is we're calculating probabilities for a range of outcomes, and in this case we've taken 30 and 70 as our domain. So these are the probability distribution values for the normal distribution that we've defined over here, and this is basically gonna give you the outline of your normal distribution. These are the points at which your normal distribution will be plotted. Now what we're basically going to do is we're going to plot our histograms using the samples that we've already generated. along with the values and probabilities of the normal function that we defined over here. So as you can see, it's almost a complete fit. The normal distribution that we have here is made using the mean and the standard deviation of our actual samples. The reason we took mean and standard deviation was because we assumed it was a normal distribution, and the parameters associated with the normal distribution are mean and standard deviation. Using the mean and standard deviation, we got the normal distribution. We calculated probabilities for this normal distribution using a random domain of 30 and 70. And we plotted the probabilities and the values on top of our histogram to see if the normal distribution was a fit to our histogram. If it was not a fit, you would have to go and do the same procedure with other common probability density functions until you found a function which was a proper fit to your histogram. Now let's move on to the final step, which is used in the calculation of our PDF. This final step is called non-parametric density estimation, and it's only used when the shape of a histogram doesn't match a common probability density function, or it cannot be made to fit one. In this case, we will calculate the density using all samples in our data using certain algorithms. This is only done when a data sample does not resemble a common probability distribution, or it cannot be easily made to fit the distribution. And this is often the case when the data has two peaks. This is also called a bimodal distribution, or it has many peaks, which is also called a multimodal distribution. In this case, the parametric density estimation will not be feasible, and alternative methods can be used that do not use a common distribution. Instead, you will use an algorithm which is used to approximate the probability distribution of the data without a predefined distribution, which is also referred to as a non-parametric method because we're not using any predefined parameters. The distribution will still have parameters, but these are not controllable in the same way as a simple probability distribution. For example, a non-parametric method might estimate the density using all observations in a random sample, in effect making all observations in the sample parameters. Now consider this graph which has two peaks. This is not a normal distribution or any other sort of distribution that we are familiar with. So for this, we're not going to use a parametric estimation method, but we're just going to calculate the parameters for every single sample point in this. Perhaps the most common non-parametric approach for estimating the probability density function of a continuous random variable is called kernel smoothing or kernel density estimation, or KDE for short. Kernel density estimation is a non-parametric method for using a dataset to estimate probabilities for new points. It uses a mathematical function and smoothing probabilities, so the sum of the resultant probabilities is always 1. Now in this case, a kernel is a mathematical function that returns a probability for a given value of a random variable. The kernel effectively smooths or interpolates the probabilities across a range of outcomes for a random variable such that the sum of probabilities always equals 1, a requirement of well-behaved probabilities. You also have a parameter called the smoothing parameter, which controls the scope or the window of observations from the data samples that contributes to estimating the probability for a given sample. As such, the kernel density estimation is sometimes referred to as your Pearson-Rosenblatt window. Now at the end, you also have a basis function, which is a function which is chosen to control the contribution of samples in the data set towards estimating the probability of a new point. This is only done to make sure that you're not learning from a lot of noise and that you're not using a lot of the outliers. Again, let's see how we can perform non-parametric density estimation with the help of Python. So first we'll start by importing all the necessary modules along with the kernel density estimation, which can be imported from Sklearn. Now let's create a bimodal distribution by combining two different samples, sample 1 and sample 2. Sample 1 has 300 examples with a mean of 20 and a standard deviation of 5, while sample 2 has 700 examples with a mean of 40 and a standard deviation of 5. We're then going to use HStack to merge both of them together to get a final sample. The means that we've chosen, which is 20 and 40, are chosen close together to ensure that the distributions overlap in the combined sample. So this is what our distribution is. Let's just plot it so you get a basic idea of what our graph looks like. So this is what our graph looks like. Now we already know that none of the various different probability distribution functions fit these graphs. So now we're going to perform non-parametric estimations. So to perform non-parametric estimations, we're going to use the scikit-learn machine learning library, which provides the kernel density class that implements kernel density estimation. First, the class is constructed with the desired bandwidth or window size of 2. And your basis function, which in this case is a Gaussian function. It's a good idea to at least test different configurations to your data, and in this case we're only going to try a bandwidth of 2 and a Gaussian kernel, but usually there are multiple different kernels that you can that you can play around with, and you can also tweak your bandwidth to exactly fit the distribution that you have. Now let's run this. So now we've gotten our kernel density estimation. Now we can evaluate how well the density estimates matches our data by calculating probabilities for a range of observations and comparing shapes to the histogram, just like we did for the parametric case before. So again, we're gonna just calculate different probabilities using the kernel density function, and we're just gonna plot it on top of our histogram to see how well the kernel density function is estimating for our data. So these are the probabilities that we've gotten finally with the kernel density estimation, and now we're going to plot it on top of our histograms. So as you can see, it's almost a complete fit. It's just left out some of these outlier values, which again are ranging very high, but overall we have a pretty good fit. The only problem is it's not very smooth, and you can again try tweaking the bandwidth to different values. So let's just in this case try tweaking it to 3 and see how well it runs. Okay, so now we've gotten new probabilities, and let's run it on top of our bandwidth. So again, using a bandwidth of 3, you can see that we're fitting our data even better, and we're again ignoring a lot of the outliers which are out there. So this is going to give us a better estimation.
And if you are one of the aspiring data scientists looking for online training and graduating from the best universities, or a professional who really sets to switch careers with data scientist by learning from the experts, then try going a short to Simplilearn Caltech postgraduate program in data science in collaboration with IBM. The course link is mentioned in the description box below, and you will navigate to the course page where you can find a complete overview of the program being offered.
So what is a population? In statistics, population is the entire set of items from which data is drawn for a statistical study. It can be a group of individuals, a set of items, etc. It constitutes the data pool for a study. In general, a population is the entire group that you want to draw conclusions about. Usually, when we talk about population, you think about the people living in an area at a time. But in research, a population doesn't always refer to people. It can mean a group containing elements of anything you want to study, such as objects, events, organizations, countries, species, organisms, etc. For example, all undergraduate students in the Netherlands, or say you would like to know whether there's an association between job performance and the amount of home working hours per week in the specific case of Belgian data scientists. In this case, the population may be Belgian data scientists. However, if the scope of the study is more narrow, then the population will be more specific and include only workers who meet that certain criteria. The point is that the population should only include people to whom the results will apply. Since in this case and many others, it is impossible to observe the entire statistical population due to time constraints, constraints on geographical accessibility, and constraints on the researcher's resources, a researcher would instead absorb the statistical sample from the population in order to attempt to learn something about the population as a whole. This brings us to the topic, what is a sample? A sample represents the group of interest from the population which we will use to represent our data. The sample is an unbiased set of the population which best represents the whole data. A sample consists of some observations drawn from the population. So, a part or a subset of the population. The sample is the group of elements who actually participated in the study. The size of the sample is always less than the total size of the population. Typically, the population is very large, making a census or a complete enumeration of all values in the population impractical or impossible. The sample represents a subset of manageable size. Samples are collected and statistics are calculated from the sample so that one can make inferences or extrapolations from the sample to the population. This process of collecting information from a sample is referred to as sampling. Say you are testing the effects of a new fertilizer on crop yield. All the crop fields represent your population, whereas the 10 crop fields you tested correspond to your sample. Now let's look at the differences between population and samples with the help of some examples. The first example would be that all students in a class would constitute the population of that class. A sample would be only the top 10 students within the same class. The sample is a small subset of the population in this case. Advertisements for IT jobs in India would mean the complete search results that pops up when you search IT jobs in India. A sample of that would be the top 50 advertisements for the same jobs. Another example is all countries of the world. This represents a population of all the countries. A sample would be countries with published data on birth rates and GDP since 2000s. Next, let's look at how to collect data from a population. Data from a population is collected when your research question needs a large amount of data or information about every member of the population is available. Populations are used when your research question requires or when you have access to data from every member of the population. Usually, it's only straightforward to collect data from a whole population when it is small, accessible, and cooperative. Population data is used when the data pool is small and cooperative to giving all of the required data. For larger populations, we can use sampling to represent part of the population it is hard to collect data from. For example, a high school administrator wants to analyze the final exam scores of all graduating seniors to see if there is a trend. Since they are only interested in applying the findings to the graduating seniors in this high school, they can use the whole population dataset. For larger and more dispersed populations, it is often difficult or impossible to collect data from every individual. For example, every 10 years, the federal US government aims to count every person living in the country using the US Census. This data is used to distribute funding across the nation. However, historically, marginalized and low-income groups have been difficult to contact, locate, and encourage participation from. Because of non-responses, the population count is incomplete and biased towards some groups, which results in disproportionate fundings across the country. In cases like this, sampling can be used to make more precise inferences about the population. And for that, we can collect data from a sample. How do we go about collecting data from a sample? Samples are used when the population is large in size, scattered, or it's generally hard to collect data on individual instances within it. We can use a small sample of the population to make overall hypotheses. When your population is too large in size, geographically dispersed, or difficult to contact, it is necessary to use a sample. With statistical analysis, you can use sample data to make estimates or test hypotheses about population data. For example, you want to study political attitudes in young people. Your population is the 3,000 undergrads in the Netherlands. Because this is not practical to collect data from all of them, you use a sample of 300 undergraduate volunteers from 3 Dutch universities. This is the group who will complete your online study. Ideally, a sample should be randomly selected and representative of the population. Using probability sampling methods such as simple random sampling or stratified sampling reduces the risk of sampling bias and enhances both internal and external validity.
Let's start by defining what is mean squared error. Mean squared error measures the amount of error in a statistical model. It calculates the average squared difference between the observed and predicted values. In regression line, the mean squared error represents the average squared residual. As you can see in the graph, as the data points fall closer to the regression line, the model has a less error, decreasing the mean squared error. A model with less error produces more precise predictions. Now let's jump to our Excel workbook and discuss it with an example. Here we have a small table with the actual and predicted values. We'll start by finding the error between the actual and predicted value, which will be the difference between the actual minus predicted values. So here 10 minus 7 will become 3, 16 minus 14 will become 2, 13 minus 17 will become minus 4, 19 minus 20 becomes minus 1, and 7 minus 4 becomes 3. Now just calculate the total of the errors. While calculating the total, we'll treat this negative value as a positive value. So here the total of the errors will become 3 plus 2 5 plus 4 9 1 10 and 13. Then we'll calculate the square of the errors. So here 3 square will become 9, 2 square will become 4, 4 square will become 16, 1 square will become 1, and 3 square again is 9. And we'll do the total of the square errors. So this will become 9 plus 4 13, 13 plus 1 14, 14 plus 16 30 and 39. To find the MSE, that is the mean squared error, we'll divide the total of the square error values with the total number of records. So here MSE will be equal to (39) divided by, and we have a total number of records, that is 5, which will be 7.8. Let's name this as model A. Now for the comparison purpose, we'll create another model, that is model B. We'll have all the columns here. And we'll keep the actual values here same. We'll just change the predicted values. So let's take some random values. We'll keep this as 13, we'll take this as 20, we'll take this as 12, 18 and 3. Now to calculate the error, we'll subtract the predicted values from the actual values. So 10 minus 13 will become minus 3, 16 minus 20 will become minus 4, this will become 1, this will be 1 and this will be 4. Now to calculate the square error, we'll just square the error values. So this will be 9, this will be 16, this will be 1, this will be 1 and this will be 16. The total of all the square values will come out to be 43. Now to calculate the MSE, again we'll divide the total square values with the total number of records. So here this will be equal to 43 divided by 5, which will come out to be 8.6. If you observe here, the total of the errors in both model A and model B is same, that is 13. So, which model to prefer? Since the mean squared error of model A is lesser than model B, we'll prefer model A because we are okay with a model that has small errors, but in model B, there are some significantly large errors. Suppose in this case 16 minus 20, that is minus 4, minus 3, and this here 4. So we do not want a model where the large errors specifically, are more frequent. We can have a model with the small errors that will be okay. So we'll prefer model A over model B.
Most of you must be using Snapchat to apply filters on your photos. But do you know how Snapchat recognizes your photo on the screen and puts filters on it? Even if there are multiple faces on the photo, it applies filters in the appropriate position. Snapchat actually does this using a technique called facial recognition, which in turn uses machine learning. The machine learning algorithm detects the features on your face, like the nose, the eyes, and it knows where exactly your eyes are, where exactly your nose is, and accordingly it applies the filters. We will take a few more examples as we move along and try to understand how machine learning algorithms can be applied to solve some of our real-life problems. So what will you learn from this video? We will talk about some real-world applications of machine learning. We will also see and understand what exactly is machine learning and how it works. We will also see the process involved in machine learning, the types of machine learning algorithms, and we will also see a few hands-on, including some code, Python code, of the following algorithms: linear regression, logistic regression, decision tree and random forest, and k-nearest neighbors. Okay, so let's get started. So let's consider some of the real-world applications of machine learning. It's no longer just a buzzword. Machine learning is being used in a variety of industries to solve a variety of problems. Facial recognition is one of them. It's becoming very popular these days for security, for police, for solving crime. A lot of areas facial recognition is being used. Voice recognition is another area. It's becoming very common these days. Some of you must be using Siri. That's an example of machine learning and voice recognition. Healthcare industry is another big area where machine learning is adopted in a very big way. As you all may be aware, diagnostics needs analysis of images, let's say like X-ray or MRI, and increasingly because of the shortage of doctors, machine learning and artificial intelligence is being used to help and support doctors in analyzing these images and identifying the advent of any diseases. Weather forecast is another area. And in fact, Netflix has actually come up with a very interesting use case. You all must be aware of the House of Cards show on Netflix. So they did an analysis on their customer behavior. They got data of their 30 million customers, information about where they pause, where they fast forward a video, and they used this information. They provided this information to their playwrights and told them that this is what we want. This is what our audience is looking for. These are the areas that interest them, and these are the areas where they get bored. And the playwrights wrote the scripts accordingly. This is really, really interesting, and it actually brings a new era. So, what is machine learning? Machine learning is a science of making computers learn and act like humans. So here, when we say computers, very often what comes to our mind is writing a piece of code or program and telling the computer step by step what to do. But in machine learning, we don't do that. The system learns on its own. We just provide past data, historical data, what we call as labeled data, and the system learns. During the process, what is known as training process, we tell the system whether the outcomes are right or wrong, and that feedback is taken by the system and it corrects itself, and that's how it learns till it gives the correct output for most of the cases. Obviously, it won't be 100% correct, but the aim is to get as accurate as possible. So let's take you through step-by-step process of machine learning. The first step in machine learning is data gathering. Machine learning needs a lot of past data, especially we will see a little later, supervised learning. We will see what that is in a little while, but that's the most common form of learning. So the first step there is data gathering. You need to have sufficient historical data. Then the second step is pre-processing of this data so that this can be used for the machine learning process. The raw data cannot be used directly, so it needs to be pre-processed before it is fed into the machine learning system. The next step is to choose a model. So what kind of algorithm and what kind of model within that algorithm are we going to use? And then we need to train this model. So before training the model, it's just like a blank model, and after training it becomes a trained model. And once we train the model, we need to also test it to make sure it is predicting correctly. It's working fine with minimum errors. And subsequently it will be deployed, and once again it may have to be tuned from time to time or fine-tuned from time to time to improve the accuracy and so on and so forth. After training the model, we have to test the model. And during testing, we may find out that the accuracy is not good enough, so we may have to tune the model, we may change some parameters and run through this process once again, perform the training once again. So it can be an iterative process. And once the model is ready, then we deploy it to do the predictions. What are the different types of machine learning algorithms? Machine learning algorithms are broadly classified into three types: the supervised learning, the unsupervised learning, and reinforcement learning. Supervised learning in turn consists of techniques like regression and classification, and unsupervised learning we use techniques like association and clustering. And reinforcement learning is a recently developed technique, and it is very popular in gaming. Some of you must have heard about AlphaGo. So this was developed using reinforcement learning. Primary difference between supervised learning and unsupervised learning. Supervised learning is used when we have historical data and we have labeled data, which means that we know how the data is classified. So we know the classes if we are doing classification, or we know the values when we are doing regression. So if we have historical data with these values, which are known as labels, then we use supervised learning. In case of unsupervised learning, we do not have past labeled data, historical labeled data. So we use techniques like association and clustering to maybe form clusters or new classes maybe, and then we move from there. In case of reinforcement learning, the system learns pretty much from scratch. There is an agent and there is an environment. The agent is given a certain target and it is rewarded when it is moving towards that target, and it is penalized if it is moving in a direction which is not achieving that target. So it's more like a carrot and stick model. So what is the difference between these three types of algorithms? Supervised algorithms or supervised learning algorithms are used when you have a specific target value that you would like to predict. The target could be categorical, having two or more possible outcomes or classes, if you will. That is what is classification. Or the target could be a value which can be measured. And that's where we use regression. Like for example, weather forecasting, you want to find the temperature. Whereas in classification, you want to find out whether this is a fraud or not a fraud, or if it is email spam, whether it is spam or not spam. So that is a classification example. So if you know, or this is known as labeled information, if you have the labeled information, then you use supervised learning. In case of unsupervised learning, we have input data, but we don't have the labels or what the output is supposed to be. So that is when we use unsupervised learning techniques like clustering and association, and we try to analyze the data. In case of reinforcement learning, it allows the agent to automatically determine the ideal behavior within a specific context, and it has to do this to maximize the performance. Like for example, playing a game. So the agent is told that you need to score the maximum score possible without losing lives. So that is a target that is given to the agent, and it is allowed to learn from scratch, play the game itself multiple times, and slowly it will learn the behavior which will increase the score and keep the lives to the maximum. That's an example reinforcement learning. So we will discuss about some of the most popular algorithms in machine learning. A few of them are listed here. This is by no means an exhaustive list. There are really a lot of algorithms available out there, but these are some of the most common ones. What are these algorithms? Linear regression, logistic regression, decision tree, random forest, and k-nearest neighbors. So let's look at each of these in detail. Linear regression. A little history about linear regression. Sir Francis Galton is credited with the discovery of the linear regression model. So what he did was he started studying the heights of father and son to predict the son's height or the child's height even before he or she is born. So he collected enough data of the heights of father and the respective sons. He plotted this data on the x and y axis, and he drew a line in such a way that the distance of these points from the line was the least, which is now what we call it as mean square error. So at that time this term was probably not there, but that's what he did. And then he was able to use this line to predict the height of the child which was yet to be born based on the height of the father. So that was the very beginning or very initial phase of linear regression algorithm. So that was a little bit of history, but what is linear regression? So linear regression is a way of modeling a linear model, creating a linear model to find the relationship between one or more independent variables denoted by x and a dependent variable which is also known as the target and denoted as y. A few examples are shown here. Let's say we are going to plot the sales of ice cream and the temperature. So temperature on the x-axis and the sales on the y-axis, and this is how the data would look. And if we draw a line in such a way that the distance of each of these points from this line is minimum, that is known as the regression line or the best fit line. So regression is all about finding this line, and it is called linear regression because it is a straight line, linear, and the equation doesn't have any non-linear component, which means we do not have x to the power of 2 or 3 or any of this. So this is simple linear regression, and simple linear regression is when there is only one independent variable. So there is only one x. So that is simple linear regression. So let's see how this is actually done. So linear regression is all about finding the best fit line, and the way it is done is in a recursive manner. So first a random line is drawn and the distance is calculated from this line of all the points, as you can see in this example, and that distance is known as the error. And to ensure that there are no negative values, this is squared. So we actually take the square of the distance of the point from the line and add it up, and we make sure that at the end this sum, which is known as the sum of squared errors, is the minimum. So as you can see, this is where we start, and then we keep changing the line in such a way and calculate the distance once again, the sum of the squares once again, and here again you will see that this is probably not minimum, and we keep changing this until we get a line where this value is minimum. So here we find that the sum of the squares of the distance, which is also the sum of squared errors, capital D, denoted by capital D, is minimum. So now we found the best fit regression line. So this is a recursive process, it's an iterative process, and this is what behind the scenes, this is what happens when we try to do linear regression. Now we'll take an example of a linear regression, and we will actually demonstrate this using Python, and we will be using Jupyter Notebook for this. In case you're familiar with Jupyter Notebook, I think that would be very helpful, and if you need the data set, please put a comment under this video so that we can provide you with the data set. Before we go there, just let's try to understand what this example is all about. Let's say there is a new joinee joining the company, and we want to determine what should be the pay or the salary for this new joinee. And for that, we already have the labeled data, which is the details of our employees based on their years of experience and their salaries. And for the new joinee, we have the experience, and we need to determine what should be the salary. So let's take a look at the demo. So before we go into the Jupyter Notebook, let's quickly review the code, what the code is doing. The first section is about importing the libraries. Some of you who are familiar with Python will already be knowing this. We don't have to go into details. And then we import the data set, and then we visualize the data just to get a quick idea about how the data is looking. And then we split the data into training and test data sets. This is a common procedure in machine learning process, any machine learning process. And the overall training and test process we do with two different data sets. So that's what we're doing here. And then we build or train our model, the linear regression model. And then we do the testing and we find out what is the errors and visualize our results. And this is how the test results look, and this is how the training result looks. All right. And then we calculate the residuals. Residuals are nothing but the errors. There are a couple of ways of measuring the accuracy. The root mean square error is the most common one, RMSE. And in this case, we got root mean square error of 58, which is pretty good. And that's our best fit. All right. So now let's go into Jupyter Notebook and take a look at by running it live. Okay, so this is our code for the linear regression demo, and this is how the Jupyter Notebook looks and this code in the Jupyter Notebook looks. I will walk you through the code pretty much line by line, and let's see how this works, the linear regression. So the first part is pretty much a standard template in pretty much all our code we will see. This is importing the required libraries. So NumPy is a library, Matplotlib is a library, pandas, and so on. So these libraries are required. Each of these libraries have a different purpose. So some of them are required for manipulating your data, some for plotting, as the name suggests, Matplotlib, and so on and so forth. Okay, so let's go ahead and import all these libraries, and then we will import our data. So in this example, what we are trying to do, the use case in this particular example is we have some historical value of salary data, and now we want to build a model so that we can predict the salary for new employee, a person who is joining new, and we will use the characteristics that were available to us or the features that were available to us, and we will try to predict what will be this salary of this new person. Okay, so that's the kind of the use case. So let's go ahead and load the data, and let me introduce a cell and see how the data looks. So salary underscore data. So we have basically two features, right? So it's pretty much like a simple linear regression we are trying to do. So we have years of experience and salary. And in this case, what we are trying to do is this is our predictor. So years of experience is our predictor, and we are trying to predict what the salary would be. So once again, so X is what is known as the predictor and Y is the target. So number of years of experience we are taking as input, and we will try to find what will be the salary of this person based on that. Okay, so that's what we are going to do. So I have shown what is how the overall how the data that has been imported looks. Now let's take a quick look at these extracted values or extracted columns as well. So let me put in X here and see how it looks. So there's basically one column, and same way if we put Y here, we will see what exactly, I'm sorry, this has to be in small lowercase. So this is the salary information. Okay, so this is how our data is, and then we can do a little bit of plotting of the data to play around a little bit, because we imported the data. Typically we want to do some exploratory analysis, how they compare with each other and so on and so forth, how they are correlated. So let's draw a quick plot, a bar plot, and see how the years of experience are being seen here, right? So this is how the bar plot looks. Similarly, let's do one more, which is basically more like this is horizontal bar plot. Okay, so how many people and with what experience and so on and so forth. So what this shows is the count, how many records are there with a given experience and things like that. Okay, so this is another way of visualizing the data, and this is a third view And this is one more view, and then we can do a quick heat map. So there's only one, or actually there are only two variables, so there's not a lot of plotting that we can do, or not a lot of visualization that we can do, since there are only two variables. But nevertheless, whatever is possible, we can do a quick to get a quick idea about how the data is looking and how the variables are related to each other. Is there a correlation and things like that? All right, so once we are done with that, this is the most important part of our demo here, which is basically this is the beginning of our training process. So the first thing before we start the model building and model training process is to split the data into training and test data sets. Okay, now whenever we do any machine learning exercise, especially supervised learning, we never use the entire labeled data for training purpose. The reason being, then we will not be able to correctly evaluate how well the training has happened. Okay, so what we do is we split the data, we take a portion of the data, we call that as the training data set, and we set aside some portion of the data, we call that as the test data set. We use the training data set to actually perform the training, to train our model, and once that is done, we use the test data set to check how well the model has been trained, how accurately it is able to predict. Okay, now the reason is with our test data set also, since that is also labeled, we allow the model to predict the values and we compare it with the labeled information to see whether it has predicted correctly or not. Okay, so that is the reason in all machine learning activities, whenever we perform machine learning, especially training of a model, we split this data into training and test data set, and that's what we are going to do here. Now there is no need to write any separate code for that. There is a readily available function for that, train_test_split. So that's what we are going to use here. It takes the data set, x and y is the data set, and in addition it takes a parameter which tells how the data has to be split. So for example, here it says test size is equal to 1/3. That means it is 33%, right? 33.33%. So 1/3 of the data you want to set aside for test. Now there are no hard and fast rules as to what should be the split of test and training data set. It is a matter of individual preferences. Some people would like to have 50-50, some people would prefer 80-20, and so on and so forth. So it is completely up to the individuals to decide on that. So in this particular case, what we are doing is we are setting aside 1/3 of the data set for testing purpose and 2/3 of the data set for training purpose. Okay, so that's exactly what we are doing here. Now the next step is to create an instance of linear regression. So linear regression model is readily available. So we create an instance of the linear regression model and give it a name like LR, and then we call the fit method of the linear regression model. Now this fit method is common across all the algorithms. So any algorithm you use, if you want to start the training process, you call the fit method. Okay, and then we pass the training data set. Now training data set, we send the predictor, as I was saying, or the independent variable, and also the dependent variable. We pass both of them. Okay, and the system will basically learn based on this. So now the training has happened, training is completed, and now we need to see whether it is predicting correctly or not. We need to test it, right? So for testing, we have another method called predict. Again, this is common across all algorithms. Any algorithm you use, you will have this predict method for testing your model, okay, or for actually predicting the values, whether during testing or when you actually deploy the model. Okay, now here predict will take only one parameter, which is the independent variables, right? The reason being, the dependent variable is what it will predict, right? So y_test we don't have to pass, whereas here y_train we passed for training purpose, but y_test we do not pass because that is what the model will predict, so we don't have to pass that. And then the model will predict, and that is what we call it as y_pred, but we will use y_test to compare with what the model has predicted, and thereby we can determine how accurate the model is. Okay, so let me go ahead and run this code. So it has done with the testing or with the prediction of the values. So these are the predicted values, and now we can visualize, we can generate some plots to visualize this information. So let's plot this training set results information and see how it looks. So what we are doing here is basically we have the training data set plotted, the salary versus the years of experience, right? This is the training data, the dots basically. And then this line is what our model has. So this is the best fit. So linear regression, what is linear regression process? We find a equation of a line which is the best fit. So our model, this is the equation, or this is the line that our model has kind of come up with, saying that this is the best fit model. Okay, so as you can see, intuitively it feels okay because it is passing through pretty much the middle of our data set. Okay, so this is for the training part. Now we do the same for our test as well and see how it is doing, or how it looks. Here also it looks pretty good because the line passes pretty much in the middle of the overall data set. That's what we are trying to do here. All right, and then how do we measure the accuracy? So these residuals are nothing but the errors. The term residuals is nothing but the errors we have seen in the slides as well. So we calculate the accuracy of our model by calculating the various residuals. We have like mean square error, then we have the mean absolute error, and then we have the root mean square error. They are very closely related. This is nothing but the error and the actual value, right? So for example, let me explain with this particular line. So what our model says is, if the value of the years of experience, right? So let me take this point maybe. If the value of the years of experience is 4, then the salary will be, according to our data, that salary probably should be, what is this, maybe around 58,000, right? And there are of course 3 data points pretty much around this 4 years experience. One may be around 58, or in fact 2 of them are around 58, and there is one more which is probably 60. Okay, now these are the 3 data points, whereas our model predicts that if the years of experience is 4, then the salary should be 60,000, let's say. Okay, let's assume this goes to 60,000, which means that one of the data points is very accurately predicted by our model, but there are 2 of them which are off. So there is an error for these 2 values. And what is that error? The error is nothing but the distance of this point from this line. Right, the distance of this point of each of these data points from the line is the error. Okay, so that's basically for each of the values it will correct, so it will calculate rather, and instead of taking the absolute value, we kind of take a square of that. So because the value can be positive or negative, so in order to avoid a cancellation, so there are some positive values, there are some negative values, and they get cancelled out, what we do is we take a square of that. So that is basically what is the root mean square, or the mean square error. And then if we take a square root of that, it becomes root mean square error, right? So this was explained probably in the slides as well. So that is what we will calculate here, and we print it. Okay, and these values, the root mean square error, the mean squared error, and the mean absolute error, the lower these values are, the better. So the accuracy is higher if these values are lower. So in a way it is inversely proportional. Okay, so that's the way we measure the accuracy of our linear regression model. Alright, so that brings us to the end of this demo, and we will continue with the other demos. Alright, now that we have seen linear regression, let's take a look at our next machine learning algorithm, which is logistic regression. Now, what's interesting about this algorithm is that while it says regression, the name has regression in it, but keep in mind this is not used for regression, but this algorithm is used for classification. Now, many people get confused by this name, so you need to be aware of it. Linear regression is used to solve regression problems where we are trying to predict a value, whereas logistic regression is used to solve a classification problem. So we are trying to find, for example, whether a person will repay the loan or not, or whether we want to find whether this image is of a cat or a dog. So this is a classification problem. Okay, so just that you should be aware of the name. So in this slide, we are talking about whether a person, credit card user or credit card holder, will default on the payment. So we can create a profile. We have historical data and of people, their income and their credit card balance, and we have examples of people who have defaulted and people who have not defaulted, and based on that we let the system learn to predict this particular value, whether the person will default on the payment or not. Now, how does the logistic regression work? If we try to draw a straight line to determine the probability, so we are trying to predict whether this person will default or not. Okay, so if we draw a straight line, then the predicted value can exceed 0 and 1, which is not a good idea. So the probability is calculated between 0 and 1 using what is known as a sigmoid curve. So it is not a straight line, but we use a different formula, a different mechanism to find the probability and find the value between 0 and 1. And the formula for that is P is equal to 1 by 1 plus e to the power of minus z. Here, z is actually the linear equation that we used in figure 1, which is m1x plus c0. So this is fed to P and the value is calculated between 0 and 1. And we will see actually mathematically, you will see here that if z is negative and much higher, a very high value, the equation will be 1 by 1 plus 0, which is equal to 1. So we will see here that if the value of z is positive and it is some high number, then the value of P can at the most be equal to 1, because this portion here is 1 by a very high number, let's say infinity. So 1 by infinity is 0, so this whole thing becomes 1 by 1, so that is equal to 1. P is equal to 1. So that is where the maximum value it can achieve is 1. Similarly, if the value is negative, if the z value is negative or negative and very high value, then this will become very high and therefore the denominator will become infinity. So 1 by infinity is 0 and therefore P is equal to 0. So that's the way the sigmoid function works. This is how the graph looks, and there has to be a threshold value, which is like in this case 0.5. So if the value is greater than 0.5, we consider the output as 1, whereas if the value is less than 0.5, we consider the value as 0. Because remember, let me go back, in this case it doesn't exactly give us a 1 or a 0. Okay, so we need to keep that in mind. It doesn't give us exactly a 1 or a 0. It will give a value between 0 and 1, irrespective of what the value of z is. It will give us a value between 0 and 1. It's like the probability between 0 and 1. Now we have to have a threshold, and then based on what the value is, if the value is greater than 0.5, then we say okay, this probability is 1, and if the value is less than 0.5, the probability is 0. So we decide that based on the cutoff or a threshold value. So for example, if we continue on that, if a person having a balance of maybe this is 1750, then the probability that he will repay the loan is 0.2, which is less than 0.5, the threshold value which we have set. That means the probability is 0, which means the person will not repay. Whereas if the balance is somewhere in the range of 2250 maybe, which is this red dot, then the sigmoid function calculates the probability of default as 0.8, which means the output is 1, which means the person will default on payment. Okay, so that is how the logistic regression works. So in this case, it says that okay, this person will default, so it is classified as a defaulter, in this case the second one, and in the first case it is a non-defaulter. So these are the two different classes of these two different cases. So let's move on and see how logistic regression is implemented. So this is another example of logistic regression. Can we predict whether a person is going to buy an SUV based on their age and their estimated salary? So these are our two inputs, and based on that, can we predict whether this person will buy an SUV or not? So this is a logistic regression problem, and we are going to demonstrate this using Python code and in Jupyter Notebook. And before going into Jupyter Notebook, let's take a look at how we go about solving this problem and how the code looks. So this is the implementation of logistic regression. This is the code, the Python code. I'll just take you very briefly at a high level what each parts are. So first section, of course, is importing the libraries, and then we import the data set. And within this data set, we just take, for performing or for training our model, we only take the independent variables into one, create one vector, and then we extract the labels separately. And then we visualize our data. This is how the data looks. And then we split the data into training and test set like we did in linear regression. And we do some feature scaling as well, which improves the performance of our model. And then we train and test the model. So these are the test results, and we visualize the test results. So this is the visualization of the trained results. They look pretty good. The classification, they are reasonably accurately classified, the red dots and the green dots. And there are a few, of course, miscalculations or misclassifications, but by and large it looks pretty good. And this is the visualization of the test results. Again, looks pretty good. And then we evaluate our model, and this is what we'll be doing in the code as well. And for this we use what is known as confusion matrix. Now let's try to understand what this confusion matrix is. Now, I know the name itself is confusing, but actually it is very simple. Now once we predict these values and compare with the actual values, we can create or represent the results in the form of a matrix. So we have altogether 134 observations, and if we put it in a tabular form, the predicted values and the actual values. First of all, in order to identify whether our model is more accurate or less accurate, the criteria is that the values along the diagonal should be maximum. So for example, this is 79 and this is 38. The sum of these should be maximum. So what do we mean by that? That means that if we have a perfect model, then this sum will be equal to 134 and the values here will be 0. So that is an ideal perfect logistic regression model. That is of course very rare, but that is the aim. The sum of these numbers or the maximum numbers should be in the diagonal, and in the other cells there should be as less as possible. Okay, so here we see in this case that it is 79 plus 38, and so that is equal to 117. So 117 of them have been correctly predicted, which gives us an accuracy of 87%. So out of 134, 117 have been correctly predicted, and the 6 plus 11, 17 of them have been incorrectly. So this is 6 plus 11, 17 of them have been misclassified, so which is about 0.13%. So we have an accuracy of 87%. Okay, so I hope the way we calculate or the way we find accuracy from confusion matrix, I hope it is clear. By the way, once again, a quick reminder, if you need this data set to perform this on your own, please put a comment and under this video and we will send you the data set. Alright, so let's go and check in Python notebook how exactly this is done. Alright, so this is the demo of logistic regression. And here what we are doing is we have taken an example of a data set and a scenario where we will predict whether a person is going to buy an SUV or not. And we will use logistic regression for this. And the parameters we will take are, for example, the person's age, his salary, and a few other parameters. We will see very quickly what those are. Okay, so the first step, we import the required libraries. So that's what we are doing in this particular cell, like for example, NumPy, Matplotlib, Pandas. So for performing any preparation of the data before we actually launch into the learning process. And then we load the data. So let me just introduce one more cell and see how the data looks. So why don't we do that here? And if I say data set, and then if I run this, this is how our data looks. So these are the parameters or the features as we call it in machine learning language. We have gender, age, and estimated salary. User ID is also there, but it's not really a feature. It will probably not contribute, so we will not be using this. We will primarily be using these three columns, and in technical terms these columns are known as predictors, and then we have the labeled value. This is known as our target, and this is the labeled value, so it has 0 or 1. So we are basically performing a binary classification, 0 or 1, whether the person will purchase or not purchase. 0 means he will not purchase, 1 means he will purchase. Okay, and the other way of also looking at it is from a mathematical perspective. These are our independent variables. Gender, age, and estimated salary are our independent variables, and purchased is our dependent variables. So in our equation, like y is equal to something something m1x plus m2x and so on, this is our y. Okay, all right, so now let's move forward. What we will do next is to extract this or separate out the independent variables and the dependent variables. How do we do that? So we load them into X, capital X and Y, and what we are doing here is we are taking the second and the third column. We are taking these three, right? So gender, age, and estimated salary. So that is what we are taking here, 2 up to 3, and then Y is basically the last column, which is the fourth column. So let's go ahead and extract that, and once again, why don't we take a look at how the data is looking. So let me just print X. So we are basically taking 2 and 3. So what is 2 and 3? 2 and 3 is our age and our estimated salary. Yeah, that's right. So these are the only two independent variables, and our dependent variable is obviously the last one, whether the person will buy or not. Okay, so we have the data loaded. Now that we have the data in Python, let's take a quick look at how the data looks. So in terms of visualization, let's visualize the data and perform a little bit of what is known as exploratory analysis, right? So as a data scientist, whenever you get new data, you just play around and see how the data is looking before you actually launch into the actual training or the modeling part of it. So let's run a small heat map and see how the data looks. So we have just passed the entire data set here, and this is how the heat map looks, how they are related, how the various features are related to each other. And this is a scale here. Very dark means basically there is pretty much no correlation. This is in a way to measure the correlation as well, and light means there is a very high correlation. So as you can see, a value or a feature will have very high correlation of 1 to itself. So the user ID, and this is user ID, it has a very high correlation to itself. Similarly, purchased it has. So the diagonal will be very high, so that is really not relevant. But then the other values is what we have to see. For example, there is a correlation of 0.6 in this area, which is basically if you take age and purchased, right? Whether the person has purchased and the age. So that's a quick look at exploring the data. So that's all we are doing here. Here's where the actual the crux of this code is. So from here onwards, what we do is the first step before we start the training process is split our data into train and test. Training data set and test data set. So whenever we perform any machine learning activity, we have, let's say, our labeled data. We never pass the entire data to the model, because when we are measuring the accuracy, whether the model is performing well or not, we will not be able to do that if we use up the entire data for training purpose. So we split the data into what is known as a training data set. We train the model with the training data set, and then this test data set, which is kept separately, which the model has not yet seen, we use that to check whether it is able to perform the predictions correctly or not. Okay, that will give us a higher accuracy or a better estimate of how the model is doing. Alright, so this is a very common practice in machine learning. So whenever we perform training of the model, we split the data into training and test. Now, how do we do this? We don't have to write any special code. There is already a method available, which is train_test_split. And we just call this method. Only thing is, it takes these parameters, and we have to specify especially this parameter, which tells the method how the data should be split. Now, when we are splitting the data into training and test, there are no hard and fast rules how we split this data. Some people prefer 50-50, some people prefer 80-20, and so on and so forth. So that is flexible, and it could be to some extent individual preferences. So in our case, we are splitting this data into 75-25, which means 75% of the data we will use for training, 25% we'll use for test. So that is what we are specifying here as a parameter. We say test underscore size is equal to 0.25. That means put or keep 25% of the data, set aside 25% of the data as test data, and therefore the remaining 75% will be used for training. Alright, so let's move on. I execute this. Then we perform what is known as feature scaling. So what is feature scaling? Usually what happens is the values that we have in the data, sometimes they can be some numbers will be very large, some will be very small. So there is a huge variation. So in order to, if we have that and if we use that as it is, the accuracy of our model may come down. So we have to somehow normalize these values. So that is what scaling does, feature scaling does. And again, we don't have to write any special code for this. There is a standard method available or standard class available called standard scaler. So we just create an instance of that and pass our data for scaling purpose. Okay, so let's go ahead and do that now. So this is all what we have done is more like a data preparation. So we chose what are the parameters, what features we want. We did the feature scaling and we split the data. Now everything is ready. Next is to start the actual training process. So this is the most crucial part of the code. So here, as we said, we will use the logistic regression model. So we have to create an instance of regression model. So I call that as classifier. You can give any name. And we just do some kind of a initialization, random value initialization. So we call this as random state, or we assign it as random state is equal to 0. And we have an instance of the logistic regression model, and we use that model, the fit method. So any algorithm that we have, when we want to perform the training, we have to use the fit method. Okay, we call the fit method. Now let's say instead of logistic regression, we are using k nearest neighbors algorithm. You will have k nearest neighbor dot fit, or linear regression dot fit, right? So that is the way it works. And we pass the training data set. The x is the independent variables and y are the labels. So we pass both of them for the training purpose. So once the training is done, we get the results of, or the model is trained. Okay, the model is trained. Now the next step is to test the model, how well the model is performing. This is where we use the test data set. We pass the test data set, and here there is another method that we have to use that is known as a predict method. So again, this is a predict method is common across all algorithms that we have. So any algorithm we have to call the predict method for performing the test, or even when we deploy it, when new data comes in, we are trying to predict for new data set, we always use predict. Okay, so fit is only for training. Okay, then predict is used for testing and for the actual performance of the prediction. Now, one thing we need to observe here again is we only pass the x part of it and not the y part of it. So this can always, sometimes this can lead to confusion. When we are calling fit, we are passing x and y. When we are calling predict, we are only calling x. The reason is the y part is what the model will predict. So you don't have to pass the y part. Right? So y is what the model will predict for us. So you don't pass. Here we had to pass it because the model has to learn from the existing values. So that's why we had to pass label as well. But when we are testing it, the model will calculate this, and that's the reason we do not pass the y value. Okay, so now when we run predict, it will calculate those values or find those values, and it will put it in y_pred, and that is what is being displayed here. And as you can see, the values can be either a 0 or 1, which means the person will buy the SUV, which is 1, which is a value of 1, or 0 means the person will not buy the SUV. Okay. Now, one more thing we need to remember is while we have not passed the y values or the labels to the system, but we have these labels available with us, right? Y underscore test is available with us. That is what we have to use to find out how accurate the system is. So it has given us the results. Now we will compare these results, which the system has predicted, with the actual values that we have, which is available in y underscore test. So we will see how well, how that is done, how the accuracy is calculated in a little bit. Okay, now that the training is completed, we can go ahead and do some visualization of the training results. So let me execute this code and take a look in a form of a plot. So this is how the classification is done. So these are like the class, this is like the class boundary. The green color belongs to the class 1 and the red color belongs to class 0. And these dots indicate it has been misclassified. So some of them have been misclassified. So that's what we are seeing, some red dots in the green area and some green dots in the red area, right? Whereas if you, probably it's not very clear, but you can see here that there are also red dots in the red area and the green dots in the green area. So those are the data points which are correctly predicted, and these in the opposite locations are the ones that have been misclassified rather. Same for test as well. So test data set also, if we visualize, we plot, we will see something similar. But this also gives at a high level whether is that a major in a major way, are there major misclassifications or there are only few here and there. It gives a little bit of an idea about the accuracy as well, but then that is not sufficient for us, right? So we have to quantify this accuracy. So how do we do that? We do this using what is known as confusion matrix. So it's a readily available method or a class which is there, and it takes two parameters, which is the, you remember I told you we will be using y test. So this is where we will be using y underscore test, which is our labeled value or labeled data set, and this is what is predicted by our model. Okay, y underscore pred is predicted, are the predictions. Here, these are the values out here we saw. This is y underscore pred. Okay, so we pass these two parameters and we create a matrix, and this matrix is known as confusion matrix. Now, what is the significance of this? First thing is that the total number of values here is equal to the number of data sets in your test data. Okay, so let's go ahead and in the next cell, let me just add up these values. So 65 plus 3 plus 8 plus 24. So how many are there? There are 100 in number. So there are totally 100 observations in your test data set. That is the first point. Then the second point is the number in the diagonals, right? The total value in the diagonals, if that is a high, that indicates a higher accuracy. The higher that number is, the total in the diagonal, the higher the accuracy. Okay, and if we have quite a few numbers in non-diagonal locations, that means the accuracy is not very high. So here looks like the accuracy is pretty good. Now we can actually quantify the accuracy by using these numbers. So what we do is the sum along the diagonal we have to take and divide that by the total observation. So 65 plus 24 is what we have along the diagonal, and we have 100 observations. So 89 by 100 is our percentage. So we got about 90% accuracy for this particular model. Okay, so that brings us to the end of this demo, and we will move on to the next demo. Alright, so the next algorithm is decision tree and random forest. They are being taken together because they are very closely related. So what is a decision tree? Decision tree is another algorithm, and unlike logistic regression, which is only used for binary classification, decision tree can be used for classification as well as regression, even though it is more popular for classification. And it can be used to classify multiple classes as well, not just binary classification. So how does decision tree work? One of the good things about decision trees is that it is easy to represent and show how exactly it works, and therefore it is very easy to understand as well. Now let's take an example. Let's say a person receives a job offer and he needs to decide whether to accept the job offer or not. So we will use decision tree to come to the decision to accept or not to accept. So this is how, first of all, a decision tree looks. It is actually an inverted tree. So the root is at the top. Okay, so and that is known as the root node. The node where the tree starts is known as the root node, and then we have some inner nodes or decision nodes, and we have the nodes where we have a decision, either positive or negative. These are known as leaf nodes or terminal nodes. Okay, so we have the root node and we have leaf nodes or terminal nodes. There can be multiple of them, and in between we have decision nodes or internal nodes. There are different terms used, so need not be hung up by the exact terminology. Now let's say we have to use this decision tree to find out whether this person will accept the job offer or not. So first thing he considers is the salary. Is the salary greater than 60,000? If no, it's a clear decision, the offer will be rejected. So we reach a decision, therefore this is a leaf node. Now, if the salary is greater than 60,000, it is not a clear-cut decision because there are probably other factors based on which the decision needs to be made. For example, what is the commute time? If the commute time is greater than 1 hour, then the offer is rejected. Okay, so even though the salary is greater than 60,000, so this is again a leaf node. If the commute time is less than 1 hour, still it is not a confirmed decision because there are still a few other factors. For example, performance incentives. Are there sufficient performance incentives as a part of this offer? If no, then again the offer is rejected, and this is another leaf node. If yes, if there are sufficient performance incentives, then the offer is accepted. So this is another leaf node. By the way, keep in mind that these are all the leaf nodes. This is a leaf node, this is a leaf node, this is a leaf node, this is a leaf node. And they of course belong to different categories. In this case, it is still a binary classification. So this belongs to one class, which is accept offer, and these leaf nodes belong to a different class, which is reject offer. So let's take an example and see how we can solve this problem using decision tree. Let's say we have to implement a classification algorithm for kyphosis patient, and the problem is a bunch of kids have undergone a kyphosis surgery, and we need to predict whether kyphosis is present in them or not. And how can we do this using decision tree algorithm? So this is how the classification tree for kyphosis looks. So it starts with if the age is greater than 8.5. So this is how the decision tree looks. So the first criteria is the vertebra, the number on which the surgery has been performed. If it is greater than 8.5, then we need to perform further analysis and look at other criteria. If it is less than 8.5, it is clear that kyphosis is present. And if it is greater than 8.5, then we check whether the vertebra operated upon is greater than 14.5 or not. If it is greater than 14.5, then kyphosis is absent. If not, then the next criteria is the age. If the person's age is less than 55 years, then kyphosis is absent. But if it is greater than 55 years, then a further analysis is required to see if the person's age is greater than 111 years, which is, of course, almost impossible, but yes. So if no, then there is no kyphosis. Then we check if the age is greater than 111 years, which means the person is between 55 and 111 years. If the person is between 55 and 111 years, that is this path, that means kyphosis is present, otherwise it is absent. So this is very easy to understand decision tree. And now what we are going to do is we are going to implement this in Python in our Jupyter notebook, and we have a data set that is available for this. And once again, if anyone wants this data set, please put a comment under this video and we will be more than happy to share the data set with you. Before we go into the Jupyter notebook, let's take a look at what the code is doing. What are the various sections of the code? So first one, of course, is loading the libraries as usual. Then we import the data and then extract the independent variables and then separate the labels, which is the dependent variable, and then we visualize the data. This is how it looks. And then we, as usual, split the data into training and test data sets and then perform the training of the decision tree. And then we test that model with our test data. And then, since this is a classification problem, we evaluate this model using the confusion matrix. Remember, we talked about this in the previous example as well. So this is the confusion matrix for this particular problem. And here you can see that 16 plus 3, 19 of them have been correctly predicted out of 25, which gives us a 64% accuracy. And this 4 plus 2, 6 of them have been misclassified. Just to recap once again, how do we determine from the confusion matrix whether this is accurate or not? The numbers in this diagonal should be maximum. So here we see that out of 25, n is equal to 25, which is the total number of observations. Out of 25, in this case, in this diagonal, we have 16 plus 3, 19 of the values are here. So that's the reason we feel there is good accuracy, which is 64%. They have been correctly classified. 64% of the observations have been correctly classified by this model, whereas 24% have been misclassified, which consists of this 4 plus this 2. So that's how we use the confusion matrix to determine the accuracy of our decision tree model. So let's go into the Jupyter notebook and take a look and run the code and see how it looks. So this is our Python notebook for decision tree, and I will take you through the code, not line by line of course, but we will see the blocks. As always, the first block is to import the required libraries like pandas and numpy and so on, and then we import the data. For this we are using kyphosis.csv file, and then we extract the independent variables and then the dependent variable. Dependent variable is the target, which is our classification, and also we call it as the label data, whether this person individual has kyphosis or not. And then we will run a little bit of initial exploratory analysis on the data. So as a data scientist, whenever you get new data, you do that. So we plot age against whether the person has kyphosis or not, and then we plot the various parameters against each other. So for example, this is like age versus the number. And by the way, the data, how does the data look? Let's take a look at the data. This has primarily 3 columns, one attribute against the other. So for example, this is age versus the number, then number versus the start, and so on and so forth. So this is just to get a quick idea about the overall, how the overall data looks. So we can do a few more visualizations, like with respect to the age and the count, the number of vertebrae that have been operated upon, and the red color indicates kyphosis is absent and the blue color indicates kyphosis is present. So this is another view, and so on. So we can basically do as much of exploratory analysis we can, and then we start training our model. So this is where we split the data into training and test data set, like in all other machine learning examples earlier also, and we can visualize the data or just take a quick look at how the data looks. Just the first 4 or 5 entries here. If we do the head, that's what the head function does. And similarly Y as well, we can take a look at how the target is looking, and then we can get into the training of the decision tree. So we train our model with the training data set using this fit method, and then we test whether the model is working fine or not using the test data set, and this is the result of our test data, and then we evaluate the model. And for evaluating, we use the confusion matrix. So just let's take a quick look at the confusion matrix and see what is the accuracy. So we get about 16, right? As I mentioned, the diagonal values is what matters. So we have 16 of them correctly identified out of 25. So that gives us about 62, I think 70% accuracy. So that is using decision tree. Now, instead of decision tree, let's check what happens if we use random forest. So we use, let's say our forest consists of 100 trees, and we do the same. We train our model, and then with the test data set, we try to test the model. And here we see that we get 19 of them out of 25 correct. So that is a much better accuracy. So this is about 76%. So 19 out of 25 is 76% accuracy. And we saw by using the decision tree, we got only 64%. That is 16 by 25 was only 64%. So this is a quick demo of implementation of decision tree. So once we evaluate the model, the next thing we can do is what happens if we want to improve the performance. So that's where random forest comes into play. So instead of using a decision tree, what happens if we use a random forest? And what is a random forest? It's very similar to decision tree. Only thing is that instead of using one tree, we use a number of trees. That's why it's called a forest. So we use multiple trees and we take like a average or a voting of all the trees for each observation, and we finally calculate or we finally classify each observation based on that. So in this case, it helps in improving the accuracy. So as we have seen here, if we take a decision tree, the accuracy now comes to 76%, right? In the previous case, it was only 64%. Using just the decision tree, now when we use random forest, the performance has improved to a good extent and it has become 76%. So random forest usually helps in increasing the accuracy when we are using decision trees as our algorithm. Okay, the last algorithm is the k nearest neighbors algorithm. This is again a classification algorithm and it is actually very simple and straightforward, very easy to understand as well. In this case, let's say we have historical data of heights and weights and we also have the labels. So if the height and weight is in this range, these are cats, and if the heights and weights are in this range, these are dogs. So this is one class and this is another class. And now if we get a new point or new data set and we find that for this particular animal, the height and weight, if we plot it, is here. So how do we determine whether it belongs to the cat class or the dog class? That is where the k here comes into play. So when we are using this algorithm, we need to specify what should be the value of k. So let's say we determine that the value of k is 3. So what we will do is we will find out the nearest three objects to this data point that we have. So let's go to the next slide here. Okay, and we define k as 3. So what happens? We find the nearest 3 objects to this data point, and then we find out what is the maximum number of items, which class the maximum number of items belong to. So in this case, there are 2 cats and there is 1 dog. Therefore, we determine that this new data point belongs to the cat class. Now what happens if we say k is equal to 7? In that case, these are the 7 data points which are nearest to this new data point. And now you see that instead of cats, dogs are more. So which means that now the point or this data or this new creature belongs to the class dog. So while this is a slight drawback, but by trial and error, we should be able to find out the right value of k. And once we use that, that's how we train the model. Now let's use k nearest neighbors and take an example to solve one of our previous problems that we did using logistic regression. Whether a person is going to buy an SUV or not based on the age and estimated salary. So before we go into Jupyter Notebook, let's again take a quick look at the code. So what are the various sections in the code? As always, we import the libraries, we load the data set, we visualize the data, we split the data into training and test data set, we do some feature scaling, and then we train our model, and then we test our model. We visualize the training set results, and then we visualize our test results, and both of these seem to be looking pretty good. And then we evaluate our model using the confusion matrix. So remember, whenever we use a classification algorithm, the way to evaluate our model, to find out the accuracy of our model, is the confusion matrix. We have seen in logistic regression, we have seen in decision tree, and now in KNN as well. So in this case, once again, the total number of observations is 100, and we see that along the diagonal, which is the number we need to consider, there are 93 values, which means we achieve 93% accuracy, and a few of them, that is only 7 of them, are misclassified. So this is a pretty good accuracy compared to our previous example. So let's go and check how this looks in Jupyter Notebook. So this is my Python notebook for k nearest neighbor implementation, and I will quickly walk you through this code. The first block is, as usual, we are importing the various libraries like NumPy, Pandas, and Matplotlib. and then we load the data set, and we split the data into training and test data sets, and then we do feature scaling, and then we start training our model. And here we are specifying k as 5. Okay, and now the data set is trained. Now we go and test it with our test data set. Then we evaluate the model, and here we get that as you can see in the diagonal, there are 73 entries. So total is 73, which means out of total of 80, 73 have been classified correctly, which is about 90% accuracy we are getting, and 7 of them have been misclassified. We can now visualize the training results. So these are the zeros and these are the ones. This is the training set. So there are a few, as you can see, misclassifications. The green ones in the red area and the red ones in the green area are the misclassified values. And same way we can visualize the results of the test data set as well. And here again we see there are a little bit of misclassification. And that brings us to the end of this Python notebook demo for KNN classification.
And if you are one of the aspiring data scientists looking for online training and graduating from the best universities, or a professional who highly sets to switch careers with data scientist by learning from the experts, then try giving a shot to Simplilearn's Caltech postgraduate program in data science in collaboration with IBM. The course link is mentioned in the description box below, and you will navigate to the course page where you can find a complete overview of the program being offered.
As you know, in today's world, data is becoming increasingly important. Entire professions are dedicated to studying, understanding, and manipulating the data. Hence, it is important to know about the different types of data and their associated properties. So, in this session, we will discuss how to calculate the distortion in the normal curve using Skewness and Kurtosis. So, let's get started. We will start this tutorial by understanding symmetrical distribution. Then we'll move on to discuss skewed distribution and Pearson's coefficient of skewness. Finally, we will discuss kurtosis. So, let's get started. Symmetrical distribution. A distribution is said to be a symmetrical distribution when it is equally distributed on both the sides of the mean value. The distribution shape can either be a bell-shaped or U-shaped. In symmetrical distribution, the values of mean, median, and mode are all equal, as you can see in the graph. Skewed distribution. Skewness is used to measure the level of asymmetry in our graph. It is a measure of asymmetry that occurs when our data deviates from the norm. Sometimes the normal distribution tends to be tilt more on one side. This is because the probability of data being more or less than the mean is higher and hence makes the distribution asymmetrical. This also means that the data is not equally distributed. The skewness can be of two types: positively skewed and negatively skewed. Let's discuss them separately. Negatively skewed. In a negatively skewed distribution, the data points are more concentrated towards the right hand side of the distribution, as you can see in the graph. This makes the mean, median, and mode bend towards the right. Hence, these values are always negative. In this distribution, mode is greater than median and median is greater than mean. Now let's move on to positively skewed distribution. In a distribution that is positively skewed, the values are more concentrated towards the right side, and the left tail is spread out, as you can see in the graph. Hence, the statistical results are bent towards the left hand side. Therefore, the mean, median, and mode are always positive. In this distribution, mean is greater than median and median is greater than mode. The measure of skewness always helps us to know to what degree and in which direction, positive or negative, the frequency distribution has a departure from symmetry. Positive or negative skewness can be detected graphically depending on whether the right tail or the left tail is longer, but we don't get the idea of the magnitude. In a negatively skewed symmetry, the values are always negative. This is the symmetrical distribution, and in a positively skewed, the values are always positive. Now let's discuss Pearson's coefficient of skewness. The median is always the middle value, and the mean and the mode are the extremes. So we can derive the formula to capture the horizontal distance between the mean and the mode using the Pearson's first coefficient. So the formula to calculate the Pearson's coefficient is mean minus mode divided by the standard deviation. The division by the standard deviation will help you to scale down the difference between the mode and the mean. This will scale down their values in the range of -3 to +3. In case where the mode is indeterminate, we can calculate the Pearson's coefficient by mean minus 3 median minus 2 mean divided by the standard deviation. If the value of coefficient is between -0.5 and 0.5, the distribution of the value is always symmetrical. If the value of coefficient is 0, then the distribution is symmetrical. If the value of coefficient is positive, then the distribution is positively skewed, and if the coefficient is negative, then the distribution will be negatively skewed. Now that we have discussed this symmetrical and skewed distribution, let's move on to understand what is kurtosis. Kurtosis is used to find the presence of outliers in our data. It gives us the total degree of outliers present. The data can be heavily tailed, and the peak can be flatter, almost like punching the distribution or squishing it. While skewness signifies the extent of the symmetry, kurtosis measures the degree of peakness of a frequency distribution. When the peak of the curve becomes relatively high, then the curve is called leptokurtic. And when the curve is flat, it is called platokurtic. When the curve is similar to the normal curve, it is called mesokurtic. The expected value of kurtosis is 3. This is observed in a symmetrical distribution. A kurtosis greater than 3 will indicate positive kurtosis. Further, a kurtosis less than 3 will mean a negative kurtosis. The range of value for a negative kurtosis is from -2 to infinity. The greater the value of kurtosis, the higher is the peak, as you can see from the graph.
Today we're going to be looking at random forest, one of the many powerful tools in the machine learning library. Before we dive into the topic, let's start by looking at a few of the uses for random forest. Currently today it's used in remote sensing. For example, they're used in the ETM devices. If you're a space buff, that's the enhanced thematic mapper they use on satellites, which see far outside the human spectrum for looking at land masses. And they acquire images of the Earth's surface. The accuracy is higher and training time is less than many other machine learning tools out there. Also, object detection, multi-class object detection is done using random forest algorithms. A good example is traffic, where you're trying to sort out the different cars, buses, and things. And it provides a better detection in complicated environments. They're very complicated up there. And then we have another example, Connect. And let's take a little closer look at Connect. Connect, they use a random forest as part of the game console. And what it does is it tracks the body movements and it recreates it in the game. And let's see what that looks like. We have a user who performs a step. In this case, it looks like Elvis Presley going there. That is then recorded so that Connect registers the movement. And then it marks the user based on accuracy. And it looks like we have Prince going on this one. From Elvis Presley to Prince. It's great. So it marks the user based on the accuracy. If we look at that a little closer, we have a training set to identify body parts. Where are the hands? Where are the feet? What's going on with the body? That then goes into a random forest classifier that learns from it. Once we've trained the classifier, it then identifies the body parts while the person's dancing. And it's able to represent that in a computer format, and then based on that it scores the game and how accurate you are as being Elvis Presley or Prince in your dancing. Let's take an overview of what we're going to cover today. What's in it for you? What we're going to start with is what is machine learning. We're not going to go into detail on that. We're going to specifically look at how the random forest fits in the machine learning hierarchy. Then we're going to look at some applications of random forest. What is classification, which is its primary use? Why use random forest? What's the benefits of it? And how does it actually come together? What is random forest? And then we'll get into random forest and the decision tree. That's like the final step and how it works. And finally, we'll get some Python code in there and we'll use the case, the iris flower analysis. Now, if you don't know what any of these terms mean or where we're going with this, don't worry. We're going to cover all the basics and have you up and running and even doing some basic script in Python by the end. Let's take a closer look at types of machine learning. Specifically, we're going to look at where the decision tree fits in with the different machine learning packages out there. We'll start with the basic types of machine learning. There's supervised learning, where you have lots of data and you're able to train your models. There's unsupervised learning, where it has to look at the data and then divide it based on its own algorithms without having any training. And then there's reinforcement learning, where you get a plus or negative if you have the answer correct. This particular tool belongs to the supervised learning. Let's take a closer look at that, what that means in supervised learning. Supervised learning falls into two groups, classification and regression. We'll talk about regression a little later and how that differs. This particular format goes underneath classification. So we're looking at supervised learning and classification in the machine learning tools. Classification is a kind of problem wherein the outputs are categorical in nature, like yes or no, true or false, or 0 or 1. In that particular framework, there's the KNN, where the NN stands for nearest neighbor, naive Bayes, the decision tree, which is part of the random forest that we're studying today. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area, and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better, even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision 3 tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. We have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, we're going to create a data set 1 and a data set 2. We just split it in two. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to two lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second two, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has two or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out how does a decision tree work. So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, they're very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle. It's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree, very similar, but it's split differently. Instead of the first one being split by diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step which is loading the different modules into Python. And let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there. And let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower, and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Pandas is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the three that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into two different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25%, we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create two variables. We're going to create two new data frames. One's called train. One's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans, and let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a Panda thing, the DF columns, and we know the first 4 of them, 0, 1, 2, 3, that'd be the first 4, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first 4. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, PD. Factorize. What's factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this automatically treats this just like when we were up here and I typed in Y and it printed out Y instead of print Y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see injobs equals 2. You can see the random state equals 0. Those are the 2 that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the Sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the Setosa, the Virginica, and the Versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal length, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with Panda's data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a Panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, Setosa, Virginica, and Versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates three numbers. So we had three leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for Virginica, and it predicts a 0 for Versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have two equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these two are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next two steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, and it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually let's do the first 25, just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head. And you'll see it says Setosa, 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 Setosa. And they match. So the first one is what our forest is doing. And the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in. And then because I'm on the Jupyter notebook, I can do a control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes two sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versicolor, Virginica, and the actual species, Setosa, Versicolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have Versicolor where they meet, and you have Virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says Virginica, but it was supposed to be Versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction, and we ran it on test features. But, we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. What is naive Bayes? Let's start with a basic introduction to the Bayes theorem, named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing 2 coins. Here we have 2 quarters, and if we look at all the different possibilities of what they can come up as, we get that they could come up as heads, they can come up as head-tail, tail-head, and tail-tail. When doing the math on probability, we usually denote probability as a P, a capital P. So the probability of getting 2 heads equals 1/4. You can see on our data set we have 2 heads, and this occurs once out of the 4 possibilities. And then the probability of at least 1 tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting 2 heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with 2 coins it's easy to see, but when you have something more complex you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case, the first coin toss will be B and the second coin toss A. This can be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A after a given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our 2 quarters, and we'll notice that the first 2 probabilities of getting 2 heads and at least 1 tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4, or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with 2 coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in, and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the two heads and two tails and head tail, tail heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like, and then we're going to solve it in Python. And in here we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our three inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount, yes or no? Do we have a free delivery, yes or no? On those days, how many people made a purchase and how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy, yes or no? As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy. It would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally, we look at the probability of B if A. In this case, we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities, and based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB. If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367, which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all 3 independent variables. Now we can construct the likelihood tables for all 3 of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. We filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these three likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We are actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times the probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the three different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those three separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for three different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those three different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. Those are our three variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our three probabilities of A if B multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B, B being all three categories, did we have a discount with a purchase? Did we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29%, given these three different variables. So it's if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on and we're going to do two steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data, so if you have smaller amounts of data, this is a great, powerful tool for that. Handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjusts for that. Those formulas are very automatic, and so you can still get a very solid predictability even if you're missing data or you have overlapping data for 2 completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the 2 overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time so you can walk through it, since we walked through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines in classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. Roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor, inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x. If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplot library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since it's an inline setup, that we want the graphs to show up on this page. Without it, in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplot library inline. And then we're going to import NumPy as NP. That's NumberPython, which has a lot of different formulas in it that we use for both of our sklearn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as NP, NumPy as NP. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplotlibrary.pyplot as PLT, and you'll see that PLT is a very common setup, as is the SNS and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of pyplot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. The term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch 20 news groups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch 20 news groups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.targetNames. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp OS, MS, Windows.miscellaneous. And it goes all the way down to talkpolitics.miscellaneous, talkreligion.miscellaneous. These are the categories they've already assigned to this news group. And it's called Fetch 20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter Notebook, and let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target_names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into fetch 20 news groups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals fetch 20 news groups, subset equals test, and categories equals categories. Let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, line 58, lines 58, in article, etc. And you can scroll all the way down and see all the different parts to there. Now, we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter Notebook and walk through it. And here we are in our Jupyter Notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top, we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the sklearn features extraction.txt, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let it know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the tf-idf vectorizer is going to do for us. And then we're going to import our sklearn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes. Pretty easy to understand that, where that comes from. And then finally we have the Sklearn pipeline import make pipeline. Now the make pipeline is just a cool piece of code because we're going to take the information we get from the tf-idf vectorizer and we're going to pump that into the multinomial NB. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through, or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the tf-id vectorizer and then we're going to push that into the multinomial NB. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the train data, and then the train target. Now, the train data has the different articles in it. You can see the one we were just looking at. And the train.target is what category they already categorized that particular article as. And what's happening here is the train data is going into the tf-id vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, and then puts that into the multinomial NB. And once we go into our naive Bayes, we want to put the trained target in there. So the trained data that's been mapped to the TF-ID vectorizer is now going through the multinomial NB, and then we're telling it, well, these are the answers. These are the answers to the different documents. So this document that has all these words with these different weights from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels, and we're going to set that equal to model.predict. Most of the sklearn use the term .predict to let us know that we've now trained the model and now we want to get some answers. And we're going to put our test data in there because our test data is the stuff we held off to the side. We didn't train it on there and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there or have some missed labels? And then we're going to put that on a heat map so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline, that way my graph shows up on the inline here. And let's walk through the code and then we'll look at this and see what that means. So make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here from sklearn metrics import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborn, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And do we have other variables that go into the SNS.heatmap? We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS, Windows, miscellaneous. And then finally, we have our plt.x label. Remember, the SNS or the seaborn sits on top of our matplot library, our PLT. And so we want to just tell it x label equals a true is true. The labels are true, and then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides, because they have a black background they put in there that helps it shine a little bit better so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does, is you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it S, a string. And then we're sending it train equals train. We have our training model. And then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train and I put the equal for model. And then we're going to set the prediction equal to the model.predict S. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words, and then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNamesPredict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word, or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. And it comes back and says it's social, religion, Christian. That's pretty good. Now, note I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE, you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous. So when we take our definition or our function and we run all these things through, kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF, IDF vectorizer. We threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier. But they're important to know. One of the main uses for the naive Bayes is with the TF, IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction and our trained model.
And if you're one of the aspiring data scientists looking for online training and graduating from the best universities, or a professional who really sets to switch careers with data scientist by learning from the experts, then try giving a shot to Simplilearn's Caltech postgraduate program in data science in collaboration with IBM. The course link is mentioned in the description box below, and you will navigate to the course page where you can find a complete overview of the program being offered.
Before we dive into the SVM, let's take a look at applications of the support vector machine, at least some general ones that are commonly used with it. Face detection, text and hypertext categorization, classification of images, and bioinformatics. These are only but a few of those that are used with this SVM. As we go through this lesson, see if you can figure out what other ones you could apply it to, and also what you would want to use some other tools for. What's in it for you? Today we're going to cover about 6 different sections. We're going to start with what is machine learning, so we can see where the vector machine fits in. Why the support vector machine? What is a support vector machine? And understanding the support vector machine. Once we go through an understanding of how it works and what it looks like, we're going to look at the advantages of support vector machine and finally dive into a use case in Python where we'll write some script on it. Let's start with what is machine learning, and even more specific, where does the support vector machine algorithm fit in? The biggest split in machine learning is between the 3 categories: supervised learning, where we have data and we can train it; unsupervised learning, where we're just guessing at what we can make sense of the data; and reinforcement learning, where we reinforce a good or bad behavior. Since the SVM is specific to supervised learning, machine learning model learns from the past input data and makes future predictions as output. So we teach the model, we teach it what a strawberry is, and once the model is trained, it can identify a strawberry. That's what's meant by supervised learning. In the larger picture of the machine learning model, and under supervised learning, you can see that the support vector fits in under classification, deciding what yes and no is. And there is also a regression version, but it is primarily used for classification. Let's take a detour and see if we can connect this to the human experience and find out why support vector machine. So in this example, last week my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, what fruit did I just pick up from the fruit stand? After a couple of seconds, you can figure out that it was a strawberry. So let's take this model a step further, and let's, why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know are strawberries, and they're already labeled as such. We already have a bunch of apples, we know are apples and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case, you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case, we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of 2 categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken a labeled sample of data, strawberries and apples, and we draw on a line down the middle between the 2 groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where you have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have 2 groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we draw in 2 lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the two classes. Here you can see there's a clear split between the two different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the two. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the two support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have 2 sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a 2-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a 2-dimensional output. As you can see in this picture here, the 1D when transferred to a 2-dimensional makes it very easy to draw a line between the 2 data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a 2-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the 2 classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a 3-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high-dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data. Whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These 3 advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo and we have the young child going, "Dad, is that a group of crocodiles or alligators? Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the two groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves, and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here in the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice correction of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. Now let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are numpy as np and matplotlibary.pyplot as plt. Now, these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the numpy array. And I'll talk about that in a minute so you can understand why we want to use a numpy array versus the standard Python array. And normally it's pretty standard setup to use np for numpy. The matplot library is how we're going to view our data. So this has, you do need the np for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import and make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data. And we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn, or the SVM, is in 2 lines of code. And we see it right here with CLF equals svm.svc kernel equals linear, and I set C equal to 1, although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. It'll be a nice linear line instead of a full plane, so we're not dealing with a huge amount of data. And then all we have to do is do clf.fit x, y, and that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created 2 blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our 2 sets of data. They represent, one represents crocodiles and one represents alligators. And then we have our measurements. In this case, we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from NumPy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a NumPy array. It turns out that our makeblobs returns a NumPy array. And this notation is great because what it means is the first part is the colon, means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma, 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot, and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dot, so we can see them instead of real tiny dots. And then CMAP equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using 2 colors, 0, 1, and that's why we get the nice blue and the 2 different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets, and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process 1 line at a time. And so in this case, I'm processing 2 lines, and then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it, and you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here, and I'm going to paste that code in. And you'll see that the plot show is moved down below. Let's scroll up a little bit, And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show. So you should be asking, why are we redoing the same code? Well, when you do the plot show, that blanks out what's in the plot. So once I've done this plot show, I have to reload that data. Now we could do this simply by removing it up here, rerunning it, and then coming down here, and then we wouldn't have to rerun these first 4 lines of code. Now in this, it doesn't matter too much, and you'll see the plot show is down here and then removed, right there on line 5. I'll go ahead and just delete that out of there, because we don't want to blank out our screen. We want to move on to the next setup. So we can go ahead and just skip the first 4 lines, because we did that before. And let's take a look at the AX equals plt.gca. Now right now, we're actually spending a lot of time just graphing. That's all we're doing here. Okay, so this is how we display a nice graph with our results and our data. AX is a very standard used variable when you're talking about PLT, and it's just setting it to that axis, the last axis in the PLT. It can get very confusing if you're working with many different layers of data on the same graph, and this makes it very easy to reference the AX. So this reference is looking at the PLT that we created and we already mapped out our 2 blobs on. And then we want to know the limits. So we want to know how big the graph is. We can find out the x limit and the y limit simply with the get x limit and get y limit commands, which is part of our matplot library. And then we're going to create a grid. And you'll see down here we've set the variable xx equal to np.linespace, x limit 0, x limit 1, 30. And we've done the same thing for the y space. And then we're going to go in here and we create a mesh grid. And this is a numpy command. So we're back to our numbers Python. Let's go through what these numpy commands mean with the line space and the mesh grid. We've taken xx, small xx equals np line space, and we have our x limit 0 and our x limit 1, and we're going to create 30 points on it. And we're going to do the same thing for the y-axis. Now, this has nothing to do with our evaluation. It's all we're doing is we're creating a grid of data. And so we're creating a set of points between 0 and the x limit. We're creating 30 points, and the same thing with the y. And then the mesh grid loops those all together so it forms a nice grid. So if we were going to do this, say, between the limit 0 and 10 and do 10 points, we would have a 0, 0, 1, 1, 0, 1, 0, 2, 0, 3, 0, 4 to 10, and so on. You can just imagine a point at each corner of one of those boxes. And the mesh grid combines them all, so we take the YY and the XX we created and creates the full grid. And we've set that grid into the YY coordinates and the XX coordinates. Now remember, when we're working with NumPy and Python, we like to separate those. We like to have, instead of it being x comma 1, x comma y, and then x2 comma y2, and in the next set of data, it would be a column of x's and a column of y's. And that's what we have here, is we have a column of y's, and we put it as a capital YY, and a column of x's, capital XX, with all those different points being listed. And finally, we get down to the NumPy VStack. Just as we created those in the mesh grid, we're now going to put them all into one array, XY array. Now that we've created the stack of data points, we're going to do something interesting here. We're going to create a value z, and the z equals the CLF. That's our support vector machine we created, and we've already trained. And we have a dot decision function, and we're going to put the XY in there. So here we have all this data. We're going to put that XY in there, that data, and we're going to reshape it. And you'll see that we have the XX.shape in here. This literally takes the XX, resets it up connected to the Y, and the Z value lets us know whether it is the left-hand side. It's going to generate 3 different values, the Z value does. And it'll tell us whether that data is a support vector to the left, the hyperplane in the middle, or the support vector to the right. So it generates 3 different values for each of those points. And those points have been reshaped so that they're right on a line, on those 3 different lines. So we've set all of our data up. we've labeled it to 3 different areas, and we've reshaped it, and we've just taken 30 points in each direction. If you do the math, you have 30 times 30, so it's 900 points of data, and we separated it between the 3 lines and reshaped it to fit those 3 lines. We can then go back to our matplot library, where we've created the AX, and we're going to create a contour. And you'll see here where we have contour, capital XX, capital YY. These have been reshaped to fit those lines. Z is the labels. So now we have the 3 different points with the labels in there, and we can set the colors equals K. And I told you we had 3 different labels, but we have 3 levels of data. The alpha just makes it kind of see-through, so it's only 0.5 of the value in there. So when we graph it, the data will show up from behind it, wherever the lines go. And finally, the line styles. This is where we set the 2 support vectors to be dash dash lines, and then a single one is just a straight line. That's what all of that setup does. And then finally, we take our ax.scatter. We're going to go ahead and plot the support vectors, but we've programmed it in there so that they look nice, like the dash dash line and the dash line on that grid. And you can see here, when we do the CLF dot support vectors, we are looking at column 0 and column 1. And then again, we have the S equals 100, so we're going to make them larger. And the line width equals 1, face colors equals none. Let's take a look and see what that looks like when we show it. And you can see when we get down to our end result, it creates a really nice graph. We have our 2 support vectors in dashed lines, and they have the near data. So you can see those 2 points, or in this case the 4 points, where those lines nicely cleave the data. And then you have your hyperplane down the middle, which is as far from the 2 different points as possible, creating the maximum distance. So you can see that we have our nice output for the size of the body and the width of the snout, and we've easily separated the 2 groups of crocodile and alligator. Congratulations! You've done it. We've made it. Of course, these are pretend data for our crocodiles and alligators, but this hands-on example will help you to encounter any support vector machine projects in the future, and you can see how easy they are to set up and look at in depth.
Let's get started. What is probability? Probability is a branch of mathematics concerning numerical descriptions of how likely an event is to occur, or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1, where roughly speaking 0 indicates the impossibility of the event and 1 indicates certainty. The higher the probability of an event, the more likely is that the event will occur. Let's look at an example. A simple example is the tossing of a fair unbiased coin. Since the coin is fair, the outcome, that is heads and the tails, are both equally probable. The probability of heads equals the probability of the tails, and since no other outcomes are possible, the probability of either heads or tails can be said to be 1 by 2, which is also 50%. The probability of an event can be calculated by number of ways it can happen divided by the total number of outcomes. Now that we know about the probability, let's see if you can answer this question. What is the probability of drawing a jack and a queen consecutively from a deck of 52 cards without replacement? Here are your options. Post your answers in the comment section and let us know. Now let's move on to conditional probability. Let A and B be the 2 events associated with a random experiment. Then the probability of A's occurrence under the condition that B has already occurred and probability of B is not equal to 0 is called the conditional probability. It is denoted by PA/B. Thus we can say that PA/B is equal to PA intersection B divided by P of B, where PA/B is the probability of occurrence of A given that B has already occurred, and PB is the probability of occurrence of B. To know more about conditional probability, you can check our previous video which is specifically on conditional probability. Now let's move on to Bayes' theorem. The Bayes' theorem is a mathematical formula for calculating conditional probability in probability and statistics. In other words, it is used to figure out how likely an event is associated on its proximity to another. Bayes' law or Bayes' rule are the other names of this theorem. The formula for the Bayes' theorem can be written in a variety of ways. The most common version is PA/B is equal to P of B/A into P of A divided by P of B, where PA/B is the conditional probability of event A occurring given that B is true, and P, A and P of B are the probabilities of A and B occurring independently of one another. Let's solve a problem using the Bayes' theorem to understand it better. There is a cricket match tomorrow. and in recent years it has rained only 5 days each year. Unfortunately, the meteorologist has predicted the rain for tomorrow. Now, when it rains, the meteorologist correctly forecasts rain 90% of the time, and when it doesn't rain, he incorrectly forecasts rain 10% of the time. Let's calculate what is the probability that it will rain on the match day. So, the two sample spaces here are the events that it rains and it does not rain. Additionally, a third event is also there that meteorologist predicts the rain. So the notation for these events appear below. Event A1 is equal to it rains on the match day, event A2 that it does not rain on the match day, and event B is the meteorologist predicting the rain. Now in terms of probability, we know the following. Probability of A1 is 5 by 365 that it rains 5 days in a year, which will come out to be 0.0136. PA2 is 360 by 365, that is no days for 360 days in a year, which will come out to be 0.986. PB/A1 is 0.9. This signifies when it rains, the meteorologist predicts the rain 90% of the time. In a similar manner, PB by A2 is 0.1, that it does not rain, the meteorologist predicts the rain 10% of the time. Combining all this, we can calculate PA1/B, that is the probability it will rain on the given match day, given a forecast of rain by meteorologist. The answer can be determined using the Bayes theorem as shown below. So here's the formula of the Bayes theorem, and putting all the values that we have calculated in the previous slide, the probability that it will rain on the match day given a forecast of the rain by meteorologist will come out to be 0.111, which will be equal to 11.11%. So there's an 11% chance that it will rain on the match day given that the meteorologist has predicted the rain. I hope this example is clear to you. So what is analysis of variance? ANOVA is to test the differences among the means of the population by examining the amount of variation within each sample related to the amount of variation between the samples. This technique was invented by R.A. Fisher and is thus often referred to as the Fisher's ANOVA. Analyzing the variance tests the hypothesis that the means of two or more populations are equal. In a regression study, analysts use the ANOVA test to determine the impact of independent variable onto the dependent variable. So, what are its types? There are basically two types of ANOVA, which is a one-way ANOVA and a two-way ANOVA. When we are comparing more than three groups based on one factor variable, then it is said to be a one-way analysis of variance. For example, if we want to compare whether or not mean output of three workers is the same based on the working hours of the three workers, we'll use a one-way ANOVA. Now let's move on to two-way ANOVA. When factor variables are more than 2, then it is said to be a two-way analysis of variance. For example, based on working conditions and working hours, we can compare whether or not the mean output of 3 workers is the same. Now, let's discuss some key terminologies used in ANOVA. We'll start with the null hypothesis. The null hypothesis is the assumption that an event will not occur. A null hypothesis has no bearing on the study's outcome unless it is rejected. Alternative hypothesis. The alternative hypothesis is the logical opposite of the null hypothesis. The acceptance of the alternative hypothesis follows the rejection of the null hypothesis. H1 is the symbol for it. P-value. In statistics, the p-value, also called probability value, is the probability measure of finding the observed or more extreme results when the null hypothesis of a given statistical test is true. The p-value is a primary value used to quantify the statistical significance of the result of a hypothesis test. Now let's move on to alpha value. The alpha value is a criteria for determining whether test statistics is statistically significant or not. This test provides a p-value, which is the probability of observing results as extreme as those in the data, assuming the results are truly due to chance alone. An alpha value of 5% or lower is often considered to be statistically significant. Now let's try to understand these terminologies by taking an example. Let's assume that a new drug is developed with the goal of lowering the blood pressure more than the existing drug. So in this case, a null hypothesis will be that the new drug doesn't lower the blood pressure more than the existing drug. The alternative hypothesis will be that a new drug does significantly lower the blood pressure more than the existing drug. And the p-value will be the result from evidence like medical trials showing the positive results which will reject the null hypothesis. The F statistic will be the extent of difference between the means of different medical trials. The sum of squares will be the variation from the mean of different medical trials. And the mean will be the average of all the results from evidence like medical trials. Now let's understand the core concept between how the ANOVA works. The one-way ANOVA compares the means between the groups you are interested in and determines whether any of those means are statistically significant different from each other. Specifically, it tests the null hypothesis. If any of the group means is significantly different from the overall mean, then the null hypothesis in this case will be rejected. Now let's discuss the term F statistics, which is very much used in the analysis of variance. F statistics or F ratio is a statistical measure that tells us about the extent of difference between the means of different samples. Lower the F ratio, the closer are the samples to the means. If you have 3 different data sets, then this part will be the within group variance, that is the variance between the samples. This line will be the variance between the means of the different samples, which is also called between group variance. If the between group variance is large relative to the within group variance, the F statistic will be comparatively large to the critical value and therefore will be statistically significant. Now that we have covered almost all the theory regarding the ANOVA, let's try to understand how this is used in a real world example. Suppose you are a marketing manager of the product company. Your team has recently launched 3 new advertisements and you want to know if the 3 different types of advertisements affect mean sales differently. So how can you do that? You will use each type of advertisements at 20 different stores for 1 month and then measure the total sales of each store for a month. To observe if there is statistically significant differences in the mean sales between these 3 types of advertisements, we will conduct a one-way ANOVA. For calculating the ANOVA, you will use the type of advertisement as a factor and the sales as a response variable. Now that we have covered all the topics in ANOVA and have understood how it is used in a real world example, let's see how you can run an ANOVA test in Excel. Suppose you are a research scientist and you want to perform clinical trials to study the effectiveness of 3 drugs developed by 3 healthcare companies to cure a certain disease. The data below represents the time taken to cure the disease for different patients when they consume either drug A, B or C. The time is represented in terms of total hours and minutes. At the 0.05 level of significance, that is the alpha value, we need to test whether the mean time for the 3 drugs to cure the disease are equal. So how you can do that? We'll first move on to the data tab and then click data analysis. We'll select the ANOVA single factor and click OK. Now it is asking for an input range. Select the data you have on the table. We have the labels in our first row and the alpha is 0.05. For the output range, we'll get the output here on the same page. So we'll select some cell in the same page and we'll click OK. So you can see we have our analysis of variance table with the summary. Let's understand each term one by one. The average time taken to cure the disease after consumption of 3 drugs are 107, 90 and 96 hours approximately. The difference between the largest and the smallest mean is 17.47. Here, one significant observation is that the F value is greater than F critical value. So, this means we can reject the null hypothesis. It also means that the average time taken to cure the disease is not the same for all the 3 drugs. Using the paired comparison, we can conclude that the time taken by the drug A to cure the disease is more than time taken by drug C, and wait further, is more time taken by drug B to cure the disease. What is correlation? Correlation refers to a statistical relationship between the 2 entities. It measures the extent to which the 2 variables are linearly related. For example, the price and demand of a product is in correlation. They are linearly related. The value of correlation always lies between -1 to +1. There are mainly 2 types of correlation. The first one is positive correlation. A positive correlation means that the linear relationship is positive and the 2 variables increases or decreases in the same direction. The number of trees cut down and the probability of erosion are in correlation. When one increases, other also increases and vice versa. Negative correlation. A negative correlation is just the opposite. The relationship line has a negative slope and the variables change in opposite directions. For example, if you decrease the speed of the car, the time taken to reach the destination increases. This is a negative correlation. Correlation coefficient. The correlation coefficient, which is denoted by R, gives us a measure of the strength of the linear relationship between the two variables. The value is denoted by the letter R and it ranges from -1 to +1. If it is less than 0, it implies that there is a negative correlation. The -1 indicates there is a strong negative correlation between the variables. If R is greater than 0, it implies there is a positive correlation and +1 is the strongest point of a positive correlation. When R is equal to 0, we can say that there is no correlation between the variables. There are also some limitations of correlation. The first one is, correlation does not give you every insight on the data. Mean and standard deviation are still the important parameters to get the insight of a data. The second one is, the data will not produce a straight line every time and it will be difficult to predict the value of R just with the straight line or the slope of the graph. Now let's see some real life applications of correlation. If you take any e-commerce company whose website is accessed by millions of users all over the world, the company can look at all the data and they can measure how much time was spent by the customer and the respective money spent by the customer. We can also predict the unique users that visited the website and how it affected the sales in a day. The third application can be the patient blood pressure and the medication used. The level of patient blood pressure and the effect of medication on it can be in a correlation. Now let's jump onto Excel workbook to see how you can calculate the correlation coefficient. So here we are on the Excel workbook. If you see, we have the temperature in degrees Celsius such as 20, 25, 30, 40, 50 and 60 and the corresponding sales of ice cream in the units. To calculate the correlation, we'll use the correlate function. Now we have array 1 and array 2. So we'll select the array 1, that is temperature in degrees Celsius, and the array 2 will be our sales of ice cream. So you can see there's a very strong correlation between the temperature of a day and the sales of ice cream unit. If the temperature increases, the sales of ice cream unit increases, and if the temperature decreases, the sales of ice cream unit decreases. What is correlation? Correlation refers to a statistical relationship between the two entities. It measures the extent to which two variables are linearly related. For example, the increase in the height of the children is accompanied often by the increase in weight. The value of the correlation always lies between -1 to +1. There are mainly three categories of correlation. The first one is positive correlation and negative correlation. The second one is linear and nonlinear correlation. And the third one is simple, multiple and partial correlation. Let's discuss each of them one by one. Positive correlation. A positive correlation means that the linear relationship is positive and the two variables increases or decreases in the same direction, as you can see from the graph. For example, the calories you burn is directly proportional to the amount of time you run on a treadmill. On the other hand, a negative correlation is just the opposite. The relationship line has a negative slope and the variable changes in the opposite direction. That is, one variable decreases while the other increases. An example can be a student who has many absents has a decrease in grades. Now let's move on to discuss linear and nonlinear correlation. When we change the value of a variable which leads to a constant ratio change in other variable, then that relation is said to be linear. For example, the factory doubles its output by doubling the number of workers. On the other hand, a correlation is said to be nonlinear when the amount of change in one variable is not in constant ratio to the change in the other variable. For example, the change in radius of the sphere and the change in volume of the same sphere does not happen to be in the same ratio. Now let's discuss simple, multiple and partial correlation. When studying the relationship between the variables, when only two variables are involved, the correlation is said to be simple. In the multiple correlation, we measure the degree of association between one variable on the one side and all the variables together on the other side. And for the partial correlation, we study the relationship of one variable with one of the other variables, presuming that all the variables remains constant. Now that we know all the types of correlation, let's discuss the two major types to calculate the correlation coefficient. The first one is Pearson's correlation. Pearson's correlation coefficient is the test statistics that measures the statistical relationship between the two continuous variables. The Pearson's correlation coefficient is often denoted by R, and the formula to calculate the Pearson's relation coefficient is sigma xi minus x bar into I minus y bar divided by under root sigma xi minus x bar whole square and I minus y bar whole square, where R is the coefficient of correlation, x bar is the mean of x variable, and y bar is the mean of y variable, and xi and yy denotes the samples of variable x and y respectively. The Pearson's correlation coefficient is the best method to measure the association between two variables of interest because it gives information about the magnitude of the association or correlationship as well as the direction of the relationship between the two variables. The second best method is Spearman rank correlation. The Spearman rank correlation is used to discover the strength of a link between the two sets of data. The formula to calculate the Spearman rank correlation coefficient is rho is equal to 1 minus 6 sigma di whole square divided by n bracket n square minus 1, where rho is the Spearman rank correlation coefficient, di is the difference between the two ranks of each observations, and n is the number of observations. Let's begin. What is correlation? A correlation is a statistical relationship between two entities. It measures the extent to which the two variables are linearly related. In simple words, it is the measurement of strength of association between the two variables. For example, an increase in the price of commodity is always accompanied by decrease in demand. The value of the correlation always lies between -1 to +1. Types of correlation. There are mainly three categories of correlation. The first one is positive and negative correlation. The second one is linear correlation and nonlinear correlation. And the third one is simple, multiple, and partial correlation. Let's discuss positive and negative correlation. A positive correlation means that a linear relationship is positive and the two variables increases or decreases in the same direction, as you can see from the graph. An example can be, as the number of trees cut down increases, the probability of soil erosion also increases. In the same manner, a negative correlation is just the opposite. The relationship line has a negative slope, as you can see from the graph, and the variables changes in the opposite direction. That is, one variable decreases while the other increases. To understand this, an example can be, if a car decreases the speed, the time taken to reach the destination increases. To know more about the types of correlation, you can refer to our previous videos and you can find the link in our description. Now, what is regression? Regression analysis, like most multivariate statistics, allows you to infer that there is a relationship between two or more variables. These relationships are seldom exact because there is a variation caused by many variables, not just the variables being studied. In regression analysis, there are two types of variable. One is dependent variable and other is independent variable. Let's discuss what the both variable represents. A dependent variable is a variable whose value is influenced or to be predicted. The dependent variable is often denoted by y and is also known as a predicted variable. Whereas independent variable, which is denoted by x, is a variable which influences the value or is used for prediction. The independent variable is also known as a predictive variable. The line of regression. The regression line is a line which is used to describe the behavior of a set of data. In other words, it gives the best trend of the given data. Regression lines are useful in forecasting procedures. Its purpose is to describe the interrelationship between the dependent variable and independent variable. The regression equation of y on x describes the change in the value of y for given changes in the value of x and vice versa. In the regression line equation, x and y are the variables of interest in our data, with y the unknown or dependent variable and x the known or the independent variable. Let's discuss the two key terms in this graph. The first one is slope. Slope is the ratio of the vertical and horizontal distances between the 2 points on a line. And you can see y-intercept, which is the coordinate of the point at which the curve intersects an axis. There are some assumptions we take to create the regression model. The first one is, the dependent variable is assumed to be normally distributed. The values of the dependent variable are statistically independent. This means that when we select the sample of a particular x, it does not depend on any other value of y. And the third one is error values are statistically independent. Now let's discuss a simple regression model. A simple regression model is used to depict a relationship between variables which are proportional to each other, meaning the dependent variable decreases with the independent variable. The equation of a simple regression model is y is equal to b0 plus b1x plus e, where y is dependent variable, x is independent variable, b0 and b1 represents y-intercept and the slope of the line respectively, and e is the error variable. Now let's move on to Excel to calculate the regression coefficient of a given data. We are on our Excel workbook. In front of us, we have the data of temperature of the day and sales of the ice cream on that day. Let's try to understand the regression analysis and summary output using this data. So, the first step is to go to the Data tab and select Data Analysis. Then select Regression and click OK. We'll get this table. Select the Y range as the ice cream sales. This Y range is predictable variable, also called as dependent variable. For the input X range, we'll select the temperature in degrees Celsius. This is the explanatory variable, also called as the independent variable. One thing you should keep in mind is that both the X and Y column must be adjacent to each other. We have the label, so we'll check the label and we'll select the output range from G5. Check the residuals and click OK. Excel produces the following output. Let's analyze some key data. We got the R-score value to be 0.9676, which is very good. This shows that 96% of the variation in ice cream sales is explained by the temperature of the day. Closer to the 1, the better the regression line fits the data. Now let's move a little more and analyze this coefficient. If you look at the coefficient, you will get the equation of the regression line. In our case, it is minus 176.33 plus 27.68 into temperature of the day. Substituting the temperature of the day for any given day, we can find the sales of the ice cream. With the above discussion, we can conclude that there is a big difference between the correlation and regression, although these are studied together. Correlation is used to study whether the variables under study are correlated, whereas regression is used to establish the functional relationship between the two variables. The equation of the regression line is of form y is equal to fx plus c. Correlation is used to establish the strength of the association between the two variables that are being studied, whereas regression is used to make the future predictions on any given event.
And if you are one of the aspiring data scientists looking for online training and graduating from the best universities, or a professional who really sets to switch careers with data scientist by learning from the experts, then try going a short to Simplilearn Caltech postgraduate program in data science in collaboration with IBM. The course link is mentioned in the description box below, and you will navigate to the course page where you can find a complete overview of the program being offered.
Before we dive in and start going through the questions one at a time, we're going to start with some of the logical kind of concept that enters in a lot of interviews. In this one, you have two buckets, one of 3 liters and the other of 5 liters. You're expected to measure exactly 4 liters. How will you complete the task? And note, you only have the 2 buckets. You don't have a third bucket or anything like that, just the 2 buckets. And the object of the question like this is to see how well you are thinking outside the box. In this case, you're in a larger box. You have 2 buckets. And also the pattern which you go on. And what that means is if you look at the 2 buckets, and we'll show you their answer in just a second, you have a bucket with 3 liters and a bucket with 5 liters. And the first thought is, what happens if you go from left to right? So we have a direction. And what happens if you pour the 3 liters into the 5 liter bucket? Well, if you pour the 3 liters into the 5 liter bucket, you have an empty bucket of 3 liters. And what's really important here is thinking outside the box, you realize that you have a 5 liter bucket that has 3 liters in it and 2 empty liters. So you have 2 additional liters you can fill up. If we continue that process, we can pour from the left to right, from the small bucket to the large bucket. You can now measure in 2 additional liters into the 5 liter bucket. And 3 minus 2 is 1. And you can keep doing that. You can empty the 5-liter bucket in, pour those 3 liters in, that 1 liter in, and then you can pour 3 liters in. What's cool about these questions as you explore them is you realize there's multiple ways usually to solve them. I went from small bucket to big bucket. The Simplilearn team, their solution that they pulled out was you fill the 5-liter bucket and empty it into the 3-liter bucket. Now you're left with 2 liters in the 5-liter bucket. So that's great. We can empty the 3-liter bucket. So now we're going from large to small. Remember, we went from small to large. So you can go both either way, but you have to go one way or the other, it turns out. And you can empty the 3-liter bucket and pour the contents of the 5-liter bucket in it. So the 3-liter bucket now has 2 liters. And if it has 2 liters, that means it has an empty 1 liter. And by now you probably have guessed that if you have that empty space, you can start using that empty space of 1 liter as a measuring. So we fill the 5-liter bucket again, and we pour the water in the 3-liter bucket. It already has the 2 liters, and so we're only pouring 1 liter in there, and 5 minus 1 is 4. So interview questions, they break up into all kinds of different patterns. We have logic like this one, which is a lot of fun. We have questions that come up that are more vocabulary. List the difference between supervised and unsupervised learning. Probably one of the fundamental breakdowns in data science. And supervised learning uses known and labeled data as input. Supervised learning has a feedback mechanism. Most commonly used supervised learning algorithms are decision tree, logistic regression, support vector machine. And you should know that those are probably the most common used right now, and there certainly are so many coming out. So that's a very evolving thing, and be aware of a lot of the different algorithms that are out there outside of the deep learning. Because a lot of these work faster on raw data and numbers than a deep neural network would. Unsupervised learning uses unlabeled data as input. Unsupervised learning has no feedback mechanism. Most commonly used unsupervised learning algorithms are k-means, clustering, hierarchical clustering, the Aporia algorithm. And there certainly are more. I'm going to say k-means definitely is at the top of the list, and the hierarchical clustering, those two are used so many times. So really important to understand what those are and how they're used. And most important is understand that supervised learning is you have your data set where you have training data and you have all those different pieces moving around, but you're able to train it. You know the answers. And unsupervised, we're just grouping things together that look like they go together. How is logistic regression done? Logistic regression measures the relationship between the dependent variable, our label, what we want to predict, and the one or more independent variables, our features, by estimating probability using its underlying logistic function, sigmoid. And whenever I draw these charts, I always end up drawing them the right-hand side first, because you want to know what your output is. What is you want out of here? And the left-hand side, what do you have going in? So you have your in and out. You can see we have a nice labeled image here to help you remember this. We have our inputs, we have our linear model, we have our probabilities. What are the probabilities of it being a certain way based on these features coming in? The sigmoid function, and it's important to note that the sigmoid function is maybe the most commonly used, but it's only one of a number of functions that are out there. And the sigmoid function turns our probabilities into a value between 0 and 1, or very close to 0 and very close to 1, between 0.1 and 0.009. And based on that, we generate an answer, in this case is 0 or 1. How is logistic regression done? So last time we talked about the sigmoid function. Generally, depending on what your interview and level of math and what expertise you're going in for the market, you'll have to understand that formula of the probability equals 1 over 1 plus e to the negative y. And that's e to the base 2. So you have your probability function or your sigmoid function, which pushes it. As you can see, we have a nice visual of that, and that helps a lot to have that visual on the sigmoid function. You definitely should know your y equals m times x plus c, your basic Euclidean geometry of forming a line, and the slope plus the intercept, the y-intercept. And then you have your natural log, and the natural log is to the e as opposed to a base 2 or base 10. So your natural log to the e of the probability over 1 minus a probability equals your m times x plus c, or your Euclidean line. That helps a lot as far as the graphing and understanding the sigmoid function. So we'll just keep pushing on to question number 3. Explain the steps in making a decision tree. And I noticed last time we brought up the decision tree in the forest, a lot of questions came up. What is the difference? So let's go through that. When you make a decision tree, you're going to take the entire data set as input. You're going to calculate entropy of the target variable as well as the predictor attributes. And remember, entropy is just how chaotic chaotic is it? So if you have like, banana and grapes and oranges, if you're mixing in fruit and that's your data coming in, you have all these different objects that are so separate from each other, and the more they become uniform, the lower the entropy. And we call that information gain. So we gain information on sorting different objects from each other. So you have your entropy, you have to calculate your information gain of all attributes, and then you choose the attribute with the highest information gain as the root node. So if you can separate your group and each group, chaos in each group is lowered, whichever split lowers the chaos the most, that's where you split it, and that's your root node. At that point, you repeat the same procedure on every branch till the decision node of each branch finalized. So understanding that setup is pretty important as far as decision trees, and you can see here we have a nice visual of a decision tree. For example, if you want to build a decision tree to decide whether we should accept or decline a job offer, since these are interview questions, that's a good one to ask. And just as a tip, you should be pretty aware of the formula for entropy and information gain. So you need to look those up if you don't remember those. And the salary, if it's greater than 50,000, no, decline the offer. Yes, it's got a good salary. The commute is greater than an hour. Yes, decline the offer. No. Offers incentives. Yes, accept the offer. No incentives, decline the offer. So we use decision tree pretty much for everything if you want. And if you have a decision tree, then you also should understand how do you build a random forest model. And remember that a random forest is built up of a number of decision trees. So if you split your data up into a lot of different packages and you do a decision tree in each of those different groups of data, the random forest is bringing all those trees together. So how do you build a random forest model? Randomly select k features from a total of m features, where k is less than m. Among the k features, calculate the node D using the best split point. Split the node into daughter nodes using the best split. Repeat steps 2 and 3 steps until leaf nodes are finalized. Build forest by repeating steps 1 to 4 for n number times to create n number of trees. So you can see it's got the same build pattern as the tree, but instead you're building a number of different trees, little small trees, so it all have an n leaf node. Random forest has a vote at the end, and whoever gets the most votes wins. That's the answer. How can you avoid overfitting of your model? Very important question in any kind of mathematical, scientific, data science setup, in any of them. There are 3 main methods to avoid overfitting, and you should really understand overfitting. Overfitting means that your model is only set for a very small amount of data and ignores the bigger picture. Keep the model simple. Take into account fewer variables, thereby removing some of the noise in the training data. Good advice for any programming at all. Use cross-validation techniques such as k-folds cross-validation. Use regularization techniques such as lasso that penalize certain model parameters if they're likely to cause overfitting. And you should also be well aware that your cross-validation techniques, that's like a pre-data, or your lasso and your regularization techniques are usually during the process. So when you're prepping your data, that's when you're going to do a cross-validation, such as like splitting your data into 3 groups, and you train it on 2 groups and test it on 1, and then switch which 2 groups you test it on, that kind of thing. So can you solve, another one of these, I love these things. There are 9 balls, out of which 1 ball is heavy in weight, and the rest are of the same weight. In how many minimum weighings will you find the heavier ball? And when we say weighing, think of a scale where you can put objects on one side and the other, and you can see which side is heavier. And you want to minimize that. You want to split the balls up in such a way that you're going to do as few measurements as you can. You will need to perform 2 weighings. So you can get it down to just 2 weighings. And I always think if there's 9 balls, I'm going to divide them into 3 groups of 3. Place 3 balls on each side. So you can just randomly pick 6 of the balls and 3 on one side, 3 on the other. And if they balance out, both sides are equal, then you know the heavy weight isn't in any of those. So out of the remaining 3 balls from step 1, take 2 balls and place 1 ball on each side. A little tricky there because I always want to put all 3. I want to put 2 on one side and 1 on the other, but no, just randomly pick 2 of those, put 1 on each side. If they balance out, then the left out ball, the one you didn't measure, will be the heavier one. Otherwise, you'll see it in the balance. You'll see which one's heavier because you'll take one of the balls down. Now we go to scenario B, where they did not balance out. So now we know which side has a heavier ball in it. And it's just very similar to what we did before. If the balls in step 1 do not balance out, then take those 3 balls that had the heavier side on them and reproduce step 2 to find out the heavier ball. Difference between univariate, bivariate, and multivariate analysis. And hopefully, if you know a little Latin, it'll kick in there that you have uni and you have bi and you have multi, because the answer is in the words themselves. So the first one, this type of data contains only 1 variable, so that's the univariate. Purpose of the univariate analysis is to describe the data and find patterns that exist within it. So when you only see one variable coming in this case we're using height of students, you're limited as far as what you can do with that data. So you can come up and draw different patterns and conclusions from those patterns using the means, the median, the mode, dispersion, range, minimum, maximum. So we're describing the data. So all those words would describe the data, and that's about all you can do with data like that. There's no correlation, there's nothing to go beyond that as far as guessing or predicting anything. So we move into bivariate. Uni means 1, bi means 2. Bivariate, this type of data involves 2 different variables. The analysis of this type of data deals with causes and relationships, and the analysis is done to find out the relationship among the 2 variables. And this is always a favorite one because everybody loves ice cream in the summer when it's hot, and very few people go for ice cream in the winter when it's really cold, so it's easy to see the correlation in the data. The temperature and ice cream cells in summer season. And you can see here where the temperature goes from 20 to 35, and as the temperature goes up, so does the cells of ice cream. It goes from 2,000, I'm not sure 2,000 of what, so I'm guessing it's a very large chain, because if they're selling 2,000 ice cream cones, and they have a lot of business, good for them. A little vendor on the corner selling 2,000 ice cream cones a day and 3,100 the next day. Here, the relationship is visible from the table that temperature and cells are directly proportional to each other. So the hotter the temperature, we can predict an increase in cells. So the word prediction should come up. So we have description and prediction. When the data involves 3 or more variables, it is categorized under multivariate. It is similar to bivariate, but contains more than one dependent variable. In this example, another really common one, the data for house price prediction, the patterns can be studied by drawing conclusions using mean, median, and mode, dispersion, or range minimum, maximum, etc. And so you can start describing the data, that's what all that was, and then using that description to guess what the price is going to be. So this is very good if you're in the market and you have already looked at the area and you already know that a 2-bedroom, 0-floor, 900 square foot house usually runs about $40,000. You can guess what the next one that looks similar to it is. And I'll just throw in another word in there I don't see very often unless you're really a hardcore data science. We talked about describing the data, descriptive. We talked about predictive, and there's also postscriptive. Postscriptive means we're going to change the variables to try to guess what the outcome is if we change what's going on. So that would be the next step. But that usually doesn't show up unless you're dealing with some really hardcore data science groups. What are the feature selection methods to select the right variables? There are 2 main methods for feature selection. There's filter methods and wrapper methods. And when you're filtering before we discuss the 2 methods real quick, the best analogy for selecting features is bad data in, bad answer out. So when we're limiting or selecting our features, it's all about cleaning up the data coming in so it's cleaner and is more representative of what we're trying to predict. Filter method. Filter methods as they come in, we have linear discrimination analysis, Anova, chi-squared. Chi-squared is probably the most common one. And these are all part of pre-processing. We're taking out all the outliers, all the things that have a difference that is very different from the data we're looking at, the odd ones. And sometimes you take the odd ones out and then you analyze them separately to see why they're odd. But remember your filter methods, you want to pull all that weird stuff out. Wrapper methods, on the other hand, are forward selection, backward selection, recursive feature elimination. And one of the most important things to remember about wrapper methods is they're very labor intensive. You have to have some pretty high-end computers if you're doing a lot of data analysis with the wrapper method. And just quickly, forward selection means you have all your different features. They're off to the side, and we test just one feature at a time, and we keep adding them in until we get a good fit. Backward is we have all the features, and we run a test on that to see how well it does, and then we start removing features to see what works. And recursive, which is the most processing-hungry algorithm out there, goes through and just recursively looks through all the different features and how they pair together. But again, we have filter method and wrapper method, and it's important to understand that we're sorting the data out and finding out which features are going to represent the data the best and which ones are not going to really add any value to our models. Let's jump to number 8. In your choice of language, write a program that prints the numbers from 1 to 50, but for multiples of 3, print fizz instead of the number, and for the multiples of 5, print buzz. For numbers which are multiples of both 3 and 5, print fizz buzz. And this really is testing your knowledge in iterating over data. Very important. My sister, who runs at the university the data science team, is in charge of their department, it's the first question she asks in her interview of anybody who comes in is, how do they iterate through data? So if this question comes up a lot and it's very important you have an understanding, and there's actually a slight error on this code, which I'll point out in just a second. The concept is we have fizz-buzz in range, and you have range 51, which in this case goes from 0 to 51. And I'm going to challenge you to see if you can catch the error, and I'll tell you at the end of the code where the error is. What that means is that we're going to go through all the numbers 0, 1, 2, 3, 4, and we're going to process through this loop. If the remainder of fizz-buzz divided by 3 equals 0, and fizz-buzz divided by 5 also equals 0, then print fizz-buzz. Continue. And else if fizz-buzz divided by 3 equals 0, then print fizz, continue. Else if fizz-buzz divided by 5 equals 0, print buzz, continue, and print fizz-buzz. You print the answer. In this case, fizz-buzz is either going to be the number we generated, which is 0, or it'll be the fizz-buzz, fizz, or buzz. Whew. That's a mouthful. Now, if you didn't catch the error in the code, which is always a fun game, find the error, it has to do with the range. And it's important to remember the range here says range to 51. That's 0 to 51, which is correct. We want to go to 51 because it stops. It gets to 50 and it stops. So that's 0 to 50. But if you remember, the question asks from 1 to 50. So the range should be 1, 51, not just 51, which does 0 to 51. In this particular script, in Python, you could leave out the continue, but the continue in this script skips the next else if, so it doesn't keep processing it going down. And in programming, a lot of scripts you don't need the continue answer, so it would depend on what script you chose. And there's probably some other ways to do this. It's a lot of fun. And you can see here from the output, we end up with fizz-buzz for 0, which shouldn't be there. 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz-buzz, 11, fizz, and so on. It sounds like a drinking game from my college days. So long ago, many decades ago. You are given a data set consisting of variables having more than 30% missing values. How will you deal with them? Oh, the joy of messy data coming in. Ways to handle missing data values. Data set is huge. We can just simply remove the rows with missing data values. It is the quickest way, i.e. we use the rest of the data to predict the values. You just go in there and say any row of our data that has a NA in it, get rid of it. That doesn't work with smaller data. So with smaller data, you start running into problems because you lose a lot of data. And so we can substitute missing values with the mean or average of the rest of the data using Pandas data frame in Python. There's different ways to do this, obviously, in different languages. And even in Python, there's different ways to do this. But in Python, it's real easy. You can do the df.mean, so you get the mean value. So if you set mean equal to that, then you can do a df.fillNA with the mean value. Very easy to do in a Python Pandas script. And if you're using Python, you should really know Pandas and NumPy, NumPython and Pandas data frames. For the given points, how will you calculate the Euclidean distance in Python? So back to our basic algebra from high school. Euclidean distance is the line on the triangle. And so if we're given the points plot 1 equals 1, 3, plot 2 equals 2, 5, we know that from this we can take the difference of each one of those points, square them, and then take the square root of everything. So the Euclidean distance equals the square root of plot 1, 0 minus plot 2 of 0 squared plus plot 1 of 1 minus plot 2 of 1 squared. Mouthful there. And you can remember if you have multiple dimensions that go past 2 dimensions, you could have plot 3 can simply be the distance from plot 1. You only need to do one side of that. Or plot 2, you can do either way and square that and take the square root of that. Another mind bender. How to calculate something, how to figure out the solution to something. What is the angle between the hour and minute hands of a clock when the time is half past 6? So you want to kind of imagine that clock where the large hand is pointed down to the 30 and the other half is going to be right between the 6 and the 7 because it's half past 6. There's actually a couple ways to solve this, but let's take a look and see how they did it. Note, a clock is a complete circle having 360 degrees. In 1 hour, the hour hand covers 360 over 12, so it equals 30 degrees for each hour. In 1 minute, the minute hand covers 360 degrees over 60 minutes, or 6 degrees per minute. The minute hand has traveled for 30 minutes, so it has covered 30 times 6, which equals 180 degrees. So we know that's 180 degrees from the 12. The hour hand has traveled for 6.5 hours, 6.5, 6.5, so it's covered 6.5 times 30, which equals 195 degrees. The difference between the two will give the angle between the two hands, thus the required angle equals 195 minus 180 equals 15 degrees. And this is nice the way they solved it, because you can now punch in any kind of time within reason. The hard part is on the hours, is you have to be able to convert the hours into decimals. Explain dimensionality reduction and list its benefits. Dimension reduction refers to the process of converting a set of data having vast dimensions into data with lesser dimensions, fills, to convey similar information concisely. It helps in data compressing and reducing the storage space. It reduces computation time as less dimensions lead to less computing. It removes redundant features. For example, there's no point in storing a value in two different units, meters and inches. And I certainly run into a lot with this with text analysis. I've been known to run a text analysis over a series of documents, ends up with over 1.4 million different features. That's a lot of different words being used. And if you do what they call connect them, you connect two words together, now you're up to 4.8 million different features, and you start having to figure ways to bring that down. What can we get rid of? That kind of thing. So you can see where that can get really high in on processing, and learning how to reduce the list dimensions is very important. How will you calculate eigenvalues and eigenvectors of a 3x3 matrix? And what they're really looking for here is when you write it out, for the eigen is that you know that you're going to use the lambda. That's the most common one. Obviously you can use any symbol you want, but lambda is usually what they use. And that you do it down the middle diagonal. And so when you take that matrix and you take the characteristic equation, you end up with the determinant, and that's the minus 2 minus lambda, minus 4, 2, minus 2, 1 minus lambda, 2, 4, 2, 5 minus lambda. And that's what they're looking for, and you know that's equal to 0. So when you're doing a matrix in the eigen setup with the eigenvectors, that's all going to come out equal to 0. And then you can go ahead and write the whole equation out. So we can expand the determinant, as you can see right here, the minus 2 minus lambda times, it's a mouthful. I'll leave it up here for a second so you can look at it. When you break it down into the algebraic functions, you end up with minus lambda cubed plus 4 lambda squared plus 27 lambda minus 90 equals 0. So now we have a nice algebraic equation built from the eigenvectors. And always remember, you can hit the pause button, and you can also send a note. Send a note to Simplilearn if you have more questions on vectors or on this. Definitely have that resource available to you, or post down in below on the YouTube video comments. And so when we calculate the eigenvalues and eigenvectors of a 3x3 matrix, as we continue on down the math of this, and to be honest, I really don't like working with matrices like this. It's important to understand the math behind it, and it's important to know the code just enough so that you're not lost when someone's explaining it or it comes up when I'm working on different data science models. Of course, if you're dealing with the high-end math side of it, then you better know this. First is by hit and trial, so you try in different variables to solve for 0, and you can come in here and you'll find that if we put in the 3 in there, we end up with a 0 at the end, and substitute the 3. Hence, we end up with lambda minus 3 as one of the factors. And you can do the math going out on that, where we have lambda cubed minus 4 lambda squared minus 27 lambda plus 90 equals lambda minus 3 times lambda squared minus lambda minus 30. So eigenvalues based on that one are 3, minus 5, and 6. And then from there we can calculate the eigenvector for lambda equals 3. And you can see here where the matrix as we write it out is the minus 5, minus 4, 2, minus 2, minus 2, minus 2, 4, 2, 2. That was from the beginning. Put in the x, y, and z equals 0, 0, 0. And so when we put in those numbers and we calculate them out, we have for x equals 1, we have the minus 5 minus 4y plus 2z equals 0, minus 2 minus 2y plus 2z equals 0. And subtracting the two equations we just had, we get 3 plus 2y equals 0, y equals minus 3 over 2, and z equals minus 1 over 2. That's going back to the first equation. And similarly, we can calculate the eigenvectors for minus 5 and 6. How should you maintain your deployed model? Ooh, distribution time, my favorite. I spent 10 years in software distribution. So first thing, and this is true not just of your data science model, but of any computer code going out there. This is basic setup can work, although usually there's a little added steps in there. First, we're going to monitor it. So we have a constant monitoring of all the model is needed to determine the performance accuracy of the models. So yeah, we want to just keep an eye on it. We want to make sure they're accurate. We want to make sure that whatever they're supposed to predict, or I threw in that bonus word, postscript, where you change something and you want to figure out how your changes are going to affect things, we need to monitor it and make sure it's doing what it's supposed to do. Evaluation metrics of the current model is calculated to determine if new algorithm is needed. And then we compare it. The new models are compared against each other to determine which model performs the best. And then we do a rebuild. The best performing model is rebuilt on the current state of data. And this is interesting. I found this out just recently. If you're in weather prediction, the really big weather areas have about 7 or 8 different models depending on what's going on. And so you actually have almost a little forest going on there where they're like, which model is going to fit best, and this is what we're going to use to predict the weather with. So not only do you don't necessarily get rid of the models, but you figure out which models fit data of what's going on, or the current state of data. What are recommender systems? Most commonly used nowadays in marketing, so a very big industry understanding recommender systems predicts the rating or preference a user would give to a product. And they're split into 2 different areas. One is collaborative filtering, and a good example of that is the Last.fm recommends tracks that are often played by other users with similar interests. So people who, if you're on Amazon, people who bought this also bought that. This got me a few times. And then there's content-based filtering. And we're looking at content instead of looking at who else is listening to the music. They use the example Pandora, which uses the properties of a song to recommend music with similar properties. So you have collaborative filtering and content-based filtering. How to find RMSE and MSE in linear regression model. Hopefully you remember what the 2 acronyms mean, because that is like half the answer. We have the root mean square error and the mean square error in linear regression model. So we're looking for error. The RMSE and the MSE are the 2 of the most common measures of accuracy for a linear regression model. And you can see here we have the root mean square error, RMSE equals, and this is the square root of the sum of the predicted minus the actual squared over the total number. So we're just looking for the average, mean. So we're looking for the average over the n. And the reason you need to know about the difference between RMSE versus MSE is when you're doing a lot of these models and you're building your own model, why do you need to take the square root of it? It doesn't change the value as far as the way you're using it, because you're looking as to see whether the error is greater or less than. So why add that extra computation in? So a lot of models use the MSE, which indicates the mean square error, or the average error. And it's the same formula minus the square root at the end, or across the whole thing. Another riddle to solve. If it rains on Saturday with a probability of 0.6, and it rains on Sunday with a probability 0.2, what is the probability that it rains this weekend? And the trick in probabilities on this case is we need to know what is the probability of it not raining. What's the chance of it not raining on Saturday? And if it doesn't rain on Saturday, we want to take that and combine that with the chance of it not raining on Sunday. The total probability, which in this case we're just going to use 1, minus the probability that it will not rain on Saturday, so that's 1 minus 0.6. We're going to take that as a union, which we simply just multiply them together, of the probability that it will not rain on Sunday. And it's important to recognize the union here, or and you can see by the formula down here, we end up with 0.68 or 68% chance that it will rain on the weekend. And there are a couple other ways to solve this, but this is probably the most traditional way of doing that. How can you select k for k-means? So first you better understand that what k-means is, and that k is a number of different groupings. And most commonly we use is the elbow method to select k for k-means. The idea of the elbow method is to run k-means clustering on the data set where k is a number of clusters. Within the sum of squares, WSS is defined as the sum of the squared distance between each member of the cluster and its centroid. And you should know all the terms for your k-means on there. And with the elbow point, and again, here's our iteration in our code. We talked about that earlier. You iterate starting with, usually you don't start right at 1, but you might start with 2, 3, or 4. And you just see where it comes out, and you can see the nice elbow there, which is easy to see graphically, where the number of k clusters and the WSS value drops, and then it just kind of flattens out, and there's no reason to take the k-means any further. What is the significance of p-value? Oh, good one. especially if you're dealing with R, because that's the first thing that pops up. P-value typically less than or equal to 0.05 indicates a strong evidence against the null hypothesis, and you should know what a difference, why we use null hypothesis instead of the hypothesis. So you reject the null hypothesis. Very important, that term null hypothesis, in any scientific setup and also in data science. It doesn't mean that it's true. It means that there's a high correlation that it's true. So if your null hypothesis means it's not true, your hypothesis has a high correlation that it's probably true. And if the p-value is typically greater than 0.05, it indicates a weak evidence against the null hypothesis. So you fail to reject the whole null hypothesis, and if you reject that, then your actual hypothesis is probably not true. The correlation of your data with what you think it's saying is probably incorrect. And if you're right at the cutoff of 0.05, it's considered to be marginal. Could go either way. And again, you can use that p-value on different features to decide whether you're going to include your features as far as something worth exploring in your data science model. How can outlier values be treated? Ooh, good one. You can drop outliers only if it is a garbage value. So sometimes you end up with like one outlier that just is probably someone's measurements way off. Height of an adult equals ABC feet. This cannot be true, as height cannot be a string value. In this case, outliers can be removed. If the outliers have extreme values, they can be removed. For example, if all the data points are clustered between 0 to 10, but one point lies at 100, then we can remove this point. And again, sometimes you just look for the outliers so you can see what's going on, if there's something unusual there. So maybe the equipment's not calibrated correctly. If you cannot drop outliers, you can try the following. Try a different model. Data detected as outliers by linear model can be fit by nonlinear model. So be sure you are choosing the right model. So if it has like more of a curved look to it instead of a straight line, you might need to use something other than just a straight line linear model. Try normalizing the data. This way the extreme data points are pulled to a similar range. If you can use algorithms which are less affected by outliers, example random forest. So there's another solution, is you can come up with the random forest, which a lot of times completely bypasses your outliers. How can you say that a time series data is stationary? Oh, that's an interesting term. Stationary, meaning it's not moving, but it's a time series. We can say that a time series is stationary when the variance and mean of the series is constant with time. And the graphic example is very easy to see. We have our the variance is constant with time, so we have our first variable y and x being the time factor and y being the variable. As you can see, goes through the same values all the time. It's not changing in the long period of time. So that's stationary. And then you can see in the second example, the waves get bigger and bigger, so that's non-stationary. Here the variance is changing with time. Again, we have y, which stays constant, so that if you look at the bigger picture, it's the same wave over and over again. And then of course we have where the wave is growing in size going up. It can also go down, so it'd also be non-stationary. How can you calculate accuracy using confusion matrix? Oh, great one. Confusion matrices are so useful when you're taking that first look at data, and also when you're showing the shareholders and you want to ask them for money. How can you calculate accuracy using confusion matrix? So you have your total data that we're looking at is 650, and you have your predicted values and your actual values, and you have your predicted P and your actual P. And so when we look at this, you'll note that if the predicted P and the actual P are 262, but our predicted P also had 15 that weren't correct. So you can see there's a false positive there of 15. And the same thing with the N. You can see where N predicts N, and it has a false negative of 26 out of the total number of N values in there. And so we can do an accuracy on there. The true positive plus the true negative is our total observations. So you have a total of 0.93 accuracy, or 93%. And just a quick note on this, this is so important, because it's one thing if someone is being diagnosed with, say, cancer. This is life-death, or is my nuclear reactor going to blow up? Suddenly, if the P is the probability of it blowing up, and this, let's say you have 15, that's a lot less than, say, the 26 chances of it blowing up. So the actual domain of your data is very important. So if you're non-positive, you don't really care about the predicted value having non-positive as positive, because they're going to go do a biopsy on the cancer or whatever anyway. But you're very interested if you have a positive, an actual positive value, which is looked at as negative. a false negative. That's really important in that domain, depending on what domain you're in. Write the equation and calculate precision and recall rate. And so continuing with our confusion matrix, I was just talking about the different domains. We have the precision equals 262 over 277. So your precision is the true positive over the true positive plus false positive. And the recall rate is your true positive over the total positive plus false negative. And you can see here we have that 262 over 277 equals a 94%. And the recall over here is the 262 over 280, which equals 9.9 or 90%. And oh good, we're going to take a pause for another brain teaser. If a drawer contains 12 red socks, 16 blue socks, and 20 white socks, how many must pull out to be sure of having a matching pair? The last time I went through these kind of brain teaser things was like 20 years ago, and I had 6 people sitting across the table waiting for my answer. That's kind of mind-numbing when you're in an interview like that. Hopefully you're not stuck in an interview like that. But on this, you need to ask yourself, how many different colors of socks are there? So they've thrown a lot of extra data in here that you don't need to solve the answer. The answer is 4. An example, your first pick is white, your second pick is red, third pick is blue, so no pairs yet. And that means when you get to the fourth pick, there's a 100% chance you're going to have a match. So the most is going to be 4 that you ever have to pull out of your drawer. If it was 4 colors, the answer would be 5, and so on. It doesn't matter how many white socks you have or how many red socks or blue socks, different pairs you have. It's the different colors, a number of different colors. People who bought this also bought recommendations seen on Amazon as a result of which algorithm? Ooh, we covered this earlier. Recommendation engine is done with collaborative filtering. Collaborative filtering exploits the behavior of other users and their purchase history in terms of ratings, selection, etc. It makes predictions on what you might interest a person based on the preference of many other users. And this algorithm, features of the items are not known. And we have a nice example here where they took a snapshot of a sales page. It says, for example, suppose X number of people buy a new phone and then also buy tempered glass with it. Next time when a person buys a phone, he'll be recommended to buy tempered glass along with it. And if you remember the vocabulary words we covered earlier, this is the recommendation. This is collaborative. The other word was content-based. So looking at things with similar content versus collaborative, which is similar people. And remember, you're not going to know every vocabulary word, but it also doesn't hurt to get your 3x5 cards out and make yourself a vocabulary stack of cards. Buy an app on your phone for it. SQL query. I remember back in the 90s, it was so important to know SQL query and only a few people got it. Nowadays, it's just part of your kit. You have to know some basic SQL. So write a basic SQL query to list all orders with customer information. And you can kind of make up your own name for the database. And you can pause it here if you want to write that down on a paper. And let's go ahead and look at this. We have to list all orders with customer information. And so usually you have an order table and a customer table. And you have an order ID, a customer ID, order number, total amount. And then from your customer table you have ID, first name, last name, city, county. And so if we're going to write in SQL with this, we're going to select, keyword there for SQL, selecting, order number, total amount, first name, last name, city, country. So that's the columns we're going to look at. We're going to do that from our order, where we're going to join it with our customer, and we're going to join it on the order customer ID equals the customer ID. So very basic SQL query that's going to return a table of data for us. You are given a data set on cancer detection. You've built a classification model and achieved an accuracy of 96%. Woo, 96%. Why shouldn't you be happy with your model performance? What can you do about it? That's an interesting one because this comes up. That's one of the standard data sets on there is for cancer detection. Cancer detection results in imbalanced data. In an imbalanced data set, accuracy should not be based as a measure of performance because it is important to focus on the remaining 4%, which are the people who were wrongly diagnosed. We talked a little bit about this earlier. You have to know your domain. This is the medical cancer domain versus weather domain. Weather channel, they can get by with 50% wrong. In cancer, you don't want 4% of the people being wrongly diagnosed. Wrong diagnosis is of a major concern because there can be people who have cancer but were not predicted so. In an imbalanced data set, accuracy should not be used as a measurement of performance. Which of the following machine learning algorithm can be used for inputting missing values of both categorical and continuous variables? So we have a couple choices here. We have k-means clustering, we have linear regression, we have the NN, nearest neighbor, and decision tree. And which of the following machine learning algorithms can be used for inputting missing values of both categorical and continuous variables? Now, certainly you can use some pre-processing to do some of that, but you should have gone with the K nearest neighbor, because it can compute the nearest neighbor, and if it doesn't have the value, it just computes the nearest neighbor based on all the other features. Where when you're dealing with k-means clustering or linear regression, you need to do that in your pre-processing, otherwise it'll crash. Decision trees also, although there's some variance on that too. Can you solve? Another riddle, always fun ones. Given a box of matches and 2 ropes, not necessarily identical, measure a period of 45 minutes. And in this particular setup, the ropes are not uniform in nature, and the rope takes exactly 60 minutes to completely burn out. So each rope takes up to 60 minutes to burn out. And there's actually a couple different solutions to this. But let me go ahead. And one of the things is they're not uniform in nature. So even though they take 60 minutes... Anyways, let's go ahead and see what they did to solve it. And then we can also look at different options. We have 2 ropes, A and B. Light A from both ends and B from one end. Okay. When A is finished burning, we know that 30 minutes have elapsed and B has 30 minutes remaining. Now light the other end of B also, so that the remaining part of B will burn, taking 15 minutes to burn. This we have gotten 30 plus 15 equals 45 minutes. Excellent solution. Mine, which I like, was to take one rope, fold it in 2, so we know it's a half hour. Take the other rope, fold it in 4 places, so we know that that one's 15 minutes, and then you can just connect the 2 and burn it straight across. I think they're trying to cover that by saying they're not regular. The ropes have some irregularities. Maybe that's what they meant by that, is you couldn't do something like that. But that's my solution. Below are the 8 actual values of target variable in the train file. So we have a training file, not to be confused with the train on the tracks. We have 0, 0, 0, 1, 1, 1, 1, 1. What is the entropy of the target variable? We mentioned earlier that you should know your entropy and how to calculate the entropy. What is the entropy of the target variable? So we have a couple options here. We have minus 5 over 8 logarithm of 5 over 8 plus 3 over 8 logarithm of 3 over 8. Okay, let's just see where they got those numbers from. We have 1, which is going to be 5 ones and 3 zeros, and then we have a total of 8. Okay, and then we have the option of 5, which is number of ones, 5 8 logarithm of 5 eighths plus 3 eighths logarithm of 3 eighths. And we also have 3 eighths logarithm of 5 eighths plus 5 eighths logarithm of 3 eighths. And then we kind of reverse those numbers around. And let's see what you're going to get here. Which one did you think it was? You should check the first one. So what is the entropy of the target variable? The key there is the target variable. So we're looking at the target in this case is going to be 1. Usually that's what you're looking for. And so the entropy of that one, we want to subtract out the entropy of the non-target variable. Whoops, I had that backwards. We're looking at 0, so we want to subtract out the 5 eighths from there. So 5 eighths logarithm 5 eighths, or negative 5 eighths logarithm 5 eighths plus 3 eighths logarithm 3 eighths. And they have the hint on the bottom, entropy equals I of P of N. So we have a negative P plus P and N times the logarithm base 2 of P over P plus N minus the N over P plus N times the logarithm 2 of N over P plus N. We want to predict the probability of death from heart disease based on 3 risk factors: age, gender, and blood cholesterol level. What is the most appropriate algorithm for this case? So we have 3 features, and we want to know the predictability of death. Okay, a little morbid there. Choose the right algorithm. Do we want to use logistic regression for this, linear regression, k-means clustering, or the Aporia algorithm? And if you selected logistic regression, then you probably got the right answer. Linear regression, remember, deals with you take your line and draw a line through the data. And of course, you don't necessarily have to use a straight line. There's other means for that. But you're dealing with a lot of numbers. And k-means means we're just going to cluster objects together. With the logistic regression, though, you can mix those things together in buckets. So really, the logistic regression is what you want to use in that model, would be the most apt fit. After studying the behavior of a population, you have identified 4 specific individual types who are valuable to your study. You would like to find all users who are most similar to each individual type. Which algorithm is most appropriate for this study? Certainly, identifying census in just about a lot of different markets is common, so maybe they have a census or whatever it means. But let's take a look at some of the different algorithms we might use on this. We have k-means clustering, linear regression, association rules, and decision trees. And I'll give you a hint. We're looking for grouping people together by similarities, and by 4 different similarities, so very specific. They gave you one of the values, specifically the K value. So K-means clustering would be great for this particular problem. You have run the association rules algorithm on your data set, and the 2 rules, banana apple is associated with grape, and apple orange is associated with grape, have been found to be relevant. What else must be true? So this would challenge you to understand association rules. You could picture in this particular one, you're going shopping, and you almost always see somebody who has bananas, they usually have grapes in their bag also. And somebody who has apples usually has grapes in their bags. And then apples and oranges is also associated with grapes. And let's go ahead and take a look at that. And we have a couple different options here. First one is banana, apple, and grape, orange must be a frequent item set. Not so much. Banana, apples, oranges must be relevant rule. Grape is common with banana, apple, must be a relevant rule. And how about grape, apple must be a frequent item set? Let's go back and take a look at that. And we notice that we have bananas, apples to grapes. We have apple, orange to grape. Boy, there's a lot of grapes and a lot of apples in there. And so if you said the last one, grape and apple must be a frequent item set, then you got it correct. Your organization has a website where visitors randomly receive one of 2 coupons. It is also possible that visitors to the website will not receive a coupon. You have been asked to determine if offering a coupon to visitors to your website has any impact on their purchase decision. Which analysis method should you use? And so let's go ahead and start by giving you another hint and give you some limiting your selection. We have a one-way ANOVA. K means clustering, association rules, and student t-test. So obviously you should know what each one of these means, but let's take a look at the question again. So you want to know which method should you use to see if the coupon's valid for their purchase. Well, we're not clustering and we're not associating things together. We want to know the end result. Student t-test also drawing that little t in boxes and switching them around. There's really only one answer that works in here, and that's the one-way ANOVA.
With that, we have reached the end of this advanced data science full course. If you have any questions, please feel free to comment and we will have it answered for you as soon as possible. Until next time, thank you for watching, stay safe, keep learning, and get ahead.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.